Yes.
Okay, so the first three talks in the session will be virtual, and the first one is from Bianca Fucinato on exploring the impacts of cold pool dynamics in Monin, insights from hurricanes. Take it away.
Okay, thank you. So good morning, everyone. I'm very happy to open the session today. And I am Bianca Fusinato, a master's student at the National Institute for Space Research. And I'm gonna share with you today my master's work entitled Exploring Cold Pool Dynamics in Mana. And one of my study cases I show here in this animation is Hurricane Elaine, for example. So cold pools have been broadly studied from observational cases to idealized cases, and the literature points to those negatively buoyant air masses with descents within the downdrafts. When touching the surface, it spreads horizontally and creating what is known as gust fronts. So gust fronts helps organize and generate new convection. And one can see here, for example, at Hurricane Barrel, those arc shapes being created by those gust fronts. So the parameterization recognizes cold pools through the buoyancy excess parameter, beta x, and is defined as a difference between the moist static energy from the downdraft and the moist static energy from the environment, as I show here. And I'm also picturing the morphology of the gust front itself, and one can see, for instance, the horizontal propagation GF and the vertical propagation WDF at the leading edge of the gust front, as well as the cold pool depth. And one can write the equations for those terms, as I show here. And for more information, one could check in details the paper as I wrote it here. So the gust front propagation itself depends on the mean cloud layer horizontal speed, as I show here. And this term thereby depends on the environmental wind, which is computed within two level pressures. So the gust front itself propagates accounting to this mean cloud layer horizontal speed, the 2D horizontal propagation of the gust front velocity, and the environment wind itself. And the prognostic equation for the beta x parameter I show here, and it takes into account a advection term, a diffusion term, and also the source being mostly by the downdraft, and also a sink term which takes into account the cold pool lifetime. And here I gather an image from the paper, and I show the buoyancy excess computed over the Amazon rainforest. And those arc-shaped convection here shows the peak of the buoyancy excess at the leading edge, meaning prompt to develop new convection. So the cold pool parameterization is coupled with the Grell-Freitas convective parameterization, and this is doing by modifying the cloud work function, as I show here. So now the cloud work function takes into account the buoyancy excess parameter, and also is modified the convective adjustment time scale. So now it depends on the vertical velocity at the leading edge of the gust front. And also it was add a new trigger function depending on the kinetic energy, as I show here. So in my study, I used the MONA system. So it's the next generation model for Brazil, South America, and Caribbean. It's based on MPAS with the default physics. And here on the right side, I showed a output from ANAM. And one can see the instruction measures right here at the rainfall. And right now, the MONA includes new parameterizations, such as in the convective scheme, the code pool, but also in the PBL scheme, the shock MF implemented by Guilherme Tavares. So for my simulations, I listed here the physics book that I'm using. And initially, I ran it at 30 kilometers horizontal resolution, but I changed it in some sensitivity tests. The model itself has 55 vertical levels, and I ran it globally with Euro 5 initial conditions, as well as a static sea surface temperature. So the goal of my work is to access code pool parameterization inside hurricanes, specifically looking at the track, intensity, and rainfall. So I would like to briefly introduce my first study case, Hurricane Beryl. So it first began at June 28th, and at the main developing region, and rapidly intensified as a Cat 1 hurricane. So right after the first landfall, Hurricane Beryl reaches the peak of Cat 5 hurricane and entered at the Yucatan Peninsula as a Cat 2, further weakening over land, but then got reorganized over the Gulf of Mexico or Gulf of America, and made the landfall in state of Texas as a Cat 1 hurricane. For my simulations, I started in July 3rd, as I picture here. One can notice that is right after the Cat 5 hurricane phase. So I'm just playing right now the trajectories outputs. I computed the trajectory basically looking the minimum mean sea level pressure point around the best track data. And the best track data set is represented here as labeled NOAA. I also compared with ERA 5 dataset using the same algorithm. And one could look at the effects of code pools by looking here at the curve CP on, meaning code pool enable, and CP off, meaning code pool disable. So those black and red curves. I also did some sensitivity tests, for instance, 1 hour meaning 1 hour of code pool lifetime. I changed the resolution into 15 kilometers horizontal resolution. I also tried to start earlier the forecast and get some optimal configuration of those parameters inside the code pool parameterization. And I labeled this as follows. So one major feature that I face here is at the Yucatan Peninsula. One could notice that CPON is the closest curve to the best track dataset, but then for further leading times in the forecast, this behavior changes. And looking at intensity, and by intensity, I mean the central pressure in the hurricane and also the maximum wind speed, one could notice that the model is not fully capturing the behavior solved in the best track dataset, and also is predicting some intensification here a bit earlier. And this was also observed on the maximum wind speed. At the rainfall, the behavior of the model is for the light thresholds, rainfall is occurring at overestimation, as well as for the extreme precipitation rates. But at the moderate rainfall here, one could notice that the CPON with the simulations with the code pool parameterization is actually doing quite good in comparison with the GPMI merged dataset. And this can be also confirmed looking at the CDF distribution. And one can see, for instance, here at the moderated rainfalls, the curves is merged. So code pool on for moderate rainfall is doing quite good. For the morphology aspect of this distribution, I gather some snapshots of the hurricane made by the simulations with the parameterization at the 30 kilometers, at the 15 kilometers, and without it, the parameterization at 30 kilometers. And one can see that the code pool parameterization is helping to make more organized convection and also producing some rain band and spirals, as shown here. And this those structures are even enhanced by the resolution. So the second study case is Hurricane Elaine, as I shown at the beginning. And it was a hurricane that formed near Mexico and then rapidly intensified as a Cat 1 hurricane, peaking at Cat 4 hurricane near state of Florida, which caused many storage surge in the Florida coast. And then when the hurricane enters the continental part, it got weakened, but interact with frontal boundary, increasing the rainfall, producing extremely flooding observed, especially in the Carolinas, picking up, for instance, 30 inches of rainfall. And the simulations I got beginning at September 24 at 12 UTC, but sorry, but I also tried with September 25, 0 UTC. So for this trajectory and intensity, I got some similar behavior with Barrow. But here, the major difference is with the optimal configuration, and this configuration is actually improving both trajectory and intensity. As one can see, for instance, here on this period, the closest line to the best track data set is the optimal configuration. So with the code pool and by tuning some parameters within the parameterization, one could get really good improvements in those aspects. And at the rainfall, I got some really close similar results to Barrow, but here we are investigating if GPM is capturing the extreme rainfall, especially the extremist rainfall amounts that occur in Elaine. And finally, I show you that even for Elaine, the organization into rain bands and also the continental part of convection is being organized with code pools. So to wrap up, we implemented and tested the Freitas 2024 code pool parameterization in MPAS Monan. The scheme was applied into two different 2024 season hurricane. Several improvements can be seen, especially in the rain bands and even at horizontal resolutions. And I did not show you, but we also tried at 60 kilometer horizontal resolution, and we also could see those rain band formation with the parameterization. The parameter 10 significantly influenced the results, as I show you, especially in the hurricane Elaine. And thinking about that, we are planning to apply more parameter calibration via ensemble experiments. We also thinking applying to the Amazon mesoscale complexity system, for instance, the squall lines and maybe even Madden-Julia oscillation. Quantify also the convective organization, for instance, measuring the nearest neighborhood distance between those convective cores. And we are also coupling the cold pool parameterization with the sea spray AC spray parameterization to look if there are any improvements. So I would like to thank my supervisor, Dr. Saulo Freitas, as well as my collaborators, George and Haishim, for their support. Thank you for the organizers for the opportunity to speak and opening this session. This work was founded by CNPq and CAPS agencies. And if one can get more information by looking at my GitHub, and I leave here the QR code too.
All right, thank you. We're going to move on to the next speaker for time, but I think you can answer questions online.
Sure, thank you.
So our next speaker is Wisimo, who will be talking about sensitivity analysis of WRF model microphysics scheme on the simulation of super typhoon Saula and the potential impact of sea surface salinity on rapid intensification.
Hello.
Good morning.
Good morning. Is it clear? Can we see the screen?
Yes.
Okay, thank you so much. Okay. So, good morning, everyone. Thank you for this valuable opportunity to share our ongoing research in this workshop. So, my name is Hui Sumo. I'm from the Hong Kong University of Science and Technology. Today, I will be present my study on the sensitive analysis of the WRF model in simulating the super typhoon Solar, with a focus on the potential effects of sea surface salinities on its rapid intensification. And today's my talk will focus on two key aspects. The first one is the WRF model sensitive analysis, evaluating the effects of the different parameterization scheme and initial conditions on the solar chest and the intensity. And the second one is the UV model's case study on the sea surface salinity, the impact of the sea surface salinity or the rapidly intensifying the tropical cyclone over South China Sea. So let's see this case called Solar. In 2023, Hong Kong experienced the issuance of the hurricane signal number 10 due to the typhoon Solar. We noticed that here is the rapid intensification process. We define as a minimum increase of the 30 knots in the maximum sustained surface wind of a TC within a 24 hours period. This solar case brought maximum sustained wind speed of 210 km per hour near its center to Hong Kong, and surpassing the previous records of 205 km per hour in 1979, and setting the highest wind speed record in the city histories since the record began in 1946. The entire cities came to complete standstill, and after the government issued the hurricane's signal number 10, over 1,200 construction sites across the Hong Kong were shut down, while the shopping mall, the school, and the private service agencies ceased operation. The typhoon caused an estimated 500 million Hong Kong dollars in direct economic losses in a single day. So also setting a 5-year record for the highest daily disruption caused by this typhoon. So to better understand this terrible typhoon, we conducted a WRF simulations analysis. We used the WRF as the meteorological field inputs, and the observed wind speed are from the IBCHS and the satellite data. This table shows the various parameterization scheme we test in our sensitive experience. The red highlighted one performed relatively well in the simulating the event. Our model set up U3 nested degrees with the high resolution inner grid designed to follow the water's movements, as you can see in the figure on the right. And that's my grid setting. Additionally, we also employ the MPAS model, which utilizes the same parameterization scheme as the WRF. The simulation initials at the 12 UTC on August 28, 2023, using the ERA5 meteorological data. But unlike the traditional nested approach, MPAS features a variable resolution mesh with local refinement down to 3 kilometers. Now we will comparing this result in more detail. We can see this figure on the left-hand side. The WRF runs start at different times. You can see the black line is the observed TC check, and the different color denotes the 00 UTC on the 27th, then the 00, 06, and the 12 UTC on the 28th, respectively. We observe significant variation in both wind speed and check simulation depending on the initialization time. Simulations initials closest to the RI moment show the best algorithm with the observed check. During the typhoon's decay phase, earlier initializations exhibit notable check deviation and tend to overestimate the wind speed. Now turn to the right panel, and here we compare the simulation using 3 different initialization datasets. For example, the FNL and the ERA5 and also the SAR simulated data. Interestingly, while all 3 produce remarkable similar trends and match the observation quite well, but here is the kicker. None of them actually capture the solar's rapid intensification process. This process remains elusive in our simulation. And then we compare the MPAS results like the WRF, the MPAS also produced a chart that matched the observation well, but we noticed something interesting. It showed a clear upward trend. You can see the green line here, and during this late stage, the green lines can overestimates the observations, and also the side-by-side compare with some reveals a key divergence. After August 13th, the warp shift northward while MPAS deviates the southward. Although the WRF and MPAS using the same physics scheme, but they show difference on the same disk case simulation. We also simulate another 2 cases, the Typhoon Konus and the Bibinka. The black line shows observations and the blue represent the GFS forecast, while the red and the yellow are the MPAS simulations. We can see that even when the initials with the same GFS data, the MPAS outperform the GFS in both checks and intensity predictions. And when we changed the physics scheme, there was a huge change in landfall location, landing in Taiwan. And for the Bibanka's case, the MPAS correctly predicts the Bibanka's landing for location and the RI, outperforming the EC and the GFS data set. So just now we discussed the simulations ability of the pure atmospheres model for the typhoon. However, the energy source of the typhoon does not only come from the atmosphere itself, and the ocean is the full tent of typhoon. When a typhoon moves, it will stir up the ocean and trigger the upwelling of the cold water, but at the same time, the rainfall brought by the typhoon will also prevent the vertical mixing process of the ocean, and a change of the sea surface salinities will further regulate the intensity of this oceanic feedback. To capture this key process, we need a couple model, an atmosphere, ocean, and wave couple model. The Unified Wave Interface Couple model we call the UWIN-CM was developed by the University of Washington, which integrates the WRF for the atmosphere component, the HICOM for the ocean component, and also the UNWM for the wave component. The model used multiple observational datasets to drive. For the atmosphere forcing, we utilize the EC or the GFS datasets. For the ocean's condition, it comes from the HICOM based on the GeoFS 3.1 datasets, and also include the topographies, MODIS, land use classification, and bathymetry, etc. In this couple model, we can also simultaneously get the hourly high-resolution simulation of the parameters like the salinities, temperatures, and sea surface height, significant wave height, and the jet coefficient, etc. This is my model configuration. We can see the left-hand side figure. The red outermost spot is the WRF D01 atmosphere domain, and next to the inside, you will see the blue one is the HICOM ocean domain, and the green one combine the wave model and the WRF D02 domain. The innermost red box is the high resolutions vortex following WRF D03 domain. We first compare the 10-meter wind speeds. The wind speeds predicted by the UWIN-CM model has been improved compared with the ERA5 datasets. In particular, the wind speed at the typhoon center has been significantly enhanced, while the ERA5 itself just underestimated. And the left animation used the UR5 reanalysis data, and the right one is the result of the couple models. As can be seen, the couple model can simulate the moving track of the typhoon, and the typhoon range is larger than the EC's datasets. And you can see that here is the sea surface height and the current simulation of the typhoon solars. In the South China Sea, the interaction between the ocean and atmosphere can significantly influence the sea surface height. During a typhoon event, intense wind and the low pressure system alter the distribution of the water, causing a rise in the sea surface height in the storm center due to the piling of the water, known as the storm surge, and this increased in sea surface heights occur due to the accumulation of water driven by the strong wind and the low pressure associated with the typhoon. This increase can lead to the dangerous coastal flooding, intensifying the impact of the typhoon on the populated area. Here are the significant wave heights and the wind simulation of the typhoon solar. Along with the typhoon chart, the significant wave height has been increasing. We can see along the typhoon chart, the typhoon made the landfalls and it brought serious disaster to the Hong Kong area. Then we use the reanalysis data to explore the chain of the different variables during the typhoon period. In the upper left time series figure, there are temperature, salinities, and the wind speed respectively. The green bar below is precipitation, and the scatter point are the square buoyancy frequency of different layers. We call the N square, which indicate the ocean stratification. The more stratified the water column, the higher the buoyancy frequencies. We found that during the earlier stage of the tropical cyclones, the intense precipitations generated by the typhoon inhibit the vertical turbulence and lead to a reduction in salinity within the upper ocean layer. This process further hampered the upwelling of the deep cold water, preventing its ascent to the ocean surface. Hence, it helped to maintain the high sea surface temperatures, favoring the typhoon intensification. On the right are the spatial distribution maps of the ocean heat contents and the square buoyancy frequencies. Along with the typhoon charts, it can also be observed that the high OHC values and the increased stratification make this region becomes more favorable area for the RI of the typhoon. So, in summaries, while our model can successfully capture the typhoon solar charts, but it still underestimates both the rapid intensification and the maximum wind speeds. Besides, the intense precipitation generated by the typhoon induced the enhanced near-surface stratification. This in turn results in a strong oceanic inhibition of the vertical missings. Such conditions are highly favorable for the intensification of the tropical cyclones. And thank you for your attention, and I'm very happy to welcome any question or the comment with the quick pressures.
All right, thank you. There's time for a question or two from the audience or online. Do you have a sense of why you're not capturing the rapid intensification for this
Yeah,
case?
and so far I know that this is a very chicken case. I cannot. Before this time, I also listened to another workshops, and they says is this solar case. So far no one can predict the intensities. Actually, we still are working on the physical scheme, but it didn't have the result right now, but we will keep doing this. So I also want to share this case and welcome all of the experts to figure out this problem. Yeah, and this solar case is also have the loops on the very beginning, so it's also the main problem. That's why the rapid intensification cannot capture.
All right, thank you.
Thank you.
All right. So we will move on to the next speaker. Our next speaker is Tianhong Zhang, talking about using large language models to produce literature reviews, usage and systematic biases of microphysics parameterizations in 2,699 publications.
Good morning, everyone. My name is Tian Hang, and I'm from the University of Manchester. Today, I will share with you an overview of our work titled Using Large Language Models to Produce Literature Reviews, Usage and Systematic Basis of Microphysics Parameterizations in 2,699 publications. This study focuses on building a review of microphysics schemes. So, why is this important? First, microphysics parameterizations play an important role in numerical weather prediction models by simulating sub-grid scale microphysical processes and hydrometeor populations. Second, a systematic understanding of how these schemes are actually used in practice and what kind of biases they introduce is essential for improving model performance and advancing the field. To achieve this goal, we propose building a meta-analysis database focusing on peer-reviewed journal articles that use the WRF model for precipitation simulations. Using large language models offers a time and labor-saving way to extract and analyze information at scale, making it much more feasible to carry out this kind of review. There are three main steps in our study. collect the literature, check the relevant criteria, extract information from articles. The first step is collecting literature. We began by conducting a literature search in the Web of Science and Scopus, using keywords like WRF, precipitation, rain, and snow. We removed duplicates contained in both the Web of Science and Scopus data. We then manually excluded book chapters, conference abstracts, literature reviews, and journal publications in languages other than English. Finally, to focus on precipitation simulated using the WRF model rather than coupled models, we filtered out abstracts involving WRF-Chem, WRF-CMAC, and WRF-Hydro. After these steps, a total of 3,559 articles remained. Next, we checked the relevance of the articles. We put all 3,559 abstracts into GPT-4 Turbo and asked a simple question: does this study apply the WRF model for the precipitation simulation? If the model answered yes, we considered the article relevant. If it answered no, we excluded it. Based on this process, 2,803 abstracts were marked as relevant. To check the reliability of GPT's response, we manually reviewed 897 abstracts and compared the results. The model achieved an accuracy of 90.1%. After identifying the relevant articles, we downloaded full text of 2,803 relevant articles as PDF fields. However, due to copyright issues or retraction, 104 of them were not found. As a result, we finalized a database of 2,699 publications for information extraction. To guide the extraction process, we designed 8 questions related to microphysics, parameterizations, and precipitations. These questions were designed to help us systematically understand each study's WRF model configuration, including microphysics, radiative cumulus, boundary layer, surface layer parameterization schemes, the simulation domain, and the performance of the microphysics schemes used. There are prompts used in our study. Then we supplied the 2,699 publications to GPT-4 Turbo as context and asked GPT-4 Turbo these 8 questions. To validate the information extracted, we select 300 publications to manually check the accuracy of the answers produced by GPT-4 Turbo. This table shows the effectiveness of extracting WRF model configuration and performance information from each article using GPT-4 Turbo, demonstrating excellent performance with an average accuracy of 94% for all 8 questions. Specifically, question 1, our model configuration has the highest accuracy of 98%, but question 4 on the performance of the WRF model has the lowest accuracy of 86%. Let's look at the microphysical parameterizations used in these studies. See this figure. We can see 95% of publications used box microphysics schemes to simulate precipitation. Only 5% used the bin schemes. Among box schemes, non-microphysical schemes accounted for most of articles. So in the analysis that follow, we will focus on these schemes. This figure shows the distribution of different microphysics bulk schemes by year from 2003 to 2023. Before 2020, the one-moment microphysics schemes were dominant. Among these schemes, the WSM6 scheme was the most popular. After 2020, double moment microphysics schemes became the popular scheme, the most popular of which was Thomson's scheme. This figure shows a global map of the number of publications associated with WRF simulated precipitation. The location is where the precipitation occurred in each publication. China, particularly Southeast China and the Sichuan Basin, and the Central United States have the most articles, more than 220 in each region in total. The relatively low concentration of WRF-based studies in Europe may reflect institutional or national preferences for alternative modeling systems, such as models developed by ECMWF, DWD, or the Met Office, which are extensively used in operational forecasting and academic research. This figure shows global maps of the number of publications using different schemes. The Lean WSM3, WSM5, and WDM microphysics schemes were more frequently used in Southern Asia and China, whereas the Ferrier, Thomson, and Morrison schemes were more commonly used in the United States. We summarize the performance of non-microphysics schemes. GPT-4 Turbo summarized a general tendency of overestimated or underestimated precipitation for each microphysics scheme in each article. In this figure, we can see 7 schemes: Thomson, WSM6, Ferrier, Morrison, WSM5, Lin, WSM3 have more articles reporting over estimation than those reporting underestimation. This figure shows the geographical distribution of the difference between numbers of publications reporting overestimation and underestimation based on the domains of the model simulations from each article. expect simulations using the Lin, Ferrier, and GCE schemes that tended to underestimate over almost all locations. The remaining 6 schemes tended to overestimate precipitation. We extract RMSE and correlation coefficients from articles. This figure shows the distribution of RMSE and correlation coefficients values for non-microphysics games. We can see Farrier and WSM5 schemes have the low median RMSE value and narrow ranges. There are still a lot of future work to be done when it comes to understanding systematic errors. For instance, we can look into how these errors vary with seasons and times of day, explore their behavior across different types of weather phenomena, investigate the reasons for these errors. There is a summary of the presentation. Quantitative meta-analysis of journal articles can quantify how models are used and suggest characteristic species. Large systematic samples of literature can be obtained by combining manual and automated methods. Mapping performance of the microphysical parameterizations reveals characteristics of spatial variations. Thank you.
All right, thank you. Are there any questions? All right, so if you find a study that may mention, for example, like over predicting precipitation in one location and under predicting it in another location in the same study, do both of those data points make it into this database?
Actually, if one study reporting both under and over estimation, we will exclude this this article. We only considered one articles that have a general results, like just overestimate or just underestimate.
Hi, is it working? It's working, right? We're good? Yeah, okay. This is really interesting work. I really enjoyed your presentation. My question was about the performance of the Chat GPT Turbo sort of system that you were using. I thought it was really interesting that the performance evaluation, it was like 86% accurate, which was based on sort of the other questions that you asked. Like it seemed like that was the thing that that Chat GPT struggled the most with. And I just wondered if you had any idea as to why it might have struggled more in sort of evaluating or sort of gathering information about the performance of the microphysics schemes. Yeah, I was just curious if you had any thoughts on why.
Thank you. Actually, if we ask the the GPT-4 Turbo, the performance of the macrophysics games, I think it's a question that GPT need to summarize the article or find other questions for other questions, there are specific answers in the articles. However, sometimes in the articles there is no specific answers, so GPT need to guess or let me see. Speculates the answer.
Yeah, that makes sense. Thank you.
Thank you.
All right, thank you. We're going to move on to the next speaker, Ronnie Abulafia Rosenzweig. We'll be talking about snow cover plays a non-dominant role in the longstanding surface cold bias in WRF NOAA MP over the Western U.S.
All right. Good morning, everyone. So this study was focused on the role of snow cover in the 2-meter temperature longstanding cold bias, particularly looking at WRF NOAA MP simulations across the Western United States. I'd like to acknowledge the co-authors that provided valuable contributions on this work. In particular, highlight that these co-authors are from many different labs and universities, which really underlines the widespread interest in resolving this long-standing cold bias issue. There we go. So a recent study, Rudisil and others in 2024 did a compilation and found that there were 44 studies with various configurations with unique land and atmospheric model couplings that consistently found cold biases. So this really highlighted that this is a widespread issue and it's not model specific. Many of these studies hypothesized that a key contributor that was partly or largely contributing to the cold bias were overestimates in the snow cover fraction, which can have important albedo feedbacks, which could impact the 2-meter air temperature. So we looked to evaluate this hypothesis and see if resolving the snow cover fraction bias could help resolve the longstanding cold bias issue. So we started with our overarching hypothesis that reducing the systematic biases in the snow cover area would significantly reduce cold biases in the mountainous regions of the Western United States. So in recent years, we developed a new snow compaction and ground snow cover fraction scheme for the NOAA MP land surface model, both of which were published in James, with the snow cover fraction paper being published very recently as of last week. We developed a scale-aware snow cover fraction parameterization that calculates snow cover fraction now as a function of the model spatial resolution, addressing that the baseline parameterization in NOAA MP had a tendency to overestimate the snow cover fraction, and that this overestimation became larger at coarser resolutions, indicating a scale dependence of the bias. So for instance, shown here are box model simulations of the snow cover fraction, where the model was driven with inputs from the 1 kilometer SNODAS data set, which is a snow data assimilation system for the United States. And the baseline simulation tends to overestimate the STC mod SCAG remotely sensed ground snow cover fraction, with this bias increasing particularly at the coarser resolutions, whereas the enhanced box model using our new parameterizations for snow compaction and ground snow cover fraction, we're able to reduce this bias and also remove the scale dependence of this bias. So we looked to evaluate the impact of implementing our new snow compaction and ground snow cover fraction schemes in WRF-NOAA MP simulations across the Western US and consider its role in the cold bias issue. So we started with a baseline simulation, which followed a similar configuration to the recent CONUS 404 dataset that was published in 2023. There were some slight modifications in this baseline configuration, specifically with alterations to some of the NOAA MP physics options. And we did find a result that's consistent with the 44 previous publications that I had shown in the prior table, where there is this widespread cold bias across the Western United States. This was our expected result here. On a regional scale, the mean bias was around minus 1.3 degrees Celsius, but this bias is particularly pronounced in high elevation regions. Specifically, for example, for elevation bins larger than 3,000 meters, the bias ranged from around minus 2.4 to minus 5.3 degrees Celsius on average, with this variability based off of averaging through different land cover classifications. And then we ran a twin simulation, except we were running with our new snow cover fraction and snow compaction parameterization. And you see that the bias pattern is quite similar. There are some reductions in the bias, regional average reduction of 20%, changing from a bias from minus 1.3 to around minus 1 degree Celsius. But the high elevation biases are still quite pronounced, even after implementing the new snow cover fraction and snow compaction parameterizations, with a mean bias ranging from around minus 2.9 to minus 5.2 degrees Celsius. So this indicates that even with our new snow cover fraction and snow compaction parameterizations implemented in the coupled WRF NOAA-MP simulations, this cold bias was still present. So we did some further investigation into this, looking at the outputs from these two simulations, the baseline and what we're calling the AR new simulation, which is the simulation that implements the new snow cover and compaction schemes. So comparing these WRF outputs to the STC ModScag and the Spires remotely sensed data, you can see that the blue line here shows that the baseline model has some periods where there's regional over and under estimates, and the map below shows that there's also spatial heterogeneity in the bias signal, whereas with the new snow compaction and snow cover fraction parameterization, there's actually this large systematically negative bias in the ground snow cover fraction, so an underestimate in the snow cover area after implementing our new parameterization. And this is particularly compelling considering that the previous slide did show that even with these snow cover fraction underestimates, there were still those widespread cold biases, which are physically inconsistent. So this is indicating that the cold biases can exist in spite of the snow cover fraction biases, which in this case are underestimates rather than being attributable to snow cover fraction overestimates. And I would like to note that the snow cover fraction underestimates shown here were largely attributable to underestimates in the snow volume in the WRF NOAA-MP simulations. So for example, here's the regional average time series from a representative near normal snow year in 2010, where the solid black line is representing the average of different snow data simulation reference products, SNODAS, UA, and the UCLA products. And then the blue and red lines are showing SWE simulated by the two WRF simulations. So the underestimation in the snow cover fraction is physically consistent with these snow volume underestimates, which is another bias issue that we're now currently investigating. And then we were also looking at the impact of the new snow cover fraction and compaction schemes on the land surface albedo simulated by WRF simulations. So as you can see here, the blue line simulates a higher surface albedo from the baseline relative to the implementation with the new snow cover fraction and snow compaction schemes, which is expected due to the reduction in the snow cover area. But interestingly, there still is this tendency on a regional scale for surface albedo overestimates despite the snow cover fraction underestimates. And this may be indicating that the bias signal in the surface albedo isn't dominated by the biases in the snow cover fraction in the model. So you'll notice that in the shoulder months of the snow season, for example, in October or in June, there are these systematic overestimates in surface albedo indicating potential model uncertainties in the albedo of the vegetation or soil that may also be playing a role in the 2-meter temperature bias, but that's further investigation is needed for looking at the connection there. Finally, we ran a dramaticized simulation to really underpin the point that the snow cover fraction isn't dominating this cold bias issue. We ran this AR new SCF times 0.5 simulation, which essentially is the same as the implementation running with our new snow compaction and snow cover fraction scheme, but at every single time step, we were dividing the snow cover fraction by 2. So we really wanted to impose this really large underestimate in the snow cover fraction in our experiments to see if the cold bias could still persist even with extremely dramatic snow cover fraction underestimates. And as you can see with the dashed red line compared to the black lines, there is this systematic bias successfully imposed. And the bias map shown here shows that there's these very large snow cover fraction biases across nearly the entire Western United States. And that this did then successfully translate to a very large tendency for surface albedo underestimates. But despite these tendencies for very large snow cover fraction and surface albedo underestimates, this cold bias was still persisting, which further was supporting the point that the snow cover fraction wasn't playing a dominant role in this cold bias issue. And in fact, we couldn't even compensate for the cold bias through the snow cover fraction underestimates, although there were some reductions in the cold bias. We're still seeing a cold bias at 64% of the Western US pixels, with particularly high biases in the high elevation regions, indicating that other forms of model development and improvement are needed to resolve the cold bias issue. So in conclusion, the baseline simulations show widespread cold biases in the Western US, which tend to be larger at the high elevation regions. And the new snow cover fraction and compaction parameterizations that reduce the snow cover area can reduce the cold bias, but the cold biases can persist in spite of the snow cover fraction underestimates rather than seeming to be attributable to the snow cover fraction overestimates, which was the previous hypothesis going into the analysis. And further model evaluation and development is needed to resolve the long-standing cold bias issue, for example, addressing biases in background albedo from soil and vegetation, as well as looking at other potential land model parameterizations related to turbulent heat flux, as well as clouds and uncertainties in wind. Thank you. And our publications for snow compaction and the ground snow cover fraction are in James. And if you're interested in the development of those schemes, you can scan the QR codes.
All right, thank you. Are there any questions? All right, anything online? All right, I think we'll move on. Thank you. Okay, so our next speaker is Yuki Kano. We'll be talking about the parameterization of melting snow for bulk cloud microphysics schemes.
Okay. Thank you. I'm Yuki Kanno from Central Research Institute of Electric Power Industry in Japan. I will talk about the parameterization of wet snow. So falling snowflakes start to melt when they are across the melting level, and the melting starts from the outer branches of the snowflakes, and produced water, liquid water, stays in the snowflakes. And this mixture of liquid water and solid snowflake is called wet snow. And as the melting process progresses, it finally become this sphere raindrops. The reason why we care about the wet snow is because it's really easy to stick to the surface of the object. The lower picture shows the wet snow stick to the overhead power lines. And this sometimes results in a collapse of the transmission tower and power outage surrounding area for several days. So the wet snow is a huge threat to infrastructure in extratropical countries. However, recent numerical prediction models do not treat wet snow as a prognostic variable. They only have raindrops and dry snowflake. Okay, so there have been several studies implemented melting snow in the bulk cloud microphysics scheme, and pioneering studies added two prognostic variables. One is the snow liquid mixing ratio, other is the minimum diameter of complete melting. And size distribution is truncated exponential or gamma function larger than this minimum diameter. So we need, in this method, we need to iteratively calculate this minimum diameter at each grid point, which is computationally expensive. However, a recent study solved this problem, Schultz et al. 2019, use prescribed threshold size, so we don't need iterative calculation anymore. And they apply this method to P3 scheme, and they successfully reproduce a different type of solid precipitation. But P3 scheme is quite different from other cloud microphysics scheme, as they only have one free ice categories, and they don't classify the solid hydrometers. So it's not clear the non-iterative melting snow parameterization is applicable to traditional bulk microphysics scheme. Here, traditional means a microphysics scheme that classify solid hydrometer into ice, snow, gravel, or hail. So this study introduced a wet snow formulation to a traditional bulk microphysics scheme, and our parameterization is particularly focused on the representation of wet snow. Okay. So we implement melting snow into the Miliband-Yo scheme in WRF model. It's a double moment microphysics scheme with 7 hydrometers, and we did a 3 modification to the scheme, which I will explain in the following slides. Okay. So first modification is to the introduction of new prognostic variable, which is a snow liquid mixing ratio. And also the definition of snow mixing ratio is changed. Now it contains both the solid part and liquid part. And number concentration is same. And using these two mixing ratios, we can define the snow liquid fraction like this. And this next equation shows the sourcing terms of the snow liquid mixing ratio. It increases due to the melting and also increases due to the collection of clouds by wet snow. And also it decreases by the freezing and evaporation of snow liquid. And this last term shows the conversion of wet snow to the rain category. And next 3 terms is a conversion of wet snow to other solid hydrometer categories. So second modification is a melting formulation. We assume that snowflakes smaller than threshold size are completely melted in one time step, but snowflakes larger than this threshold size are partially melted. The modification in the equation is in the integral interval. So integral from 0 to threshold size, it means the conversion from snow to rain, but integral from threshold size to infinity means the conversion of snow to liquid water. Okay. So next we show it's an assumption of the wet snow parameterization. The important assumption are 2 in the left side. The meltwater distribution, we assume that melt liquid water migrate inner part of the snowflakes, which means that the solid part is exposed to the surrounding air, which allows the wet snow to occur for the deposition and sublimation. This assumption is based on the observed melting behavior of wet snow. The terminal velocity is also based on the observation. We use equation from the Frick et al. 2013, and it's written shown in the right figure. It's a diameter and fall speed relationship. For the liquid fraction smaller than 0.7, the change in the terminal velocity is small, but with higher liquid fraction, the increase in terminal velocity is large. And these two assumptions in the left side is different from the previous study, and our assumption is based on the wet snow. So we check our formulation for the heavy wet snow event in Japan. It occurred on December 23rd, 2022 over East Hokkaido Island, this northern island here. And this event was caused by the northward moving extratropical cyclone, and warm frontal rain band of this cyclone caused wet snow. And due to this heavy wet snow, we had a collapse of transmission tower at northeastern side of this island. And this day was most favorable day of the occurrence of wet snow in Hokkaido since 1976 from my statistical analysis of the station data. Can you proceed the slide? Next slide. Thank you. So we did a downscaling experiment using WRF model. It's a downscaling from ERA5 reanalysis dataset. And we have a one-way nesting, and inner domain has a 1.6 kilometer resolution. And we compared original Miliband-Yau scheme with our modified Miliband-Yau scheme. Next slide, please. So for observation, we compared observation which we obtained in our test power line site. We have a test power line in eastern side of Hokkaido Island here. And here we observe temperature, wind speed, and precipitation. And we also have a two-dimensional distrometer, which observe diameter and fall speed of precipitation particles. And during this event, we also observe the wet snow stick to the overhead power line, like in this picture. You can see here. Yes. Next slide, please. So first, it's an evaluation of the temperature and precipitation, and upper left figure shows the time series of the precipitation. During this event, there are two precipitation events, which is well reproduced in the model, but second event is a bit delayed in our simulation. And for the temperature, temperature was between 0 to 1 degree Celsius, which is favorable for the wet snow occurrence. And in the modified scheme, the temperature is slightly lower than the original scheme, which I will explain later. And right figure shows the vertical profile of temperature, and we also show the temperature at radio on the site. And our simulation will match with the radio zone observation, and the difference between the two Miliband-Yau scheme is small. Next slide, please. So next figure shows the time vertical cross-section of snow liquid fraction. So it means the location of the existence of the wet snow. And we have melting layer here and here at height of 1,000 meters. And below here, below this melting level, we have refreezing layers. And near the surface, we again have melting layers. And wet snow is simulated in the melting layer, and in the refreezing layer, you see a decrease in the snow liquid fraction, which is due to refreezing. And if you focus on the melting layer near the surface, actually the increase in the snow liquid fraction is not just below the 0 degree Celsius line, because not only the temperature, but also humidity also affects the onset of the melting. Next slide, please. So next figure shows the spatial pattern of the accumulated precipitation, and lower figure shows the difference of the rainfall and snowfall. In the new scheme, snowfall is increased and rainfall is decreased, which makes sense because in the original scheme, snowflake is immediately converted to the rain due to the melting, but in the new scheme, the melted snowflake stay as wet snow. Next, please. So next figure shows a comparison with the 2D distorometer. Upper left figure shows the observed diameter and fall velocity relationship, and this is a 2D histogram based on 1.2 million pairs of the diameter and fall velocity of precipitation particles. And you see that vertically elongated distribution, which means the rainfall, and horizontally elongated distribution, which represents snowfall. But its distribution is between this black and orange line. These lines are theoretical line from the Miliband-Yo scheme. So this distribution between these two lines is a mixture, means partially melted solid hydrometers. And of course, original scheme only have a rain and snow, dry snow. It's only on the theoretical line. But in the modified scheme, we have some distribution between these two lines. So we can simulate wet snow, and the distribution is similar to the observation. So a modification will reproduce the observed diameter for velocity relationship. Next, please. So this is a final result. Here, what I show is what happened in this new scheme. So it focuses on the temperature budget. So in the original scheme, we have a cooling of the atmosphere due to the melting of snow. But in the modified scheme, we also have cooling due to the melting in the lower left one, but it's coming from the conversion from snowflake to snow liquid water. And in the modified scheme, we also have heating due to the refreezing of the melted water. And finally, we also have a strong cooling near the surface, which is due to the evaporation of melted water. And this strong cooling near the surface explains why we have why the new scheme has slightly lower surface temperature compared to original scheme. Next, please. And this is a summary. So we introduced a wet snow formulation to Miliband-Yo scheme in the WRF module, and we evaluated new scheme for wet snow event in Japan, and modified scheme will reproduce the observed diameter for velocity relationship. That's all. Thank you for listening.
All right, thank you. Any questions? Okay, so how did you choose that threshold of 125 microns to completely melt snow?
Yeah, it's this value is same as the value of the threshold for the hot conversion from ice to snow, and we also perform a sensitivity experiment, but it doesn't significantly affect like a temperature budget or precipitation pattern.
All right, thank you. Okay, so our final speaker of the session is Juhai Kim, and the talk is positive bias in surface solar irradiance and missing clouds over CONUS in WRF simulation.
Good morning, everyone. My name is Juhae Kim, and I'm from NSF NCAR. Today, I'm going to talk about the positive bias in surface solar irradiance, which is the short wave downward, and missing cloud over the CONUS in WRF simulation, focusing on the CONUS 404 dataset. Surface solar irradiance provides wealth information for understanding the Earth's surface condition, surface energy cycles, and the distribution of cloud and aerosol in the atmosphere. The CONUS 404 dataset generally shows a positive bias in the SSI, associated with the underestimation of the direct effect of clouds on scattering out of solar irradiance. In this study, we use the cloud radiative properties from the National Solar Radiation Database, a satellite-based solar irradiance observation to identify the cloud missings from CONUS 404 and explore their impact on the positive bias of the SSI. This image shows the GOES visible channel, and these are the SSI from the NSRDB and the CONUS 404. You can see the distribution of cloud here. But CONUS 404 misses some cloud. Let me introduce briefly for the CONUS 404 dataset. These are WRF simulations at 4 kilometer horizontal resolution covering the CONUS over the past 40 plus years. This is the high resolution, self-consistent, and long-term continental scale hydroclimate dataset. And the model physics configuration is like this. Thomson and Adams microphysics was used, YSU PBL and the RRTMG radiation, and the NOAA MP render surface models were used. This figure shows the distribution of the 2018 annual SSI and mean SSI, cloud cover, and ECOD from the CONUS 404 and the NSRDB. When you look at the SSI distribution, the CONUS 404 has an overall positive bias compared to the NSRDB, especially over the Mid-Atlantic region and the Montana and Idaho region. For cloud cover, CONUS 404 generally shows the simulate the fewer cloud frequency than NSRDB over most of the CONUS. When you look at the ECOD bias, then it also shows the relatively large values in the Mid-Atlantic, Montana, and Idaho regions, as does the SSI bias. The correlation between the SSI bias and the ECOD bias is 0.9. So we will introduce the methodology of the cloud detection using the surface variable, the SSI and the SSI for a clear sky. We have selected 2 regions with the large SSI bias and 2 regions with small SSI bias. We will focus on understanding how this CONUS 404 SSI bias is related to the optical properties of the cloud in these regions. ISCCP categorized all the clouds into following 9 cloud type based on the cloud optical thickness and the cloud top pressure. NSRDB provides both information, allowing us to analyze the climatological characteristic of the cloud events over CONUS. And Yang et al. 2022 first used the difference between the SSI clear and SSI to determine the presence of the cloud. This was an attempt to use the surface variables to determine the existence of the cloud in the atmosphere, and it was very efficient. ECOD is the variable corresponding to the cloud optical depth. We defined this variable as an logarithm of the ratio of the SSI clear to the SSI, which can be easily calculated. These are a comparison of the monthly cloud cover, ECOD, and precipitation over the 4 region. California and Texas shows small SSI bias. Pacific Northwest and Mid-Atlantic region shows the large SSI bias. Cloud cover in CONUS 404 is underestimated throughout the season in all 4 regions. This underestimation of ECOD is greater in Pacific Northwest and Mid-Atlantic, and it is slightly underestimated in California and Texas Gulf. The variability of CONUS 404 precipitation follows the observation relatively well in those all 4 regions. This suggests that the specific type of clouds that are presenting or missing are different in the region with the small SSI biases and the regions with large SSI bias. Let's look at the cloud frequency which occurred across the CONUS. These 3 are the low altitude cloud, and these are mid altitude cloud. These are high altitude cloud. The first column shows the optically thin cloud. The second column shows the optically medium cloud, and the third shows the optically thick cloud. The most frequent clouds over the CONUS are the cirrostratus and the cirrus, which are optically medium and thin clouds at high altitude. The percentage of optically thick, optically medium, and optically thick clouds are about 23, 43, and 33% respectively. So the most common clouds are the optically medium cloud. CONUS 404 misses 49% of the optically thin cloud, 29% of the optically medium cloud, and 15% of optically thick cloud. Then what is the difference of the cloud frequency in those 4 regions? Looking at the number in the parentheses, this number is calculated by the sum of the older numbers in the blue bar. So higher number indicates the more frequent cloud region in that area. So in these 2 regions, the number is small, which means the clouds themselves are less frequent. And this is very important feature. California has a lot of cirrus, but very few optically medium and optically thick cloud. Texas Gulf has a similar percentage of cloud to the CONUS average, but fewer clouds frequencies themselves. And Pacific Northwest and the Mid-Atlantic area. This area shows high proportion of the optically medium cloud. The amount of cirrostratus is high, as well as the other optically medium cloud. And this is very important. The cloud themselves frequently occurs. These are a very big number compared to the CONUS average. What an actual impact on missing each cloud on the SSI bias? We compared the NSRDB and the CONUS SSIs for each cloud type. So looking at the bias, when optically thin cloud, such as this cloud, are present in NSRDB, the SSI bias is small despite the high missing rate in CONUS 404. And the cirrostratus is an optically medium cloud, accounting for 24% of the total cloud occurrence. The magnitude of the bias due to the absence of this cloud is the largest. And the optically thick cloud have a relatively low missing rate, but missing deep convection cloud introduces a large bias. This is an additional analysis using the ECOD. ECOD can be calculated equally well from the NSRDB and CONUS 404. ECOD reflects the COD as the 91%. COD is complex to calculate, but ECOD is simple to calculate using just two surface variable. This figure is the result of the counting the number of ECOD of each bin from the both dataset. And yeah, it also confirms that the absence of optically thin and optically medium cloud in the CONUS 404. Then can we improve this result by utilizing the shallow cumulus scheme? So we applied this analysis to the other WRF simulation, which employed the shallow cumulus scheme. So in this WRF solar experiment, we used the Grell Fresta cumulus and the MYNN shallow cumulus schemes. And in this experiment, we tested the Deng shallow cumulus scheme. Yeah, the shallow cumulus scheme helps in cloud detection, especially for the optically medium and optically thin cloud. And the combination of GF cumulus, MYNN shallow cumulus, and MYNN PPL schemes shows the best performance in the SSI simulation. Yeah, we have a cloud like a magic. And yeah, so here is the summary. CONUS 404 misses 49% of optically thin cloud, but their impact on the SSI bias is not significant. CONUS 404 misses 29% optically medium cloud, and its impact on the SSI bias is large, resulting in a large SSI bias in this region, where many of these clouds occurs. CONUS 404 does a relatively good job of simulating the optically thick cloud with precipitation. And when we apply a shallow cumulus scheme, it's very effective in detecting the optically thin and optically medium cloud. The ECOD can be easily calculated from the model surface variable, and it has a correlation of 0.91 with the cloud optical depth. So we propose using the ECOD to describe COD in cloud analysis. Thank you.
All right, thank you. Any questions?
Thank you for the interesting presentation. Now, 2018 was one of the worst fire years in the US. That's also when actually this campfire happened in November. So it's like 5-6 months of that year was really affected by smoke in the Western US. How your analysis can take into account the effect of aerosol, smoke aerosol?
Yeah, so we haven't think about the fire for this analysis, but yeah, it would be good to see what is the impact of the aerosol. Yeah, thank you.
Any other questions?
Thanks for the presentation. We've been looking into the lack of clouds in our NOAA models as well, and we have similar issues. What are some of the implications for the users of the CONUS 404 for like hydroclimate? Are there implications of the lack of clouds for analyses that downstream users might want to do?
Yeah, so CONUS 404 data is actually really a valuable data set, but yeah, this is a kind of a one weak point of the CONUS 404 data. And we can do many application using the CONUS 404 data, but for this point, yeah, we have to aware of this, and I'm not sure, yeah, what we can improve the results by doing something. I don't know, but yeah. Anyway, the CONUS 404 data set is very valuable for many other application. Yeah.
All right. Thank you.
Thank you.
I think it's time for some coffee. So thank you, everyone.
And with that, I have nothing else to say, but I'm very pleased to introduce our first speaker, Pablo Lichtig. He will talk a little bit about a new tool for model evaluation today to us. Pablo, it's all yours.
Thanks, Gabby. Can you hear me?
Yes, we can hear you.
Great, thank you. So what I wanted to present today, as Gabby mentioned, is new Python tool called Melodies Monet. It's an open source tool that has been co-developed by NCAR and NOAA. The goal, as it's mentioned here, is to evaluate research, operational, and regulatory models against a variety of observations, including surface, aircraft, and satellite, all within one common framework. So we try to make all of the data that you input look the same so that you can do all of this with a simple YAML file, which is basically like a name list for everybody used to WRF. This is led at NOAA by Rebecca Schwantes and at NCAR by Luisa Emmons. And today, since we're in the WRF MPAS workshop, the examples that I'm going to show are with WRF-Chem, but there is a whole variety of models and observational data sets that are supported. Right now, the MPAS script does not work with this tool, but it's hopefully something that we hope will come as we add support for UX array. It's a tool that you can install very simply using Conda for everybody used to it. And if you decide to move with this, we do still recommend to go with the developed version, which requires a few more steps. But I believe that all of the PDFs will be available in the workshop agenda. So if you want to use it, this should all be something that you can use. As a general idea, the tool works with different dependencies, which are called Monet, which were developed at NOAA, and Monet.io. Monet.io deals with doing all of the reading in. Melodies Monet has the only configuration file that you'll use, and then the pairing and processing are done both within Monet and within Melodies Monet, and then you will output all of the data that you need. As you can see here in the left, I'm showing a YAML file. You can see that it's something fairly simple, that has different blocks just defined by indentation, and a Python script which will always look the exact same pretty much, which are about 8 lines of code, or 9 if you decide to also save per data. And then you can create per data files that you can use for your own plotting routines, or you can create directly plots and statistics out of Melodies Monet. When it comes to the code structure is managed by a driver. The driver has one class that will control all of the code, which is called analysis, and 3 classes that mostly contain data, which are the observation class, the model class, and the paired class. So what you will always do is create just your YAML file and run that very simple script that I described before. And that will read the observations and create the observation class, instantiate with the observation class, read the model and instantiate the model class, then pair the data and create the per data class. If you have already saved per data, you can just read it indirectly, and that saves quite a bit of time. After you have your per data instance, you can save it for later use or to use your own plots. You can plot it directly, or you can calculate different statistics. First, I wanted to show then an example of application with WRF-Chem and now. This example is within the Melodies Monet documentation. That's not the case for the next examples that I will show. And I'm just looking at ozone, and you can see that you can plot time series, spatial overlays, box plots, and bias plots as simple plots. And you also have options for more advanced plots, like Taylor plots, which, if anybody has doubts, can be very useful for comparing multiple models. You can run this with multiple models at the same time. You can create multi-box plots where you have different regions, and then it plots a box plot per region. And you calculate some more advanced evaluation things like critical success indexes, or choose a statistic to define the scorecard and check which model works best for different statistics and for different sites. Right now, if I'm not wrong, these scorecards work mostly with American data, especially with now. Then I wanted to show an example of application with aircraft. This is using data from Asia IQ, which for those who are unfamiliar is, although the campaign is not really running new measurements anymore, but it's still being analyzed and processed, is a measurement campaign and modeling campaign over Asia to try to understand air quality. Right now, we just recently created a specific branch to add code that might be needed for this specific use that will then hopefully make it into the main branch. And this includes a lot of aircraft. So I'm showing some plots from aircraft where you can see a time series including altitude, curtain plots, observational scatters. You can compare observations with models with a scatter plot. You can create vertical profiles. I'm showing here one example where you have shaded areas, but you can also have box plots at each measurement point. And once again, you can create Taylor plots, which, as I mentioned before, can be extremely useful when you have to compare multiple models. It's not the case for this particular plot, but the capability is there. Last but not least, I wanted to show an application example with the geostationary satellite Tempo. For those unfamiliar, that is a new geostationary satellite. It's fairly recent. It started providing data mid-2024, which is pointing at North America, and it provides approximately hourly data for all of North America during daytime. And it already provides some products like NO2, formaldehyde, total ozone, and will provide in the future AOD and probably other species. Creating code for satellites is a lot more complicated than for other data sets, because it requires applying averaging kernels, applying smoothing, and so on. This is usually indicated in the user guide for each satellite product, and it can change not only by instrument, but also by product. So the way that you're meant to do this is not necessarily the same. This means that right now, unifying the way that you can plot is still work in progress. But what I'm going to show is all of the plots that are there for Tempo, and the rest of the satellite products have similar plotting capabilities, but sometimes there are a few things that are still not there that will make it probably fairly soon into the develop branch at least. This includes spatial distributions where you can apply the averaging kernel and see how the model looks once the averaging kernel has been applied, or in the case of Tempo, they're scattering weights and air mass factors, but that's a detail. It's just averaging kernels, if you want to think about it that way. You can have spatial biases, time series with multiple models. So here I'm showing it for WRF and music aversion 0, which was regridded to a long lat grid. The vertical things are still not working with unstructured grids, but they are working with WRF. And diurnal cycles, which is something fairly exciting because it's something that you couldn't do with any other type of satellite. Orbital satellites usually provide one measurement per day. So that's pretty cool. And you can calculate a whole bunch of different statistics. This works for aircraft, for satellite, for surface, And I'm not gonna go into any detail of all of these statistical parameters. Some of them are similar, but not exactly the same. Some of them probably all of you are familiar with, like the standard deviation, mean bias, and normalized mean bias. And this will be outputted as either as a table that is plotted, so as an image, if you want to just look at it, or as a CSV, if you want to later do your own plots or process them in some different way. Having said that, I'm down to questions. Here you have the QR codes for the GitHub page. This is something I forgot to mention. This, as I said, is open source, and we welcome any contributions. It's all managed via GitHub. And then we have the documentation in Read the Docs, which we try to keep pretty up to date. So feel free to check that, or feel free to shoot me an email if you have any doubts on how to use this tool. Thank you very much. Oh, and there is also a tutorial that is already uploaded into ACOM's website. Thank you very much, and I'm done for any questions.
Thanks very much, Pablo. Very nice tool to use. Are there any questions in the room? Or yes, there is one here.
Hi, thank you for your talk. This is a pretty amazing tool. I have a question. When you compare model and satellite, are you able to put them on the same grid, or are they compared on their own grid?
What we do is we grid everything. It depends on the satellite product, but for Tempo in particular, we grid everything to each swath of the satellite. We do all of the processing there. So all of the processing is happening at the time and at the position of the swath. This can be done either conservatively or bilinear. Both methods are supported. And then for plotting, we grid it back into the model space. For other satellites like Tropomi, we grid the satellite to the model space directly. This has been published in a paper by Moon Lee from CIRIS and NOAA. Right now, we're still working on having it be an option for the user, which of the ways you want to do, but we always pair it at one of those spaces. So they are always paired at the same grid. It's just that which grid we choose is still not consistent. It's something we're working on.
Okay, cool. Thank you.
Oh, any other questions in the room, or do we have any questions online? Sounds good. Well, thanks a lot, Pablo. Then let's move on to the next talk. And the next talk is given by Shima Shams, and she is basically also telling us something about satellites.
Hi, everyone. My name is Shima Shams. I'm a project scientist at NSF NCAR. And today I'm going to talk about air quality forecasts in East and South Africa, where we are leveraging chemical data assimilation to improve the results. And I would like to acknowledge all of my collaborators and colleagues in this project. So as an introduction, I just borrowed a table from Institutes of Health Metric, an evaluation which is showing even for the country of Rwanda, which is one of the most developed countries in that continent, still air quality has been the second most important factor of death and disability with the evaluation done in 2019. And these are current condition. It's expected that the African continent will have a rapid population growth over the next century, which comes with dramatic increase in anthropogenic emission on top of the biomass burning activities in dust. So that kind of highlights the importance of having air quality forecast system for the region. So the goal of this project, which was funded by NASA Servier, was to utilize chemical DA for air quality forecasts by better understanding of local stakeholder needs, so we can help and assist to inform public and decision makers. So we started with a stakeholder engagement at the earliest stage of project. We had participants from 5 countries, as mentioned, and different sector from each country participated, mostly at high level staff and scientists of each center. The survey was distributed. And one of the results that I'm sharing here is that 78% of participants mentioned that having air quality forecast is a mandate for them, but they don't have the capacity to do so. So the system that we developed and worked on is a WRF Go-Kart GSI. It's in 15 kilometer. And we're showing some case study for June 2022, where there is a biomass burning activity and a dust event. The goal forecast are 48 hours and is a 3D VAR GSI. Here I have a list of emission inventories that are used. We used CAM's monthly anthropogenic emission, FIN version 2.5 for fire, and you can see the rest of a list of conditions in the boundary condition that were used. So we had a handful of presentation through this meeting on data assimilation. So I hope there is some familiarity with the cost function that needs to be minimized for DA. And there are 2 very interesting and important matrices here, B and R, where B is background error covariance, R is observation error covariance. And these are the matrices that really impact how much observation can allow changes in DA versus how much the model can enforce the results. So for the BA, we use GenBE embedded in WRF. We magnified the emissions by factor of 2. And then how GenBE works is that at the time of Weir's overpass, which is 12 UTC for this case study, it creates pairs between background and perturb, and then it does some statistical calculation to come up with horizontal and vertical length scale. And these are estimated at 1 degree latitude and longitude. And here you're looking at the background covariance error for aerosol species. And the part that I was focusing over the past few months is the observation covariance error. And so we mentioned or not, but we are assimilating Weir's AOD. And for AOD retrieval, surface reflectance, and the source of aerosol species matters a lot. And as expected, there would be subjectivity to the region of interest. And we looked into articles to see if there is any updated estimate of errors of Weir's for Africa, and we couldn't find one. And we realized that it's not been done. So we built on a code from NOAA, so now we have the capability to create these observation covariance errors for us. And so here I'm showing all of the aeronet stations in the continent, which are 29, and we're looking at 21 to 24 because we want to look at the most recent progress of satellite products, and we are looking at both dark target and deep blue products of AOD. And here you can see the different criteria of pairing that we implemented in the code to create these pairs based on the high quality Weir's data and aeronet data. And overall, for each of product, both deep blue and dark target, we have more than 6,000 pairs. And here I'm just showing the angstrom exponent from aeronet data and what is the dominance mode of particles in the region. And as expected, you can see blue stations are encoded the dust belt, so they have more coarse particles, and then we have a couple of mix, and most of our stations are dominated by fine particle, meaning smoke and anthropogenic aerosols. So we actually realized that there is a lot to unfold over there. So we are working and finalizing a paper just on the estimating the Weir's error assessment. But the final results that is needed for the DA is coming up with the observation covariance error, which I'm showing here for both of these products. And that basically is how your bias standard deviation varies with increasing in your AOD from the satellite. And that basically the standard deviation that you see is the equation that will be implemented in DA. Here I'm just quickly showing another part of that paper that we also showcase that there is a seasonality in these errors, which makes sense. As I said, the surface reflectance matters, and by season that changes, and also the source of particle changes through season. So these are all reasons that we see different errors. But going back to the data assimilation impact, I just finished those results, so we don't have the final DA run with those, but we started with a paper in 2016 that they came up with an estimate of global estimate of error, and that estimate is actually higher, is showing a higher error for AOD on a global scale. So ours being a less value for EOD higher than 1 means that we expect that our final DA will have more impact from the AOD fears. But for now, just looking at what this result showed to us, we have the background run here, the DA, and what the difference is. And we are looking at the June 2022, and you can see on top of the map, we see the dust event in South Sudan, and then we also have the biomass burning in Congo. And what DA showed to us is that for the source region of dust, it's decreasing the AOD, but for the transport, it's increasing. And there is a bit more complex story happening around the fire region, but we're not going to dive into it for now until we get the final set of runs as well. A couple of notes on uncertainty estimate and the challenge that we have in the region. One of the key part is that this is a tropical region, so the cloud presence is a very serious challenge for the DA. So here, what's this? Okay. I wanted to use the laser point, but it's not happening. Anyway, so you can see on the red plot that's showing the aggregated number of years over half a degree over June. And what we see is that there were cloud presence or a lack of high level, high accuracy AOD in a lot of region that we are interested in. And that comes from not just the cloud themselves, but also there is still an ongoing challenge in retrieval of AOD and distangling cloud and aerosols when there is a high load of aerosols next to the cloud. So that's one part. And then if you look at the maps that I had before and where we are showing the peak season and the differences, the peak area, there are in the countries, the source region that there is no observation of AirNet or AirNow. So we don't have the observation at the heavy load of aerosols, and consequently, they also don't happen to have the highest impact that that the DA implemented. But at least for 2 regions that we have enough observation showing that both DA and the background is doing a decent job compared to AirNow, compared to AirNet in this example. So in conclusion, we are finalizing this as a Docker package that automatically download VIRs and run the DA. And we had a modest setup so it can be run on a standalone system. So it can be usable for any country that they are interested to have the system running on their own setup of computers, and we are at the final stage of creating a dissemination platform on the chemical DA, emphasizing on the local importance of having estimate of covariance error. We are still finalizing the sensitivity analysis over there and how that impacts the DA, and just overall talking about the importance of DA in improving air quality forecasts, especially for a region that they don't have enough ground-based observation to be incorporated in DA. And challenges, the high cloud coverage in tropical region and the challenge of retrieval at these regions as well, and the still ongoing methodology development and the difficulty of distinguishing heavy aerosol load and limited observation data, surface observation in Africa. And I've been involved in a couple of proposals that we are hoping to get funded, but even for those, the challenges in the social political issues is that still there won't be in the region that the source existed. So that will be an ongoing issue for a while, but I'd be happy to have any question.
Thanks, Shima. Nice work. Are there any questions in the room or online? Chris.
Was interested that the AOD observation error varies with AOD. So is the value, does that depend on the observed value of AOD or the background value or both?
The way that for the DA is important is that what satellite is observing, because you want to know how much your uncertainty would increase when you are getting an increased value of AOD. So these are years, the years AOD versus the biases.
But when you compute the standard deviation of the observation error, it's a function of AOD.
Yes.
That AOD comes from the observation or from the background, or is it some combination of the both?
So the bias is observed like satellite minus AeroNet, and the x-axis was AeroNet, was VIIRS, if that answers your question.
Thanks.
Any more questions in the room? I don't see any question online that refers to the talk here, but maybe I just have one question. So you said you're working on a dissemination website now.
Yes.
Is there also plans to then hand over the system to some of the African partners and have them actually run it forward, or how is that going to work?
Some of the plan changed over the recent policy changes. That what we are doing right now is that the Docker system being in a way that any interest party could just download and not get involved in what needs to be downloaded or not, and then kind of minimizing the work of software engineers and like what is the setup of the package.
That sounds great. Yeah.
Yeah.
Thank you. Thanks a lot, Shima. Let's move on to our next speaker, and we stick around with satellite data, but we move continents over to Asia, and Vorapop is going to tell us about NO2 emission adjustments.
Hello everyone, my name is Vorapop. I'm from CU Boulder. I'm a PhD student, and for today I would like to talk about one of my projects, the NO2 emission adjustment using the GEM satellite data over the Thailand. And in this project, we aim to improve the NO2 simulation over the Thailand area, and we would like to address the problem on lacking the local inventory for the Thailand by using the satellite data for doing a top-down emission adjustment. At first, I would like to introduce the GEM satellite data to everyone. GEMS is the geostationary satellite that's covered in Southeast Asia domain. So it's similar to like Tempo, but moved to the Southeast Asia domain. And because it is a geostationary satellite, so it have more than like one data point per day. And for the GEM case, we kind of have around like 8 to 10 data points per day. And the resolution is 3.5 times 8 kilometers square. Yep, and this is the example of the GEM satellite data. This is the tropospheric NO2 vertical column density in Thailand area on the September 2023. The figure on the right is the GEMS, and the figure on the left is from WRF. You can see that right on the GEMS, we kind of have the peak of the NO2 in both like North and Bangkok, Thailand. But for the WRF, you can you can clearly see that the NO2 in Bangkok is significantly higher than the one in the north. And you can also see that, right, the WRF overestimate the NO2 in Bangkok, but underestimate the NO2 in North Thailand here. And I would like to mention that in September 2023, we have a very small biomass burning in Thailand. So the NO2 here is mainly come from the anthropogenic emission. And for our warp chem setting, we use the diamide kilometer horizontal resolution with the mosaic scheme and the anthropogenic emission that I would like to update it based on the CAMS inventory here. And the method that we use for the top-down emission adjustment, I'm gonna use the simple mass balance. The simple mass balance kind of like assume that the NO2 profile in this grid cell here is mainly come from the source in this grid cell because NO2 is a short lifetime species, right? So we kind of like assume that the transportation from source to surrounding grid cell is very small here. And we use the equation from Martin 2003. The idea on this equation is we just calculate the ratio between GEMS and WRF and apply that ratio to the CAMS emission to get the posterior updates emission. Yep, and this plot shows the diurnal variability of the NOx emission profile from the prior CAMS emission, and the mark here represent the timing that we have GEM satellite data. And because GEM is a satellite data, right? So we can have only the data in the daytime only. And for the Thailand, we have the data from 8 a.m. to the 3 p.m. local time. And for how we update the emission, we kind of like update the emission by fix the diurnal profile from the prior here. So the idea is we calculate the monthly average of the GEMS and WRF and calculate those ratio and then apply that to the prior emission. So this means like the diurnal profile of our posterior and prior emission is going to be the same here. And for this one, we would like to make it very simple first because we're still not sure like how to update the diurnal profile on the timing that we don't have GEMS satellite data like the nighttime here. And let's look at our like preliminary result. This figure shows the percentages change in NOx emission from the prior to the posterior here. The figure on the right is the prior NOx emission, and the one on the left is the percentage change from the prior emission. You can see that right in the North Thailand, we get the increase in NOx emission, but we get decrease in emission in Bangkok here. And then we kind of like compare our like model with the GEMS satellite data. This figure shows the means bias, the panel A from the prior and panel B from the posterior one. You can see that like from the panel A, at first, our WRF kind of like overestimate the NO2 in Bangkok, but underestimate the one in North. However, after the update, we get the significantly reduced of the means bias in Bangkok. In North, we get some improvement, but we get the increase of the means bias in the rural area here. And the correlation coefficient is kind of like improved. The correlation coefficient from the prior is at first it's 0.65, but it gets improved to like 0.82 from the posterior one. And this kind of like obvious, right? Because we use GEM satellite data to update the emission. So the performance when comparing with GEM should improve, right? And the next step, I'm gonna compare it with the data that we haven't seen it before or haven't used it for the simple mass balance. This is the comparison between the WRF and topomy in September 2023. In the topomy, we get some peak in North, but get a higher peak in the Bangkok, Thailand. And if you see on the WRF here, you can see that, right, WRF kind of like overestimate the NO2 everywhere in Thailand comparing to the topomy here. And then when we calculate the means bias between the WRF and topomy, for the prior emission, we get the overestimation of the NO2 everywhere in Thailand, right? But for the posterior one, we get significantly reduction in the means bias in Bangkok area. However, if you look at the one in North Thailand, you can see that like it's clearly increased in the means bias. And this is because if you kind of like remember it correctly, our WRF came kind of like underestimate the NO2 in North comparing to GEMS, but for the topomy, it's kind of like overestimate for the NO2 in the North here. So this means we get the increase for the emission from GEM. So it leads to significantly like increase in the means bias from the topomy here. And for the correlation coefficient, the blue one represent the correlation coefficient from like everywhere in Thailand grid cell. And you can see that, right? The correlation coefficient when we compare it with topomy get decreased. For the prior it's 0.79, but for the posterior it's 0.55 here. And this is mainly due to the increase in like the means bias during like the North Thailand here, because we try to calculate the correlation coefficient in Bangkok area, which is represented in orange here. We get a little bit improvement here. The correlation in Bangkok in the prior is the 0.9 at first, and after the update we get it into like 0.95 here, even though it's a little bit, but yeah, we have some improvement here. Yeah. So in conclusion, right now our simple mass balance provide the improvement of the MO2 in Bangkok, Thailand for both topomy and GEMS, but we still get some challenge in the North Thailand as well. And so our next step, we would like to evaluate our updated result with the surface NO2 observation in Thailand, and we would like to find a good method to update the diurnal variability as well, maybe like not only in the timing that we have GEM satellite data. And for the last one, we would like to apply more like complex mass balance that maybe like account for the error on the emission and also the satellite data as well. And I think that's all for me. I'm happy for the question.
Thank you very much, Warapop. Pretty neat work, and it's great to see GEMS data being used. Are there any questions in the room or online? We do have time for questions.
Thanks for the really nice talk. Just a two quick question. Have you looked at your ozone performance after you update the NO2? And the second one is, correct me if I'm wrong. If I remember correctly, GEMS also have a formaldehyde data set. Do you have plan to adjust the formaldehyde data as well?
Yeah. Thank you for the question. Actually, like I have a look at on the ozone data, yes, and also for the formaldehyde as well. This is maybe like my future step that I'm going to need to take account for this one. Thank you so much.
Thanks. Any other questions in the room, or is there anything online? No? I think everybody's getting a little bit tired. Warapop, I have one question.
Yeah.
Do you have a hypothesis why topomy and GEMS are so different over the northern Thailand region?
Yeah, Gabby. Actually, I just like check on that one, and I found that in North Thailand, the errors for the GEM dataset is significantly high. It's kind of like 2 or 3 times compared to like the one in Bangkok. So I think that might be the case, because when we compare it on the WRF-Chem topomy and WRF-Chem kind of like almost the same, right? But GEMS is different from WRF-Chem and topomy. So I think that might be related to the errors in the GEMS dataset in North Thailand. Yeah.
Interesting. Maybe just one other one. Are there any Pandora instruments in Thailand that you could compare to?
We have the one in the north, but I haven't checked on the data availability yet. Yeah.
But could be an interesting additional data set to compare this to the satellite data.
Yeah, I think that is going to be my next step one. Yeah.
Cool. Thank you very much. We are right on time, thanks to the speakers who actually stick to their allocated time slices. So we are moving continent again. We are moving now to South America, and we are looking at dust emissions. And Nilton Rosario is going to tell us something about that.
Thank you, Gabrielle. Thank you. Good afternoon, good morning. I'm Nilton Evra from São Paulo Federal University. And also I'm working at the Brazil National Institute for Space Research. This is research focused on dust emission from agriculture land in Brazil. And my collaboration is with Saulo Freitas, Dani Long from NCAR, Demerval from São Paulo State University. Okay, just to start, Brazil has experienced large and intense expansion of human land use in last decades. And as a result, we have a large amount of exposure of soils around the country. And this combined with the severe drought that we experience with high recurrence, of course, will produce this new experience, which is a strong event of dust storm. And this has been historically neglected, but that's somehow expected because the major source of aerosol in the region is biomass burn. But with this increasing number of reports of dust, this is a topic that starts to get more attention. And just to show here two events that happened one in 2023 in the Amazon, close to the Manaus city, when during a severe drought, most of this dust was coming from dry up riverbed. And then we had another stream dust event in São Paulo State, in the countryside, in agricultural land. So this is something important. Then we start to think about how can we deal with this process in the context of MONA. MONA is this Brazil initiative to develop a unified Earth system model, and its dynamic core is based on MPAS. Many physics from MPAS also, and some of other physics developed by the community, and two physics that we are working now on in MONA that has importance for this type of process, the dust emission. It's a cold pool dynamic, since basically a common aspect related to these dust events is a convective system around. And we also are implementing and testing this dust emission scheme developed by Leung et al. And this entire effort is to develop MONA aerosol emission module. The dust emission scheme that we are using, which is based on Leung et al. Work, initially based on Koch dust emission equation, which allow emission in region that are without that prescription, the traditional prescription of source function. And it has this advancement implemented by Leung, which is the dependence of the threshold friction velocity with moisture, soil erodibility, also dependence on moisture. And this the friction velocity is scaled down, taking into account the effect of rocks and vegetation. Regarding the cold pool dynamic, Bianca explained about it today already. Just go to mention that one of the impact that we can explore from this parameterization, it's how we can enhance dust emission. So this is this cold pool results expressed in terms of buoyancy excess, and this ring of buoyant excess are associated with the strong cold pool outflows that certainly is going to affect dust emission. And we would like to try to test that in terms of this process. So then we take this case of São Paulo, which is this huge hubbub for our standard that happened in 26 September 2021. And it affected most of the north of São Paulo between 14 and 16 local time. PM10 in some region went up to 200 microgram per meter cubic. So it was indeed a huge event for this region. For MONA was set up with this process, these schemes, MPAS of course dynamic core, NOAA and cloud fraction from this reference, convection updated Freitas, pool dynamic set Freitas et al. We did 3 running one with 10, another 30 kilometer, and one global with 60 kilometer. The idea was to see if we can produce emission using different resolution. But the dust scheme actually was forced offline, so we are using mono metrology to force this dust scheme offline. And then we just to contextualize about the convective system that forced this dust storm in São Paulo. It starts at 13 local time, and then it starts to increase, to intensify, and at the same time move to the north part of São Paulo. And by 15 local time and 16 local time, it was at its maximum of intensity. And then it starts to decrease intensity, but at that time it was affecting this region. So this is the cycle of that convective system that produced that Habub. And just to show you how the surface meteorological evolution occurred in that period, I took these two stations, one in the region that the convective system started to develop, which is this Pradópolis meteorological station. And then this green one, it's a Franca meteorological station. In the middle of them, we had an air quality station. Unfortunately, there wasn't meteorological data for that day. And then here we can see the time that the system start to affect the yellow site here. At 15 o'clock, you can see this huge increase in wind and gust, and large decrease in temperature along precipitation. This air quality station that was a little bit ahead start to register a high amount of PM10 around 70 local time. And if you look to the Franca station, which is the green one, it starts to be affected by the system at 18 in local time, when the gust velocity was extremely high, followed by precipitation. I'm showing you it's a comparison between model and observation. What I did, I took an average of these sites, this region, this meteorological station that was close to the beginning of the system, and compare with the model for the same sites. And the diurnal cycle of temperature here is just for orientation, although there's important aspect difference between model and observation. But what I would like to focus here is this gust velocity that we were able to reproduce only when we consider the cold pool parameterization. And the model was able to get the velocity and also the timing of this cold pool effect. So the 10 kilometer running was the one that get closer in terms of magnitude of this gust velocity. But we can see that 30 kilometer present a lower wind speed, but the three of the simulation were able to reproduce this increase in wind speed at this time when the dust storm was happening. And when we look at the simulation of the dust emission, what we can see here is that even for the 60 kilometer, we are able to reproduce emission in that region. Without the cold pool parameterization, we didn't see any important emission. So what I'm showing you is just the simulation when we take into account the cold pool parameterization. And we can see that even for 60 kilometers, we're able to produce some emission in that region, mainly associated with this maximum of gust velocity. But of course, the structure of that will explain a Habub is not there, but that certainly, considering the resolution, it's something that we would expect. But when we move to the 30 kilometer resolution, we start to see structure that will remember a Habub, but it's a little bit far west compared with the main report was produced. And when we move to the 10 kilometer, we are able to reproduce indeed that structure that would explain the Habub. And it's clearly related to this cold pool parameterization forcing this soil emission. Regarding the extension of the structure, we were able to reproduce a similar extension compared with the observation. So this shows that without this cold pool parameterization, it will be difficult to reproduce this structure. We can see this emission in these three simulations, but of course, with the high resolution, we will get a more realistic structure. So next step in this process is to evaluate atmospheric loading and other aspect of this transport and removal process. This is an aspect that is going to be done soon, since mono aerosol process it's under development, but we are looking forward to see the impact in the atmosphere concentration. Another aspect that we plan to consider, because we did this simulation without further adjustment in terms of agriculture structure of land surface, with just using what is there in terms of NOAA surface information. And then we can see that there is a high dynamic here in terms of land surface characteristics between seasons. So this is something we would like to implement so we can improve the simulation of this emission throughout the year. So that's all. Thank you.
Thanks, Nilton. Quite a strong event. Are there any questions in the room here or online? I think everybody is getting really, really tired. Gretchen.
Yeah, I'm sorry if you discussed this and I missed it. I was wondering if you've looked at how the cold pool in that particular case looks at higher resolution, or is that a plan to look at, without the parameterization?
No, if we look at the high resolution without parameterization, no, we didn't. We didn't look at it at high resolution without parameterization. We just start with that. Actually, this is quite recent, the results that we are getting. So I think it was
very impressive. It was very good. I was just curious. You've looked at when you start to resolve possibly the cold pool, what the differences might be. Yeah, thank you.
Yes, that is something that we can think about. Thank you.
Another question here?
Yes, just have a very quick comment on your future plan about implementing a dynamic crop. So we have a pre-harvest and post-harvest. So we've done some work with NOAA crop model, and then we try to do that also in the crop, but we haven't looked at in the South America, but it would be good to connect in the future.
Okay, thank you. It'd be great, yes.
Okay. Well, then, thank you very much. Let's move on to the next talk. And the next talk will also be given virtual by Min Huang. And we are hearing about WRF and MPAS modeling.
Hi, everyone. Can you hear me okay and see my screen okay?
Yes.
Okay. Thank you for the opportunity to present this work. And I wanted to thank all the people who helped make this work possible. So African dust is actively transported across the Atlantic Ocean to the Americas in summer and fall, which overlaps with the Atlantic hurricane season. And the interactions between this dust-rich air layer and the tropical cyclones can have interested many communities for a long time. Certainly, the aerosol feedback to the storm depends on the distributions and properties of aerosols, which can evolve as they undergo chemical aging processes and deposition during the long-range transport. So we have been using observations, laboratory data, and modeling tools, including WRF, MPAS, and operational products to study compound events, especially those during the past season. We used a lot of observation data, and some of them that will appear in this presentation include Cygnus and the Spire ocean surface winds, which were collected using the quickly advancing GNSSR remote sensing technique, as illustrated here. It basically uses the surface reflected GNSSR signal to infer the Earth's surface conditions. And the Spire data product include the data based on different transmitter constellations, including Galileo, GPS, Beidou, etc. And Cygnus only uses the GPS. While GNSS soil moisture data are also available here, we only use SMAP for its higher accuracy. And we also use MODIS NDVI, GPM precipitation, and aerosol products from different platforms having different overpassing times. In terms of the modeling system, we have the global MPAS system set up, including a dust tracer experiencing atmospheric transport. And we also have a full chemistry regional WRF systems. So for MPAS rounds, we do them both uniform and variable resolution grids with the refined regions for the variable resolution case encompassing both the source and receptor continents and also the Atlantic Ocean. WRF domain also looks similar to those refined region. And for MPAS, we simulate the GNSS ocean surface wind into that system using the JEDI data simulation tool and a hybrid 3D MR approach. For WRF-CAM, the land surface, so NASA's land information system serves as its land component, and it also facilitates offline spin-up that provides high quality land initial conditions for the coupled simulation. Just an overview about the 2024 conditions based on climate indexes such as ONI and AMM. It is suggested that the conditions overall favors the development of tropical cyclones for that season. And indeed, for June, July, August of 2024, there were 5 National Hurricane Center named tropical cyclones, including 3 hurricanes. And we look at satellite data including soil moisture, NDVI, precipitation, ocean surface winds, and aerosol data for that season, and to relate the data to a multi-year seasonal average conditions since 2019. The results are shown in the lower figures. They indicate that in 2024, the Western Africa experienced drier and barrier conditions than normal. Ocean surface winds were overall stronger, and transport of dust was overall more active. And we also see that Eastern Texas experienced relatively wetter and greener conditions. One of the named tropical cyclones in 2024 is called Beryl. It formed near the end of June 2024 and quickly got intensified into Category 5 hurricane before it made its final landfall in Texas around July 8th. And the upper panel animation shows the day-to-day variability of SMAP morning and evening soil moisture together with the Cygnus or Spire ocean surface wind data. And I also have the predicted track of Beryl from NOAA's new hurricane model HAFS. And you can see a pretty good spatial coverage for Cygnus and Spire data, but this and SMAP data and the Spire data look very sparse. We also look at AOD from VIIRS and aerosol absorbing index from GOM2, as well as the aerosol layer height from TROP-OMI not showing figure here. They together indicate that a lot of dust was emitted and exported to higher altitudes above Africa before this slowly descended into Western Atlantic Ocean and the Americas, where Beryl was active. The combined impact of dust and the storm were highly visible. Just start to show the model results. Here you're seeing the free-running modeled wind speed and direction from all of the systems on July 7th at about 6 UTC, shortly before the landfall of Beryl. And I have the surface observations and the surface level drop zone data overlaid on all of the panels. You can see that over the ocean, all of the free-running systems had problem capturing the high wind areas around Burrow impacted regions, but the wind directions were well captured. And over the land, the wind speed were much slower and well captured by all of the systems. But in terms of the wind direction, WRF-Chem slightly outperformed MPAS over Texas regions, and I circulated those areas in orange. We also looked at the water balance elements from a forecast initialized from July 6th around July 7th at 6 UTC for the next 3 days when Burrow caused a significant impact over land. So we can see that all of the systems predicted a higher enhanced precipitation, soil moisture change, and runoff along Burrow's track. While the MPAS predicted hotspots for all of these fields seems to be slightly shifted towards west, diverging from the Texas and Louisiana Boulder regions, and this might have something to do with the less accurate environmental wind direction in MPAS that I discussed in the previous slide. And such uncertainty is also seen in some of the NOAA operational hurricane models. So I wanted to spend a couple of slides showing the impact of ocean surface wind DA on MPAS wind speed. So we see that by assimilating Cygnus ocean wind data, which already have pretty good coverage over those low latitude regions, that caused a notable impact on the wind speed fields, especially over the ocean. While assimilating Spire data had relatively smaller impacts and more confined in a smaller region. And if we assimilate Spire data on top of Cygnus, the added value is very small. We cross-validated the results by comparing the MPAS fields with Institute data, and they suggested that the Cygnus DA more effectively reduced the MPAS observation mismatches than Spire DA. I wanted to note that those observation areas used in the DA for Cygnus and Spire follow different functions of the retrieved wind speed data, as shown in the scatter plot here. And this is based on a NOAA retrieval product, and there are certainly NASA versions and Spire's own retrievals. And if we implement those data, we would get quantitatively different results. We initialized the MPAS forecast since July 7th for the next 3 days using the analysis field and compare that with the baseline NODA forecast I showed earlier. And because the dust tracer is affected by Burrow's track, we can see that it's sensitive to the ocean surface wind DA. And the DA also adjusted atmospheric water vapor transport and impacted precipitation, model forecasted precipitation, runoff, and soil moisture dynamics, and therefore shifted the partitioning of the water balance. And this kind of impact is either desirable or not desirable, dependent on the where we are looking at. I wanted to point out that the dust fields in the MPAS system look similar to the WRF-Chem predicted PM10, but a lot of the dust-related processes are still missing in this MPAS system, according to WRF-Chem. And this includes deposition processes. Here I'm showing that WRF indicates that throughout the lifetime of the Burrow event, we see high elevated dust deposition fluxes not only over and close to the major dust source region of Africa, but also along the track of Burrow. And this enhancement is particularly evident after the landfall. The strong winds carrying a lot of dust and pollution, as well as the enhanced precipitation and soil moisture, play important roles in driving those anomalies. And we also see slight enhancement for the total reactive nitrogen deposition along the Burrow's track. And for the nitrogen deposition fluxes, we also see hotspots over those semi-arid regions in Africa and the US South Central Great Plains. And this is partially due to the strong soil emissions from these regions. Some of the reacted nitrogen containing gases can quickly reacted on the dust surface as they together transported across the ocean under quickly changing environment. We conducted sensitivity analysis to determine the dust impact on weather. The first sensitivity simulations reduced the dust emissions arbitrarily by half, and we got both positive and negative sensitivities in the modeled precipitation, wind speed, and surface temperature as shown here. But interestingly, for this case, under a low dust emission scenario, we would get more precipitation over those populated urban regions in Texas, including Houston and Dallas. And another sensitivity analysis we did is in relevance to the global GVAX soil wet initiative, where we upgraded the default soil texture input with the soil grade product. And this upgrade enhanced the soil moisture in a lot of the wet regions and reduced them in some of the desert regions. And the updated system created soil moisture better correlated with this map data across the domain based on the figure here. The soil moisture sensitivity feedback to the atmosphere through evapotranspiration and the perturbed weather and land surface fields adjusted also some of the emissions and deposition fluxes and therefore impacted chemistry fields, which in turn feedback to the weather. So we see that a lot of the model fields reacted to the soil moisture input upgrade in the system. And finally, I wanted to say that I only have time to cover the case study for Beryl, but we also have completed case studies for other storms for last year, such as Hurricane Debby. We're also monitoring the 2025 events. In the future, it would be interesting to investigate the utility and the quality of commercial data for the regions outside of the Cygnus sampling locations. And it would be very exciting to simulate ocean wind data into more models and include chemistry and chemical data simulation into MPAS. The final note is that land atmospheric interaction plays important roles in regulating storm development and intensification and a lot of chemistry related process. So we need to ensure that the land initial conditions for the coupled simulations are good. And currently for the WRF-Chem, we couple it with NASA Listen, and we hope we'll be able to do similar things for the MPAS in the future. That's all I have, and thank you very much for your attention, and happy to take any questions.
Thank you, Min. That's an amazing amount of work that you have been doing here. Are there any questions in the room or online? Do we have anything online? We have Ravan.
You showed MPAS simulations, but it wasn't clear. Does MPAS include the dust scheme or just the meteorology?
We use the GFS aerosol fields to initialize it, so it only has the atmospheric transport.
But hopefully soon we have at least some version with some chemistry and some aerosols. So, yeah, I have also one quick question, Min. Which chemical scheme did you actually use for your WRF-Chem simulations? You said mosaic aerosols, and which gas phase scheme?
CBMZ.
Okay, so have you also looked much at how the gas phase compounds, if they were impacted and how they changed during the dust event?
Yes, I do, and then I also have been playing with different dust emission schemes, and then yeah. So what I have here doesn't cover like everything I experimented.
Sounds like a very, very comprehensive study you have done. Thank you very much. Any other questions? Else, I think everybody is just hungry and wants to go to lunch. Let's move on to our next talk. And well, I need to call it down. Given by Apijit, and I apologize if I totally mispronounce your name. And we are also looking at dust and the error parameter.
Thank you. You actually spelled my pronounced my name correctly. Hello everyone. I'm Abhijit. I'm a second year PhD student at the Department of Atmospheric Sciences in Texas A&M University, and today I'm going to present my research on evaluating the role of erode parameter in simulating the agricultural dust storm, a case study of Illinois dust storm in 2023. So this dust storm, it occurred on 1st May 2023, which induced zero visibility over the I-55 highway and resulted in a chain crash involving 72 vehicles, ended up killing 7 people and injured 32 people. This is a MODIS RGB composite map showing this magenta plume over the I-55 highway, capturing that storm that time. So what we try to do is we try to simulate the dust storm using WRF CAM. It was a single domain simulation, involved 4-day simulation from April 29th UTC to May 3rd. Our output had a special resolution of 9 kilometers and temporal resolution of 3 hours. And we used NCPFNL from GDAS as the boundary conditions. And I would like to show that in the domain, I have marked a region named detail. So this detail is the region where we only considered the erode parameter to keep the focus of the storm. It involves the I-55, the Springfield, and the accident site. And these are the model physics and dust parameterizations we have used. So for dust module, we have used the emission scheme following Shao et al. 2011. And as you can see in the image, this is the accident location, and the wind basically blowed from the northwest direction, and it has following dry croplands. That's why we have selected this study to study an agricultural dust storm, and to study the erode in an agricultural dust storm as the dust sources. We have considered a tillage-derived erode, and our study is comprised of several case studies where I have basically perturbed different parameters to see the outcomes of those perturbations. The first 4 cases have different combinations of wind perturbations and threshold friction perturbations. And I would like to mention that for case 2 and case 4, the threshold friction velocity is directly scaled down by 50%, as for case 1, we didn't see a significant emission from the dust sources. And here, the erode parameters are manually selected, which means the area I have introduced on the previous slide, over that area, I have manually selected the erode values to the highest, which is 1. But for these 4 cases, the default dust model doesn't account the erode values in the calculation of the dust flux. It just treats the erode parameter as the source function where it is possible for there is possibility of emission. For case 5, I have introduced a tillage-derived erode. At the same time, I have modified the dust flux function, which I'll talk more about in the next slide. So these are the modification I have done in the Shaw model. The first equation is the dust flux equation, which is a size resolved dust flux equation presented in the Shaw et al. 2011 study. And there, the eta free is the amount of the fraction of free dust available for erosion. And in their study, they have only considered a minimally disturbed particle size distribution in calculating the fraction of free dust particle. But I have modified the fraction of free dust particles based on the erode values, as a higher erode means there is high tillage, and high tillage means the topsoil is fully disturbed. So here I have scaled the eta free based on the minimally disturbed size particle size distribution and fully disturbed particle size distribution. And this is basically, I have break down the equation, and you can see the flux is directly dependent on the 1 minus vegetation fraction, which is basically the fraction of erodible land. And as I have defined the erode based on tillage, I have also corrected the vegetation fraction based on the erode value, which is using this equation. This is just a schematic of the modifications I have done. So we have gathered categorized tillage data set for corn and soy crops, and I have filtered out the tillage data set based on the planning dates that lies from 20th April to 3rd May, which is basically I have selected the window based on the actual storm that happened. I have averaged the soy and corn tillage data set and normalized that data set to create a normalized erode parameter. That erode parameter directly modifies the eta free through equation 2b that I have introduced earlier. And it also modifies the vegetation fraction using the equation 5 I have introduced earlier. And the vegetation fraction directly modifies the threshold friction velocity. So these are the corn and soy tillage data, filtered corn and soy tillage data set I have gathered, and from that, by averaging and normalization, I created a erode fraction for only the selected area I have mentioned earlier. So now when we start comparing the dust concentration based on different cases, as you can see, for case 1, which involved the default wind initial wind conditions and a default threshold friction velocity setup, it doesn't produce much emission. So that's why basically I scaled down the threshold friction velocity by 50% for case 2, which shows an increased emission over the simulation. And for case 3, I kept the 50 I kept the default threshold friction velocity, but raised the wind components, initial wind components, by doubling them. And on the right panel, I showed case 2, case 4, and case 5. So case 4 is basically a reduced threshold friction velocity scenario, but increased vegetation fraction. So despite having, for case 2, as we can see, because of the reduced threshold friction velocity, we are getting higher emission, but despite having those emission scenarios, when we increase the vegetation fraction, the emission reduced to a significant level. And for case 5, where we used all the default setups, but tillage-derived erode parameter and a modified dust flux equation, we got similar kind of dust concentration to our case 2. But the fact is, from this average dust concentration time series, it's not we cannot really say that the case 5 is a better simulation. So that's why I want to introduce this figure where the A, B, C are the vegetation fraction scenarios for case 2, case 4, and case 5. As you can see, for case B, we have just used a different vegetation fraction scenario where the vegetation fraction is really high, and which led to almost no emission for case 4. But for case 2, there are so many emitting dust emitting points on figure D, but the case 5 has only a few dust emitting points. That includes a very close the location also is very close to the accident site. This is basically a part of the simulation. It involves the simulation scenario during 1st May, and the left panel is the case 2, the middle panel is case 5, and the last one is basically a binary dust map collected from the MODIS dust dataset. And as you can see, our case 5, which is a tillage-based erode, it matches the location, and to some extent it's a better simulation compared to case 2 in terms of intensity and the location. So now I want to say that when I compared the friction velocities based on different case studies, I found out that the friction velocity only depends on the surface wind velocity. So as you can see, for case 3, the surface wind velocity, we doubled the surface wind velocity, and as a result, only for case 3 there is a deflection in the friction velocity, but for other cases it's more over the same. But the threshold friction velocity, for case 1 and 3, the threshold friction velocity is really high because we didn't perturb the threshold friction velocity. For case 2, where we scale down by 50%, the threshold friction velocity comes down. For case 4, as we increased the vegetation fraction, the threshold friction velocity increased. And for case 5, where we considered a tillage-derived erode parameter and a corrected vegetation fraction based on the erode values, it shows a significant reduction in threshold friction velocity, and thus we had a better simulation for case 5. So the summary of the study, we incorporated a tillage-based erode parameter derived from planting dates and tillage intensity, which significantly improved the dust simulation accuracy in WRF CAM. The case 5, which we used, where we used the this tillage-derived erode approach best matched the observed dust plume on May 1, 2023 in both location and spatial extent. Our results confirmed that the tillage timing and intensity strongly influences the surface erodibility and dust emission potential. And increased vegetation cover effectively suppress the dust emission of even under favorable wind conditions. Thank you.
Thank you very much. Do we have any questions in the room, or is there anything online? So I would have one question. So if I saw that correctly in your time series of dust concentrations, for the cases 1, 2, and 3, you had quite a different temporal evolution, right?
Yes.
And what mostly causes the changes in the temporal resolution? I mean, evolution, sorry. So it seemed like, I think it was case 2 that had more really saw the diurnal variability, and the other ones, it wasn't quite as obvious.
So for case 3, I just increased the initial wind condition, like doubling the default wind conditions. So with an increased wind speed, the friction velocity is really it gets higher. But as I haven't changed the vegetation fraction or threshold friction velocity, the threshold friction velocity is more over the same. That's why the variability is decreased. As you know, the dust flux equation, from the dust flux equation, the variability also depends upon the difference between the friction velocity and the threshold friction velocity. So that's what I would say caused the temporal variability for those cases.
Interesting. And maybe one other quick question. Have you also done, and are there any surface observations of PM in the area that you could compare to?
And so I have done I have compared the model simulated AOD with the AOD from MODIS, but those are not very significant because of the cloud coverage and other things. I mean, we couldn't get a very reliable surface dust concentration observed data sets.
Okay, great. Thank you very much. That brings us to the last talk of this session, and that is given by Minsu Choi, and we are talking about HER-Chem and the radiative forcing of wildfires.
Hello, everyone. My name is Minsu Choi. I'm currently a postdoctoral associate at Series and NOAA GSL Atmospheric Composition Branch. Today, I'm going to talk about my recent work with its preliminary result. As you can see on the title, we did simulating radiative forcing of wildfire smoke using a coupled high-resolution chemistry and meteorology model. HER-Chem. For those of you who are not familiar with the HER-Chem is based on WRF-Chem with the in-house update on the gas and aerosol chemistry with the fixed grid resolution of 3 km, which cover entire CONUS. Thank you. So to begin with, I want to introduce the motivational central scientific question of this research, and also a little bit of background. One of the central scientific question that lead to this research was how well do regional chemical transport model predict the biomass burning influence on climate? And as we all know, aerosols have significant impact on the Earth radiation budget by both direct and indirect effect. It's cooled the surface by reflecting the sunlight. It also warmed the atmosphere by light absorption. And it also leads to cloud brightening and also increase the cloud lifetime. And we all know that wildfire have significant impact on the atmospheric aerosols. And it is no exaggeration to say we are by far living in the era of the wildfire these days. And our community of atmospheric science have delved into study this problem, wildfire impact on air quality and radiative forcing. As you can see on the left bottom panel, remote sensing and satellite remote sensing community has delved into resolve the uncertainties in the emission flux estimation. And also there has been tremendous effort from the measurement community by doing an extensive field campaign like FireXAQ, CalFight, and WeCan. Not only that, our modeling community has delved into look at this problem from different scale, from global to the regional scale model, like a GeoScam and then WolfCam CMAC. While we have dedicated to study this problem, we are still have challenges to accurately predict its impact on air quality and then radiative forcing, not only due to its inherent complexity from the wildfire itself, but also often, for example, global model limited by its coarse resolution. And for example, for the regional model, oftentimes this valuable measurement from the field campaign is very rare. So they often fail to validate their model with this extensive data set from field campaign. So to tackle this problem, we want to answer this sub-science question: how well do NOAA's HRCAM predict the biomass burning influence climate? Next page, please. I think, yep. So I want to begin with the our model introduction on our model configuration. Here in this slide, you can see summary of our model configuration. So first of all, I want to highlight this model cover entire CONUS with the 3 kilometer grid resolution. You can see the grid, number of the grid cells here. We have 1,799 grid cells by 1,059 grid cells. And in this study, we are not using daily fire emission, which apply for the diurnal variation. Inside the model, we use in-house hourly wildfire emission. This hourly wildfire emission has estimated based on the FRP, hourly FRP product from the rave emission. And this FRP has further used in speciated those aerosol and gas phase species using a speciation factor reported in Andrea et al. 2019 ACP. And for the polymerized algorithm, we are using Freitas polymerized algorithm, and it called it in the model every 30 minutes. And we model August 3rd to 17th, which basically cover pretty much a FireXAQ campaign. And we have 3 days of spin-up from July 31 to August 2nd, but those spin-ups are not included in our result. And in the table down below, you can see some important model configuration. We use RTMG for both shortwave and longwave. And for the gas and aerosol phase scheme, we use reduced hydrocarbon mechanism for the gas phase mechanisms. And then we use updated made VBS SOA scheme for the aerosol scheme. And FireXAQ campaign has actually covered a whole bunch of wildfire events in Eastern US and Western US. But in this research, we are mostly focused on William Flats, Castle, and Horsefly Sheridan fire. And in this talk, due to the limited time that I have, I'm only focusing on the William Flats, Castle, and Horsefly fire. And there are also some important updates in our model. Our model includes light-absorbing organic aerosols, which treat as a brown organic aerosols. Based on my understanding, official version of WolfCam treats organic aerosol as a purely light scattering compounds. So we updated this brown organic aerosol to predict more realistic radiative forcing from the wildfire smoke. Not only that, we adopted some update from the recent work from Feng et al. They have resolved spectral shortwave wavelength spins in their WolfCam simulation, and they proved that they have a improved result on the radiative forcing calculation. So we update our shortwave bin from 4 to 14. And we also have minor bug fix, but those are not directly related to the radiative forcing calculation. So I'm not going to cover those minor bug fix in our current version of HRCAM here. So from this slide, I have a comprehensive evaluation of our model. We take 2 different approaches. One is classical approach using surface measurement data set. And also in the later part of the evaluation, we use in situ measurement data set, mostly from DC-8 flight during the FireXAQ campaign. So here, what you can see on the top two panel is selected location for the AQS site and AirNet site, which is located at downwind area of William-Flesch fire. Our model was in general in a reasonable performance in reproducing PM2.5 and AOD level if you compare with the AirNet dataset. However, we are missing some hours by overpredicting PM2.5 in the Spokane location. And for bottom two panels for PM2.5 and AOD, these are located in downwind area of horsefly fire. Conclusions are pretty much similar to the William-Flesch fire performance. Our model was generally produced this variation of PM2.5 and then high peak AOD. And then you can also see summary statistics of hourly PM2.5. And we also did evaluation for daily OC and BC from improved network. We evaluate this all available station in our CONUS domain. You can see number of data set used in the statistic calculations. And our model are in generally speaking in a reasonable range of reproducing PM2.5 and also organic carbon and black carbon. And then the next one, we evaluate our model predicted AOD compared with the VIIRS retrieved AOD. Here you can see daily AOD at the selected time, day passing time, 1 to 2 p.m. local time of VIIRS AOD, and then compare with our modeled AOD. So take home message here, VIIRS AOD have some challenges due to cloud coverage and then thickness of the plume. It has some missing data near the fire core region. Our model in general in the right level of background AOD, but we are missing slightly high AOD near the fire core area. The significant underpredictions are mostly can be found in the August 3rd and August 7th, but except for these days, we are in general in a good place of reproducing AOD. And this is for the Castle Fire. Castle Fires was in northern part of Arizona within the different day. This is from 2019, August 11th to the 14th. We do see more missing data set in the VIIRS AOD here. In general, we are able to reproducing the background AOD, but if you look at the August 13, we are missing those very high AOD near the fire core area. But in general, our model was able to reproduce some high AOD on August 14 and also August 11. And last session for the classical approach, we also evaluate the radiation-related products from our WRF simulation. This is surface downwelling flux predicted from WRF, and then we compare that predicted value with the measurement from SOL-RAD network operated by the GML at NOAA. You can see the selected location, which marked with the green circle on the right panel. And what you can see here, black line represent our model predictions with the diurnal averaged. And then the blue arrow bar is observation from those SOL-RAD network. So our model in general outperform in reproducing this surface downwind flux. But important to note that these locations are mostly outside of the fire plume. So there's no impact on the fire smoke in this measurement location. But by doing this analysis, we ensure that our model's general performance of reproducing radiated products are very well. And from here, I'm going to introduce the extensive evaluation one by one. Instead of exact explicit point-by-point comparison, what we did is we matched the time and location, latitude and longitude with the modeled reset, but we find maximum value and then the top 10% of the predicted species concentration and then the coefficients within that vertical grid cells. So what you see on the gray area, those are the top 10% predicted from the model. And then the orange line represent the 75 percentiles predicted from the model. And then the red dots are measurement from the DC-8 flight from the different instrument. And then I want to highlight this is 1 or 2 second time resolution measurement data sets. So if you look at the black carbon at the very top left panel, we are over-predicting 2 peaks at the first 10 to 20 minutes. But in general, our model outperforming in reproducing black carbon. And if you look at the organic aerosols, we are missing those high AOD measured by AMS, which goes up to 2,000 microgram per cubic meter, but in general, we are captured those variation very well, and then also was able to capture very high OA concentration, which goes up to 1,000 microgram per cubic meter. And on the right panel, you can see carbon monoxide evaluation and then also absorption coefficient evaluations. Our model was in general in a reasonable range of reproducing carbon monoxide and also the absorption coefficients. And if you look at the fractional contribution of organic aerosol, which measured it from the MPAS data sets, these are mostly dominated by the organic aerosols. You can actually see some green and red area, which dominate by the nitrate and sulfate concentration. But if you look at the absolute concentration organic aerosol, PM1 on the right Y2 axis, those concentrations, overall concentrations are very low when the sulfate and nitrate contribute largely on the PM1 concentration. And this is for the different flight transect. This is for the Castle Fire. You can actually see the flight transect on the right bottom video. Conclusions are pretty much similar to the William-Fest fire. We were able to reproduce the black carbon concentration with the site over predictions. OA concentration were in general captured it very well, but we are missing some very high peaks above 300 microgram per cubic meters. CO are in general consistently well reproduced by our model. Absorption coefficients are also well represented by our model. Now you might think your model may be too good. So we actually look at the other transect. So this is a different day of the William-Fest fire, August 7th. We actually, our model actually struggled with the black carbon and organic aerosols. We have some over predictions in the black carbon. And then organic aerosols, we are under predicting organic aerosol a lot. But if you look at the AMS data set, it goes up to 4,000 microgram per cubic meter. We were able to reproduce more than 2,000 microgram per cubic meter, but we were not able to capture this extremely high OA concentration from this wildfire event. And that leads to some underestimation of the absorption coefficient, as you can see. I believe this underestimation most likely due to the brown organic aerosols because we are over predicting black carbon, but we are still under predicting the absorption coefficient. But further analysis needs to be done to justify this assumption is correct. And this is for the other flight transect for the Castle Fire. We're back to Castle Fire here. We are doing okay with the black carbon, but here we do see another problem with the organic aerosol when the concentration goes very high. Now this time goes up to 800 microgram per cubic meter. Our model was not able to capture this concentration for this specific transect. And I believe these are inherent problem of the modeling work. I feel that this is most likely due to several reasons. First, our fire emissions are heavily rely on the hourly FRP product estimated from the satellite remote sensing. And as you can see on the GOES image right here, the fires itself is getting very thick on the selected day that we had a huge underestimation from our model. And also there are some cloud formations. So we believe that there are some underestimation of FRP. So that leads to underestimation of emission flux of those species, which leads to the underestimation of overall organic aerosol concentration. And some of you might want to know, how is your scattering, aerosol scattering in your model? So we compare the single scattering albedo, measured it from DC8, and another measurement framework or added here, which with the red error bar. Those are from the stationary ground network, which operated within the fire safety campaign. If you look at the ground side, we are actually outstanding on reproducing single scattering albedo at that specific location. But if you look at the DCA data set, our model struggled to reproduce this high single scattering albedo most of the time. So I believe our model has some problems with reproducing aerosol scattering, while we are capturing aerosol absorption very well. And one other problem is we have very high resolution, 3 kilometer, which cover entire conus, but our model may not still able to resolve this fine scale real world 500 meter to 1 kilometer resolution fire event. What you can see here in the box plot, this is binded organic aerosol averaged based on delta CO bin, which delta CO represent proxy to the wildfire core region. So here background is mostly background conditions. And then as you go further, it represents more close to the fire core region. So while you can see in the top 10%, our model was the most struggle with the reproducing those extremely high organic aerosol concentration. So by acknowledging these limitations and also some strengths from our model that reproduce really well for the black carbon and organic aerosol absorption coefficient for selected flight transect, I want to summarize the radiative forcing impact from the Wolfcam result. So here you can see is the result from the William Flash fire. We have 6 panels here. Top 2 panel represent the net short wave, long wave, total radiative forcing, and then bottom 4 panel represent only the aerosol radiative forcing from both short wave and long wave. And then the last row represent the short wave direct aerosol radiative forcing. What you can see here, we actually see very strong localized reductions in the solar radiation reaching at the surface, which reaching up to 28 to 32 watt per square. This is 15 days of average. And conversely, aerosol absorption led to atmospheric warming at the top of atmosphere, which goes up to 20 to 24 watt per square. However, by acknowledging our model's uncertainties on reproducing absorption coefficient for some transect and also struggle with reproducing aerosol scattering, I believe this surface cooling effect can be more dramatic. And also this warming effect on the top of atmosphere could be overestimated by our model. And if you look at the small fire, which discussed during this presentation, Castle Fire, the impact are smaller than the William Flash fire. It goes up to 1 to 3 watts per square meter in localized fire region. But as I mentioned, it much weaker than William Flash fire. But especially this Castle Fire has more significant underestimation from our models. So I believe the uncertainty levels is more broader than William Flash fire events. So to summary, our model was in general able to reproduce very high organic aerosol concentration with this high resolution. High resolution. But as you can see, we are indeed outstanding for the selected flight transect, but we also very struggle with the selected flight transect. And what you can see here, as I presented during the slides, most important underestimation was organic aerosols, which was not likely not resolved by the 3-kilometer resolution. And this bias leads to discrepancy in the radiative forcing. Some of the previous work from the various cross-scale modeling work could be more biased, I believe. And current ongoing work are listed here. We are working on the heterogeneous chemistry implementation in this mechanism right now. We observed that significantly high secondary inorganic aerosols, not only the organic aerosols in the William Flash fire events. So we believe that most of this scattering discrepancy is led by missing OA plus missing surface aerosols. And also, as you can see on the Castle Fire, if the fire size is very small, satellite remote sensing has struggled with the FRP estimations. So we need some scale up for the small fire events. So with that, I'd like to stop my presentation and happy to take any question.
Thank you very much. Nice talk. We have time for 1 or 2 questions. Are there any online, or is everybody just smelling the lunch and ready to go and get some food? So yeah, really, really nice work. Is there anything online?
I don't see anything. Oh.
Reminder, if you have any questions afterwards, we have 1 question here. Yes, absolutely.
I just had a question about the organic aerosols that you were talking about. In the plots where you show the breakdown essentially of, I think it was like the 1 minute average plots where you're looking at like the organic aerosol versus other kinds of aerosol. Do you have any way to like further speciate the organic aerosols, like try to figure out what based on what the face you're making, that's no, but I was just wondering if there's a way to sort of further speciate the organic aerosols and maybe get a sense of what specific organic aerosols are missing from the HurChem model.
Oh, you mean from the model?
Yeah.
As we are using VBS scheme, we do have different volatility away from the different volatility beams. But if you're asking me for organic aerosol from the different precursor species, I believe that it's not capable of doing with this current version of model, but that is something that worth trying. But if you are asking for the different volatility beam, we are able to, yes, we can do that. We can speciate that. And based on my understanding, our model reproduce 2 times higher primary organic aerosol compared to the secondary organic aerosols. And we are currently working with the group that measured this AMS, the organic aerosol concentration, to figure out how much of POAs was there and then how much of SOA was there. Yep.
Great, thank you.
Well, thanks. So let's give all our speakers a hand and then off to lunch, and we reconvene at 1 p.m. Thank you.
I guess we'll wait another couple seconds and then get started. Some people are trailing in from lunch.
Okay, perfect. No problem.
Okay, well, it's 1:01 in local time, so why don't we go ahead and get started? So this is the model applications and evaluation session. Got a number of presentations. This one's virtual from Juan Carbone, talking about coastal breezes and thermal comfort during a heat wave event in the Iberian Peninsula. So take it away.
Okay. Hello, everyone. Thank you very much for the opportunity to present my work. My name is Juan Carbone. I am a PhD student in the MedCRIM research group at the Complutense University of Madrid. And I'm currently working at the University of Cádiz. And I'm going to present our recent work, which explore how coastal breezes affect the thermal comfort in the southwestern of Spain. Okay, the aim of this study in Cádiz is to analyze the effect of sea breezes on thermal comfort. Sea breezes are a mesoscale meteorological phenomenon. They are driven by thermal contrast between land and sea, and this temperature difference creates a pressure gradient, which makes the wind blow from the sea. Sea breezes have different impacts. In this study, we focus on their effect regulating the strength temperatures. Okay. The study area is the southwestern Spain, focusing on the Gulf of Cádiz. The southern part of this is dominated by the easterly winds, while the northern part is dominated by the development of breezes. And this blue line is on the map is an imaginary boundary that separates the area with more breezes from the area dominated by the easterly winds. And this boundary changes depending on the event. In this figure, you can see the weather stations used by our research group. The highlighted stations are the ones we use in this study. The red one is the La Jara station, which is the most influenced by the breezes. And the blue one is located on the Puerto Real University campus and is the most influenced by the easterly wind. This is a typical example of the breeze effect at the La Jara station. The black dots in this figure show the wind direction, and the red line represents the temperature. You can see that when the breeze arrives, the temperature drops. On the other hand, if we look at the specific humidity, we can see an increase when the breeze arrives. Temperature, humidity, and wind are important factors for the thermal comfort. And our goal is to understand if the breeze improves this thermal comfort. For this, we use the Universal Thermal Comfort Index, the UTCI, to assess the thermal comfort. This index depends on temperature, humidity, radiation, and wind. And the values of this index have the same units as temperature. Therefore, higher UTCI values means worse thermal comfort. And to obtain the values of this index, we use the WRF model with a comfort parameterization to calculate the UTCI and its subgrade scale variability. To include this subgrid variability in the UTCI calculation, we obtain the following values in each grid cell: 3 values of wind speed, 6 values of mean radiant temperature, 3 values of air temperature, and no variability in absolute humidity is considered, but relative humidity is calculated using the 3 air temperature values. Based on the variation in these meteorological variables, 54 possible combinations are created. We calculate the UTCI value for each combination, and from this result, we estimate the 10th and 90th percentiles of UTCI to represent a cold and a hot area within each grid cell. And this is part of the simulation domain where the weather stations are located. This domain has a resolution of 1 kilometer, and we analyze only 2 days of July 2024. And in the second day, there is a heat wave. In this figure, the solid orange line shows the observed values of temperature, and the dashed line represents the model values. At the rural point and the urban point closest to the station, we can see that the temperature is higher on the heat wave, especially at the urban point, because the effect of urbanization is included in this area. And the temperature shows the breeze effect. It doesn't have the usual bell shape, but it still shows a clear temperature drop when the breeze arrives in the 2 days. At the Puerto Real station, we see a different pattern. On the heat wave event, the temperature has a bell shape, showing no breeze effect. This is because the station in the southern part of the study area, which is most influenced by the easterly wind rather than the sea breezes. As a result, temperature remains higher. We study the thermal comfort at the urban point closest to the station or La Jara station. The orange line shows the 90th percentile of UTCI, and the blue one shows the 10th percentile of the UTCI. The day before the heat wave, the UTCI decreases, and that's when the thermal comfort is meaning better thermal comfort. However, on the heat wave, there is a no decrease, and that's when the thermal comfort is worst. If we look at the figure with the wind direction, we can see that there is a breeze on both days. But on the heat wave, the model shows that the breeze arrived later. This makes that the model estimates worse the thermal comfort than what happened in this station. At the Puerto Real station, thermal comfort also improves on the first day, thanks to the breeze. But on the heat wave, this area has a easterly wind, which makes the thermal comfort worse. At this station, the breeze doesn't arrive, so it doesn't improve the thermal comfort. The main conclusion is that the WRF model is useful tool for studying the thermal comfort, but the model has important limitations. First is the representation of the area that can be further improved. And second, in this event, the model show a delay in sea breeze onset, leading to worse thermal comfort than observed. But sea breezes help improve to thermal comfort, but their effect is limited due to its local nature. Finally, I will show you a part of the future work. Our research group launches radiation campaigns during the breeze events to study the vertical structure. Therefore, the further work will focus on validating this structure in the model using the data from this campaign, and this will help us better understand how debris form and develops. And in these figures, the model shows that the vertical structure of temperature and wind direction is well before and during debris, but it doesn't perform as well for wind speed and specific humidity, which is usually underestimated, especially before the breeze starts. We are also working on predicting these breezes. It's a valuable tool for our campaigns. In these figures, you can see the wind direction and wind speeds. The solid black line shows the observations, and the dashed line shows the model results. We ran 3-day forecast, and we see that in the forecast made 2 days and 1 day before, the model still tends to delay the breeze arrival, just like we saw in the previous results in the other simulations. This is all. Thank you very much for your attention.
Well, we definitely have some time for questions. So any questions for Juan in the audience?
Hi, thank you. I noticed in the vertical profiles you had that sea breeze is the cool air is very shallow in your slides. Do you think that the vertical mesh spacing down below might have an influence in how, like, for example, the timing of the sea breeze and other aspects? Have you looked at that?
It's very important for the thermal comfort when the breeze arrives, and maybe the synoptic conditions is very important. Maybe in other events dominate the synoptic condition, the easterly winds, and the breezes cannot bear the thermal comfort. I don't know, I respond your question or... Thank you.
Any other questions? All right. Thank you very much, Juan.
Thank you.
There was another question, I think, in the back. Sorry about that.
Okay.
Like any explanation for the delay of the onset of the sea breeze? Your hypothesis was the sea breeze.
You move a little closer to the mic.
I wonder if you have any hypothesis why the onset of the sea breeze is delayed.
I don't know. We are working in this. Now I don't have idea what is the problem with the model, but it's normally. I read other publication, and it's normal that in the breeze event the WRF model delay in the onset of the breezes. It's not only for me, more for my simulation. More people. I don't know why. Sorry.
Thank you again, Juan.
We have a Slido question as well that just popped in. They say they're sorry if they missed it, but what was the grid resolution for the WRF model runs?
What? Sorry, I don't hear well.
Someone wanted to know what the grid resolution is of the WRF model runs.
It's 1 kilometer.
Okay, thank you.
Thank you very much.
Thank you.
Sharing the slides. Okay, the next presentation is on flooding in parts of South Africa. Take it away.
Okay, thank you so much. Good day, everyone. And I really want to appreciate this opportunity to present my work. My name is Akintunde Israel Makinde. I am a PhD student at the University of Cape Town, South Africa, under the supervision of Professor Babatunde Abiodun. The title of my presentation is Simulating the Influence of Agola's Current System on Cutoff Flow-Induced Flood in KwaZulu-Natal province of South Africa. To give a little bit of background here, extreme rainfall and flood are a threat to socioeconomic activities worldwide, particularly in the marginalized communities like in the KwaZulu-Natal province of South Africa, where people are both poor and flood exposed. The concern is that the impact of this extreme event may be more in the future as climate change continues to fuel severe events. It is therefore imperative that we improve our understanding of the drivers of extreme events and how accurately they are reproduced by models. See, this will foster improvement in early warning systems and preparedness efforts. In the literature, several studies have identified cutoff flow as a major synoptic driver of extreme rainfall in the region, KwaZulu-Natal region. However, the environment that a cutoff flow tracks into plays a significant role. Local features such as mesoscale convective systems or Agola's current system could influence the intensity of rain produced by cutoff flow. So, for instance, Toiti et al. 2023 demonstrated how mesoscale convective system and low-level jet can enhance rainfall from cutoff flow over the region, KwaZulu-Natal. Similarly, O'Connell et al. 2020 showed that Agola's current system can intensify rain-producing system through latent heat fluxes to enhance convective activities. You see, however, while these studies speculate on the potential influence of Agola's current system on rain-producing systems, there is little or no information on how Agola's current system influences cutoff flow-induced flood in KwaZulu-Natal. Hence, this study aims to investigate the influence of Agola's current system on cutoff flow-induced flood in over KZN. And to accomplish this, we'll employ a top-down approach. That means to say, from atmosphere to hydrology to hydraulic. First, we'll look at the influence of Agola's current on cutoff flow-induced rainfall over KwaZulu-Natal. Then we will assess the impact of Agola's current system on stream flow in the river basin. Lastly, we will examine the flood characteristics under different Agola's current scenario. So in this talk, I will show us results from the first part of our objectives. So far, for the first part, we set up MPAS atmosphere model version 8.2.2 to study the influence of Agola's current system on cutoff flow in this presentation over KZN. Two resolutions were set up. The first is 60 kilometer uniform using mesoscale reference suit, as shown in the table to the left here. The second is 60 to 3 kilometer variable resolution using convective permitting suit. And we configured both resolution with 70 vertical levels up to a model top of 40 kilometer, and we ran 11 member assemble simulations. The model were initialized with ERA5 datasets and first with surface update from ERA5 also at every 6 hours. We evaluate the capability of the model by comparing the assemble mean of the simulated results to ERA5 reanalysis. And then as regards the presentation, we compare that to two satellite presentation products. Okay, here is the result. MPAS provide a realistic simulation of the cutoff flow characteristics, including the evolution of the cutoff flow, the large scale structure of the coal, and it clearly delineates the code core of the event over South Africa in the period from 10th to 13th of April. However, MPAS 60 simulate a southward shift in the track of the cutoff flow, as we can see here, about almost 2 degrees south compared to the reanalysis, and produce a code bias of about 1.5 to 2 degrees at the core of the cutoff flow compared to the reanalysis during the peak intensity, which is on the 11th of April. In addition, the simulated closed low center is slightly bigger in MPAS 60 than in the reanalysis, as seen with this geopotential height contour here. And stretching the resolution to 3 kilometers, that is in MPAS 3, improves the biases in MPAS 60 by simulating a smaller cutoff flow core that is just as deep as the reanalysis. If you look at this place, however, the code biases in the cutoff flow core and the southward bias in the track also deteriorate as we increase the resolution. As you can see, this is the part of MPAS 3 kilometers. See, this suggests that resolution alone does not address the all aspects of the model performance. For the cutoff flow associated rainfall, we compare the 3-hourly accumulated cutoff flow precipitation over the KwaZulu-Natal and the cutoff flow domain with 2 satellite observations and the reanalysis. And here is the result. Here, the light blue shade and the pink shade represent the ensemble spread between the ensemble members. Like I said, 11 ensemble members. The light blue is for MPAS 60, the pink is for MPAS 3. Likewise, the green shade also represent the spread among the 2 observation products that were used in this analysis, which is a Partian and Partian CCS. The black line represent the reanalysis. Okay, over the cutoff flow area, the amount of simulated precipitation in both MPAS 60 and MPAS 3 is quite comparable, as we can see to the observation, especially in the initial part of the time series until the 10th of April. Though beyond the 10th of April, the model tends to underestimate the amount of precipitation. Similarly, over the KwaZulu-Natal, the amount of precipitation associated with the cutoff flow, when compared with the satellite product, began to the model overestimate the amount of precipitation when compared to the satellite product until the 9th of April, where it starts declining and grossly underestimates that. However, increasing the model resolution improves the model performance and simulates precipitation amount that is comparable to the observation, though it simulates the peak precipitation later than the observation, as we can see here. Someone may ask, what about the WRF? Yes, we note the high spike in the WRF over KwaZulu-Natal on the 11th day of April, and to investigate this and the disagreement between the observation and the reanalysis, we plotted the spatial distribution of cutoff flow and the associated 3-hourly precipitation over South Africa on the 11th day, which corresponds to that spike here of April 2022. The first 2 columns represent the precipitation from the 2 satellite precipitation products, which is Partian and Partian CCS, overlaid with a cutoff flow. We overlay with a geopotential height contour from WRF. Generally speaking, we see that MPAS simulates the cutoff flow precipitation and position it on the eastern flank of the cutoff flow as observed and seen in the reanalysis. However, MPAS 60 simulates a precipitation pattern that is confined to the east coast of the subcontinent, whereas WRF put its maximum precipitation on the KwaZulu-Natal. As we can see here, this is that of MPAS 60. And you see, this explains the spike that we see in WRF on the 11th day, because the maximum intensity of precipitation was on the KwaZulu-Natal compared to MPAS that confined its own to the eastern coast of the subcontinent. In addition, the simulated pattern is broad, is wider. Take, for example, this one in MPAS 60 compared to the concentrated rainfall indicated in both the reanalysis and the observation. This could be as a result of the wider cutoff flow center that we noted in the previous result, which might have spread out the region of maximum moisture advection and upward motion, thereby diffusing the rainfall intensity over a larger area and reducing localization of cutoff flow associated precipitation. We investigate this further by plotting the moisture flux, advection, and the convergence. While both MPAS model agrees with the reanalysis that majority of the moisture comes from the Southwest Indian Ocean over the Agulhas Current region, however, MPAS 60 simulates a slightly stronger but not easterly moisture flux north of KwaZulu-Natal, as we can see from there, compared to the nearly easterly flux in the reanalysis. In addition, MPAS 60 grossly underestimated the deep convergence that was seen in the reanalysis. We can see it underestimated that over the KZN and over and beside the KZN, increasing the model resolution that is in the MPAS 3 improves the strength and the direction of the moisture flux as well as the moisture convergence over and near KwaZulu-Natal as seen in both panel I and this one. So we use this bar chart of the 5-day average precipitation over KwaZulu-Natal to summarize the performance of MPAS models in simulating cutoff flow associated rainfall. As we can see, MPAS 60 km exhibit a dry bias of about 30% in the cutoff flow rainfall over KwaZulu-Natal. By contrast, the convection permitting MPAS 3 km narrows this gap by raising the simulated cutoff flow rainfall to about 73% of the observed value. The persistence of a residual dry bias in MPAS 3 highlights that despite explicit resolution of convective dynamics, further refinement of microphysical parameterizations and maybe boundary layer moisture exchange processes may be needed to reconcile the simulated observed precipitation in cutoff flow events. Notwithstanding, the findings indicate that the MPAS 3 reliably reproduce the cost structure and temporal characteristics of cutoff flow precipitation and substantiate the model's ability credibility as a viable tool for subsequent process-oriented investigations. So building on this, we set up some sensitivity experiments to investigate the influence of Agulhas current on cutoff flow induced precipitation. First, we define Agulhas current region, that's ARC, as an area bounded by 0 to 60 degrees east, 5 degrees south to 50 degrees south. Secondly, we calculate zonal average as the average of SST along each latitude within the Agulhas current region. Thirdly, we define an Agulhas current system threshold as the zonal average plus 1 degree centigrade. We are going to use this threshold to identify the degree that must be cooled or that must be warmed. See, following this definition, we set up 3 experiments, namely the control, CTR, which is the control experiment. No modification was performed on the SST. Then the second experiment we named cool ACS, where the SST value within the Agulhas current region that are greater than the threshold was set to the threshold value, thereby cooling it. And the last experiment is warm ACS, where SST values within the Agulhas current region that are greater than the threshold was set to the actual SST value plus 1 degree centigrade. That is to say, we warm it. So this is the result for the sensitivity study in MPAS 3. The result shows that cooling the Agulhas current system generally reduces the intensity of cutoff flow precipitation over the eastern coast of Southern Africa from central Mozambique down to around the southern tip of Eastern Cape province of South Africa. The following rows of analysis shows the mechanism through which this is accomplished. First, cooling the Agulhas current system, led to the reduction in surface latent heat, as we can see here. This means less energy is available to drive evaporation, leading to drier and cooler boundary layer. This in turn lowers the convective available potential energy, which is the measure of energy available for buoyant updrafts. That means the atmosphere is less unstable and the resulting updraft are becoming weaker. In fact, we can see that in the vertical structure, which shows the cooling of the Agulhas current system weakens or suppresses updraft. If we compare it to this place, to this control, it suppresses the updraft and over the coast while enhancing updraft over the ocean, I think along about 35-degree longitude. And this explains the pulse of enhanced precipitation that we see here. Conversely, if when we warm the Agulhas current system, it boosts the near surface moisture and latent heat flux, strengthens the available energy for positive buoyancy and enhance the cutoff flow driven 5-day accumulated precipitation along the eastern coast and particularly it will restore the region of updraft. If you compare to this one here, the cooling it suppresses it, and we have this region of updraft over the ocean, but warming it returns this region of updraft back to about 31 or 32-degree longitude. Similarly, over the KwaZulu-Natal area, the story is also, it's also the same. Cooling the Agulhas current system leads to reduction in the intensity of cutoff flow precipitation, whereas warming the Agulhas current enhances cutoff flow over the region. However, one would have thought that maybe warming the Agulhas current should have at least restored the cutoff flow precipitation to the amount of the of the control system. Well, I think a further analysis may be needed to investigate why warming the Agulhas current could not at least return the cutoff flow precipitation back to 100% of the control simulation. In conclusion, MPAS gives credible simulation of cutoff flow and the associated precipitation over KwaZulu-Natal. It shows that cooling the Agulhas current system releases less surface latent heat into the cutoff flow, thereby releasing the convective available potential energy of the boundary air, making the air less buoyant, and suppresses convective activities along the coast, but enhance them offshore, which and then decrease cutoff flow precipitation over KwaZulu-Natal. And conversely, warming the Agulhas current reverses all these processes and restore and enhance convective activities along the coast, thereby enhancing cutoff flow precipitation. So these preliminary findings provide foundation for investigating the influence of Agulhas current on both the stream flow and the flood characteristics in KwaZulu-Natal. Thank you.
Thank you very much, Akintunde. In the interest of time, questions can be addressed on the Slido app, but we won't have time to take any here. So the next speaker is also virtual. Looks like a follow-up on sensitivity of the cutoff lows to the Agulhas current system, also over parts of South Africa, and this is Chelsea Jensen. So take it away.
Hi, can everyone see my screen? Hear me?
Your volume is a little low.
Can you hear me now?
It's a bit better. How's everybody in the audience?
We'll try to boost it up here, but try to remain close to your computer so that it can pick you up a little better.
So, good morning, good afternoon, everyone. I don't know where you are in the world right now. So I'm from the University of Cape Town, and today I'll be speaking on. It's a little different because I've added a different system as well as the one I've sent in the abstract. So my current title is Simulating the Influence of the Gades and Benguela current systems on current flow and the associated rainfall of the Western Cape, South Africa, using MPAS. And I would first of all just like to thank my co-authors, Babatunde Abiodun, Akintunde Makinde, and Sabina Ababumber. They are all also from UCT and the Nansen Tutu Center. And I would just like to give thanks to these organizations that have allowed me to conduct my research. So cutoff lows are cold core low pressure systems that form in the upper atmosphere, and they're usually associated with extreme weather conditions like strong gusty winds, heavy rainfall, and flooding. So the Western Cape is prone to cutoff low activity, as it releases approximately 10 cutoff lows per year, which contributes to approximately 11% of the annual rainfall. So the motivation behind doing this study is because when cutoff lows pass, they can sometimes cause extreme rainfall and flood events. And our case study is the September 2023 cutoff low event. So just to give you a background on cutoff lows in the Southern Hemisphere, so they are cold core low pressure systems. They usually have a short life cycle. They occur all year round and generally propagate southwards and eastwards. But there are certain mechanisms that influence these characteristics. For instance, a study done by Upper Umar and Abiodun found that not all cutoff flows that pass over the Western Cape bring rainfall. And another study that they did suggests that moisture contributing to these extreme rainfall events over the Western Cape is sourced from the agullets. So that brings me to my aim is to investigate the relative contribution of the agullets current system and to these cutoff low and the associated rainfall of the Western Cape. Okay, so the way we set up the model is that we ran it at 60 and we initialized it with error 5. We used the default scheme in MPAS, the mesoscale reference. So the way we conducted our sensitivity is a bit different to my colleagues. So we also computed the zonal mean. Within this 2 grid boxes, we defined the colors from 0 to 60 and then 10 to 50 degrees. And for the Banguela, we defined it from 10 degrees to about 20 degrees east, 10 degrees west to 20 degrees east, and then from 10 degrees south to about 35 degrees south. So we first calculated the zonal mean of the sea surface temperature for both the Agulhas and the Banguela. But because the Agulhas is a warm ocean current, any value that exceeded the zonal mean by 1 degree was identified and replaced with the zonal mean minus 1 degree. But for the Banguela, we did it a bit differently. We identified values that fall below 1 degree and replaced it with the zonal mean plus 1 degree. So essentially, we reduced the SST over the Agulhas, but we increased the SST over the Banguela. Because the Agulhas is a warm ocean current, so to remove the footprint, we reduced the SST, and similarly with the Banguela. So this is the results from the control simulation. So MPAS is able to capture the track really well. It does deviate slightly southwards when compared to the reanalysis data, but generally it moves from west to east, which is comparable with the literature. So secondly, we wanted to look at the spatial structure of the cut flow, and we can see that MPAS is able to capture the cold core system alongside the low geopotential height minima and the clockwise rotation of the wind vectors. However, there is a slight cold bias in MPAS, but it's very slight. Secondly, we also wanted to look at the cutoff low rainfall. So we plotted the daily rainfall and we compared it with observation and the reanalysis data sets. So we found that MPAS is able to capture the intensity of the precipitation, particularly over the Western Cape. It even performed better than the reanalysis when we correlated it with one another. But then we also looked at the cutoff low precipitation for the Western Cape only, is what you see in the panel. And we also looked at the total precipitation. And once again, we can see that MPAS is able to capture the peak, the temporal peak, and it lies between the 2 observation And for the total precipitation, we can see that MPAS actually performed really well in the sense that it's the closest value to the observed. Okay, then we looked at the contribution of the Agalis and the Benguela current systems. And we can see there's not much difference in the track between the sensitivity experiments and the control simulation. And we can attribute this because what drives the current flow track is the temperature gradient, and we didn't change that gradient. Then we also looked at the influence of the colors on current flow precipitation. So the first panel is the control simulation, and the second row is the difference between the colors and the control, and the third is the Benguela and the control. So what we noticed that there's significant reduction with the Benguela, and there's a slight increase with there's a significant reduction with the Agalis, and there's a slight increase with the Benguela. Then we once again looked at the current flow precipitation of the Western Cape, but just for the sensitivity experiments. And we can see that with the colors, there is a reduction, but with the Benguela, there's no significant change when compared to the control. So to investigate why this was, we looked at the moisture flux. And once again, this is the moisture flux for the control, and then for the colors, so difference between the colors and the control, and difference between the Benguela and control. So there's strong decrease in the magnitude with a reduction of SST for the colors agent, and that is why we are seeing this strong reduction in precipitation. But with the Benguela, although there is a strong increase in the moisture flux, it is not reaching the Western Cape province. So that's why there's not a significant change in precipitation. So just to conclude, MPAS was able to capture the track that deviates slightly southwards. It's able to capture the temporal peak in precipitation and the spatial distribution of rainfall over the Western Cape. And the main message with the sensitivity experiments is that cooling the SST of the current system is strong reduction in moisture, and this suppressed convection, and it was a notable decrease in precipitation. And then with the Benguela, despite warming the SSTs, this led to a slight increase in atmospheric moisture, the modest increase in precipitation of the Western Cape for the same period. And like I said, that moisture doesn't really get to the Western Cape. So these findings basically reinforce the importance that the Agalis is a key moisture source for extreme rainfall events of South Africa. Thank you. Any questions?
We have time for one or two quick questions for Chelsea.
I think it was a similar question for both speakers, just a technical question of how do you generate the ensemble for MPAS?
So what we did to generate the ensemble is that we introduced, we perturbed it at 500 hectopascal because that's where the current flow lies. And we did random perturbations between that, varying them. And that's how we generated our 11-member ensemble.
You missed part of that answer. So at what level, or how did you do what levels did you?
We perturbed
No, we missed part of it. Temperature at some levels?
At 500 hectopascal.
Okay, okay.
maybe have time for one more quick question if there is one. Okay, we'll move on to the next presentation. Thank you, Chelsea. So next we have Ting-Hu Cha from NCAR talking about a comparison of simulated and observed radar data in a tropical maritime convection event.
Hello. So, how do I use it? Can I? So is this a pointer?
Large. Moves the slides forward. This is the pointer, and this one backwards.
Oh, I see. Okay.
Would you like this on, or do you want me to time you from the phone?
Can you put that on?
Sure. Ready?
Okay. Yeah, I'm ready. Okay, thank you everyone for being here today. So my name is Ting Yu and I'm a project scientist at MCube. So before I start, I just want to thank my collaborators on this work, including Rosie, Wenchow, Chris, and Jen DeHart. And I also want to thank the funding source, including the NSF NCAR Advanced Study Program, the 2022 Precip Tahoe T Part 2 field campaign, and the Inform project at NCAR. So let's dive into it. So it's no secret to this community that atmospheric models are increasingly used to study and predict weather phenomenon because we can study like the physical mechanisms or processes behind like the changes in space and time. But evaluating their performance with observations remains particularly challenging. So polarimetric weather radar provides insight into precipitation and cloud processes. It can detect precipitation and detect like the in-cloud information, as well as like the storm movement, and then also rain rate retrieval, etc. So using radar data is very powerful to understand the weather phenomenon. So in our study, we really want to focus on the gap between the atmospheric model and observations. Specifically, does accurate simulated rainfall result from a realistic representation of drop size distribution in weather models? Does it really reflect like the a realistic representation of drop size distribution in weather models when we compare with the radar observations? And furthermore, can we find the best practice to validate atmospheric models using radar observations? So the case that we're interested in is IOP9, which is a low pressure system and moisture surge event on July 29th, 2022. So we conducted the Precip field campaign back in 2022 and during the summertime season. And at this time, there was a monsoonal gyre located to the east of the domain. So you can see the bottom, the bottom panel on the left-hand side. This is the Central Weather Administration Surface Analysis plot at 0Z, July 29, 2022. So you can see a low-pressure system located east of Taiwan. And when this system moves poleward and westward, it brings a very moist air mass over Yonaguni Island and Taiwan. So the Yonaguni Island is the small island very close to Taiwan, as you can see from the bottom right figure showing here. So at this time, we put the CSU CPOL C-band radar at this location to sample the precipitating events. And during this time, when the monsoonal gyre moved over to our interested domain, and there was a prolonged convective linear squall line system persisting for 8 hours and continue propagating to the west. And for this event, it was well sampled by radar, radiosound, and distrometer, and which makes us very interested in this tropical maritime event. So for the model that we have is we use the WRF simulation. So for our WRF simulation, I initialized it by the ERA 5 reanalysis data, and we started the run at 12 UTC, July 28, 2022, and then we started our analysis time at 0 UTC on July 29th. And then for the microphysics scheme that we use is Morrison scheme, but we also tested like Thompson scheme and Peters scheme. And we have like 3 nested domain, including 9 kilometers, 3 kilometers, and 1 kilometers. So on the right-hand side is our domain configuration. But for the remaining talk, I would only use like the 1 kilometer resolution run to show the results. And in addition to our model simulation, we also use the CRSIM, which is the Cloud Resolving Model Radar Simulator. So this is a forward simulator for producing dual polarimetric variables. And it's a single scattering, only consider single scattering, and it uses like T-matrix method and package as lookup table so that it can like check like the dual polar for the dual polarimetric output. And the reason why we wanted to use like CRSIM is because that it allows apples to apples comparison of the observed variables. It can produce the dual polarimetric variables that we are able to see from the radar observations. And furthermore, we also use the AOSPREY. So AOSPREY stands for APAR Observing Simulation, Processing, and Research Environment. So APAR is the Airborne Phase Array Radar, which is one of the big mission within NCAR. And so with this AOSPREY software, so it actually calls like CRSIM module to compute dual polarimetric variable, and it can output data in a standardized radar file format, which is a CF radio file format. And the benefits of using the radar file format is that like it can allow like validation of the retrieval algorithms developed from radar observation, so that we can do more like validation as well as on the like retrieval algorithms. And yes, and then for AOSPREY, it also can create data sets with realistic sampling strategy, and also consider attenuation and radar sensitivity. And yeah, so okay, so let's move on to our CPOL C-band radar observation. So typically when we collected the radar observation during a field, and you would see like on the top panel is like the raw reflectivity when we just collect it directly. So there's no QC, and you can see a lot of noise, and also a lot of like low echo area, which is not the precipitating system that we're interested in. So if we want to conduct any scientific analysis, we really need to apply some quality control procedure. So typically in the field, we perform like 2 steps quality control procedure. The first one is like the level 2 procedure. It can remove the lowest quality signal, and as well as like correct ZDR bias. But if we really want to produce like high research quality radar analysis, then we would recommend to apply a more aggressive quality control algorithm, including removing low quality echo and non-weather echoes. Also doing the attenuation correction for all the variables. And so after applying those, you can see on the bottom panel is the after QC one. You can see there are a lot of like non-weather echoes and low echo area were being removed during this process. So for the level 3 QC procedure, we usually we use the polarimetric variable to threshold and to remove the non-weather echoes. And we also apply the NCAR particle identification, NCAR PID, to identify non-weather echoes, and then further censored those non-weather echoes. So now we have like the radar observations. Then what about the WRF model? Like, so we can directly get the WRF model output. And this is an example of a WRF model output 10 centimeter reflectivity pattern. And do we want to directly compare with the QC data? But for the CSU CPOL radar, it's C-band radar, but not S-band radar. But for the WRF output, it's S-band reflectivity, so it's using different wavelength, and it's not apple-to-apple comparison. And then what about like after resampling by Osprey, it actually takes like the radar sensitivity and the geometry, like the scanning geometry into account. So you can see that now it looks more similar to the actual radar observations. And then if we further apply like the more aggressive quality control algorithm, and it removes the low quality and also sensor non-weather echoes, and you can see that yeah, so some of the low echo area even being removed during this procedure. So in this, for the rest of the results, I would show mainly show the results from these three methods. So before we dive into like the polarimetric variable, we just want to verify if this model simulation also produce like reasonable like rainfall pattern. And so on the left hand side shows the iMerge 6-hour rainfall accumulation. On the right hand side is the WRF 6-hour rainfall accumulation. So you can see that although it's not exactly the same, but it still like generally capture the linear structure produced by this linear score line. And when we further compare like the histogram of like the rain rate, so bottom panel shows the histogram of the rain rate, and black bar represents iMerge, and gray bar represents the WRF rain rate. So you can see that the simulated precipitation intensity is generally consistent with the iMerge data set, but you can also see that for the WRF, the simulated rain rate is overestimated for the low intensity rainfall. But for the WRF rain rate is underestimated when the rainfall event is strong. So there are some discrepancy, but there's also a caveat that the iMerge data oftentimes like overestimated the convective precipitation. So the next question we have is, did the model capture the vertical structure? So here we just want to show an example of a vertical cross-section of convection. So this is from the CSU SIPO radar observation. The left-hand side shows the reflectivity, right-hand side shows the ZDR. And you can see that there's a strong reflectivity tower, like close to like 60 dBz, and then it's associated with like ZDR around like 2 to 3 value in the low levels, suggesting that this rainfall, the very oblate raindrop size and intense precipitation for this event. And then when we look at like the Osprey reflectivity, and this is just an example, so they don't match. They are not like matching exactly the same, but just showing an example for the cross section. And this is the left hand side is the reflectivity, right hand side is the ZDR as well. And you can see that the convection was shallower, but and also wider compared to the real radar observations. But you can still see that the strong reflectivity tower is associated with large ZDR. And now like the ZDR in the low levels is close to 4, and which indicates like very large raindrops. But there's one interesting to see that when it's above the melting level, so the melting level is about like 5 kilometers high for the 0 degree sea altitude. And you can see a lot of like large ZDR and looks like unrealistic signatures above the melting level. So this just doesn't look right to us. And then after we apply like the level 3 like quality control filtering algorithm onto the model data, it actually like removed all the like the unrealistic signatures after applying those. So the next one we wanted to see is the statistical distribution of the reflectivity structure. So we performed the contour frequency by altitude diagram CFAT, and it can show that the statistical structure. And left-hand side shows the CSU SIPO radar observations. Middle plot shows Osprey reflectivity, and the right-hand side shows like the most aggressive applying the most aggressive like quality control algorithm. So and then the blue dashed line represents the 0° C altitude, and the blue solid line represents the temperature profile. So it corresponds to the top axis there. And so when we look at the left one, like the CSUC pole radar observation, it shows that there's an enhanced reflectivity below the 0° C. But for the A Osprey data, it doesn't show that signature at all. And we know that like in CRC, there's no mixed phase information. It doesn't take mixed phase into consideration. And then the next one we saw is that for the higher frequency, there's higher frequency of 30 to 40 dBz below 2 kilometers in the radar in our CPOL radar observations than simulated reflectivity. So you can see like for the majority of the low level reflectivity is more towards like low values compared to our actual observations. But when we apply like the censoring algorithm, like the most aggressive like filtering one, then you can see that lots of low reflectivity data were removed after applying the radar processing algorithm, and it shifts the distribution more to higher value in the low levels. So the next question we have, okay, so now we have a pretty similar structure in the low levels for like the reflectivity. Then what about like the low level drop size distribution? So here, it might be really hard to see. I'm sorry about that. But this is the drop size distribution derived from the WRF model output directly. And the top panel shows the median drop size, and bottom panel shows the generalized intercept parameter. So there are a lot of like small droplets and lots of small droplets. And for the intercept parameter, it is skewed towards to like more than 10. And so then when we compare with the drop size distribution retrieved from the radar forward operator, you can clearly see that it removes a lot of small particles that radar cannot observe. And then when we look at like the censoring, when we look at like the most aggressive censored one, and you can see that this radar quality control algorithm further removes echoes that are not categorized as weather echoes in reality. And so you must be very curious about like, what about like observation? How does it look like? So you can see that this is the red bar represents the CSUC pole observations. And for the filtered one, it resembles the most as the CPOL observations compared to the raw one. And it becomes more like a, the distribution. So let's back to the question that we have in the beginning. Does accurate simulated rainfall result from a realistic representation of drop size distribution in weather models? So in this one experiment and test, and it shows that the simulated low-level drop size distribution closely resembles the DSD retrieved from radar observations. But if we look at the direct WRF output, it actually shows a significantly different distribution. So in our, to summarize, we just really think that there's a best practice needed for the comparison of simulated and observed parameters in order for us to control unobservable and unrealistic characteristics. And I hope that for this experiment that you can can see why we think that the best practice is needed. So thank you so much for your time, and sorry.
Thank you. Very great work. In the interest of time, we won't take any questions here, but you can contact the speaker during the break or on the Slido app. We will go right into the next talk. This will be Kelly Nunez Acasio talking about responsive African easterly waves and other high impact weather events to a warming climate using an MPAS convection permitting approach.
Hi, thank you. Good afternoon, everyone. I would like to start by acknowledging my collaborators, Erin Doherty, Chris Davis at NSF NCAR, and Zachary Moon at Texas A&M. As it pertains to the tropics and how they are modulated by the warming climate, we've learned that warmer ocean waters and moisture and warmer atmosphere will result in more intense hurricanes with greater amounts of rainfall. And this actually has been documented by a plethora of studies. This is just a few examples here, but how a warming climate may be impacting hurricane formation, or what we call the process of tropical cyclogenesis. The tropical cyclone seed has just started to be studied. And particularly in the region of Africa and Atlantic, the majority of those seeds are African easterly waves. And so when we talk about how these waves are going to change with the warming climate, very few studies have started to look into that. And really the focus has been on how these seeds really impact the frequency of tropical cyclones in the Atlantic. And a few of these studies even have gone beyond to say that if we reduce the number of these seeds, it really doesn't impact the tropical cyclone numbers. But the reality is that to this day, we don't really even know how the frequency of tropical cyclones is going to change with the warming climate. Moreover, we don't even know how the frequency of these African easterly waves are gonna change with the warming climate. But it's not only frequency why we study these African easterly waves. The intensity, how the intensity of these waves is going to be modulated with the warming climate is also important to study. Our observations and research of these waves have provided us with different physical mechanisms that scientists have proposed, and including some of my own work, that really all comes to the general same conclusion that a seed that comes off of Africa with, say, more vertically aligned structure, a more convectively in face structure, a seed that is better suited by the time that it crosses the west coast of Africa is more likely to become a tropical depression in the Atlantic waters. And so the intensity of the seed directly relates to the intensity of the tropical cyclone. So it is important to understand how these African easterly waves will be modulated by the warming climate. But in addition to that, regardless of these waves being seeds and becoming hurricanes, they are still high impact weather events. They affect the communities of Africa. They are coupled with convection, and with that convection, there's rainfall. And the majority of these communities are communities that depend on rain-fed crops. And so we need to understand how are they going to be modulated. These waves, some of them, like I said, don't become hurricanes, but they still traverse the Caribbean, some of them even Central America, and they leave behind hazardous conditions, both rainfall and wind. So we really do need to understand how they're going to be modulated. So I hope I've convinced you about why do we care about these easterly waves in a warmer climate. And today what I have for you is some results of a case study that we still have under review in James of how these African easterly waves may potentially be changing in a warmer climate scenario. And we did it with this novel configuration that I developed during my time at NCAR before I actually was here at Texas A&M. And the description of the methodology is in this paper that is already out, where for the first time we use MPAS together with the pseudo global warming method, which essentially it's a method that allow us to give MPAS not only initial conditions but lateral forcing that represents a future warmer climate scenario. In this case, we use the SSP3 7.0. And so what I basically did in this configuration here is that I took the variable mesh of MPAS, specifically the 15 kilometer to 3 kilometer, and as you can see here in the diagram, I cut it so that we can provide these continuous lateral forcing. And so what's important about this is that with the storm resolving resolution, we can get to say that we are doing a sort of storm resolving climate projection that can allow us to now better understand those convective interactions between wave, rain, and convection. And so without going too much into details, we have some control experiments and we have some future climate experiments or PGW experiments. And so the first result that I have for you is here, as you can see, a time series of the position of Helene. Now this Helene is Helene from 2006, not from 2024. And what I'm showing you is the longitude as the wave traversed from Africa into the Atlantic, right? From left to right. And so the orange lines are the experiments of the future climate. The blue ones are the current climate. And then magenta is just ERA 5 for comparison. And what the dots represent is when the wave crossed the west coast of Africa. And what we saw is that, especially with the experiments with longer lead time, the African easterly wave of the future climate experiments was definitely taking longer, or actually moved slower than the current climate wave. We know the implications of that. A tropical system that moves slower is going to have consequences in a specific area in terms of wind and rainfall. We also see that for all three experiments, that future Helene also was more intense both over the continent and over waters. And I'll quickly say that these results that we saw in this paper were also very similar to results that we saw in a previous paper that actually went out last year, 2024, serendipitously the same time that we were experiencing a lull in the 2024 Atlantic hurricane season. And we saw some characteristics over Africa that were the same characteristics that were happening during that time. And in the interest of time, I won't go over that, but we can chat more if you like. So let's go into the results here. What I did here is that we composited the African easterly waves that were active during this short period, those that moved over Africa on the left box plots, and those that were active over water, so Africa on the right and over water on the left. And the orange box plots represent future climate, and the blue box plots represent current climate. And this specific variable is the 950 hectopascal water vapor mixing ratio anomaly. So this quantity in particular tells us something about the dynamic of the convective activity. And what we see here very clearly, that both over water and over Africa, they both have greater 950 hectopascal water vapor content relative to their respective environments in the future warmer climate. And so in that previous paper that goes before this one, we show that the West African monsoon in this future climate scenario becomes more intense, both thermodynamically and dynamically. And through energetics, we show that the jet becomes less energetic, and it seems to be the case that these waves may be, in fact, more moisture laden. and less canonical as we know them today. So now let's look at the rainfall. The rainfall right at the center of these waves. And what we're seeing here is that future African easterly waves over Africa seem to be projecting to be rainier at the center of the trough than the current climate ones. Now we're saying that we're being conservative and not saying it over water. As you can see here, only one of the three experiments showed significance. Now I put the rain rate box plots on the top just so we remembered, but the new quantity on the bottom is 950 hectopascal evaporation vapor pressure deficit. And what we're seeing here is that over the continent, this quantity is significantly higher in the future warmer climate. So this tells us that both water vapor and temperature are relevant and may be playing a role in future African easterly wave convective evolution. Now, based on the results that we saw in the previous slide, you may be asking, well, then in this future increase in precipitation over land, despite of this greater saturation fraction, right? This drier air increase, where is that rain coming from? Well, in a sister paper that is still also under review, we are looking into the convective systems in this future climate. And we're seeing that both CAPE and SYN are increasing in this PGW experiments. And it turns out that the most organized and most intense systems in these future climate experiments are also getting more intense. And these are the types of MCSs that are more likely to be coupled to these African easterly waves, especially those that do become hurricanes. And so with that, this time I don't have a summary slide, but if we have time, I'm happy to take questions. Thank you for your time.
Thank you very much, Kelly. We are a little over time, so I would encourage anyone to put the questions in the Slido app for Kelly.
Thank you.
Thank you very much. Our last speaker is Quentin Lawton from NCAR, talking about investigating the forecast scale of tropical waves in MPAS atmosphere simulations.
Yeah. So I just go forward like this. Awesome.
The middle button is
Okay.
forward and bottom.
Okay. We don't want to be here for 20 minutes more, right? All right. All right. Thank you, everyone. So I know I'm closing out a midday session, so try to keep this entertaining for you. I'm going to talk about investigating the forecast scale of tropical waves in MPAS simulations. First, I want to acknowledge my collaborators on this work, both here at NCAR and at ECMWF. Without them, this would not have been possible. And Kelly really teed us up a bit for waves in the tropics. So why do we care about waves in the tropics? Tropical weather is strongly influenced by these waves. So Kelly just talked a lot about easterly waves, which are these synoptic scale systems that propagate westward and generate rainfall. So this is an image of a satellite image, an African easterly wave. So this is one of the waves that we've been investigating in these simulations, which I'll talk about. We also are curious about another type of wave, which is an equatorial wave called convectively coupled Kelvin waves. So these are a bit larger than easterly waves. They're closer to planetary scale. Their dynamics are coupled with the convection, and they propagate the other direction. They propagate towards the east, and they also can modulate rainfall globally. This is schematic kind of showing the vertical structure. You get rainfall, enhanced rainfall in the center, and then you have this inflow up and out kind of motion. And why these are important is something Kelly actually touched on, which is that they have connections to extreme weather. So for example, last season, we had a lot of flooding rainfall in the Sahel region of Africa related to these African easterly waves. And also these waves can interact with one another. And these interactions have been shown in recent work to influence things like extreme rainfall and tropical cyclones. So this is some floods in Indonesia in 2019 were precipitated by these wave interactions. And this is something that a lot of recent work has focused on, including work of my own and collaborators, in understanding the dynamics of these wave interactions. But kind of zooming out, there's always been a question that has struck me about this is when we study these wave interactions, we have this implicit goal of actually trying to improve medium to a long-range forecasting of extreme weather events. Because if we understand these interactions, then we might be able to predict these events. But this kind of presumes a few things. The first thing it presumes is that we have accurate model predictions of waves like Kelvin waves and easterly waves, and that these wave interactions are actually being captured in these model forecasts. And also that there's a true cause and effect relationship for these interactions to begin with. And unfortunately, there's been some limited work on this, but the work that we have seen has shown that many numerical models struggle to resolve these Kelvin waves, and there's really a lack of research on how they handle wave interactions. And so what we've really been trying to focus on in the last few months is leveraging both objective wave tracking and the MPAS system to understand sources of this Kelvin wave and easterly wave forecast error. And so what I'm going to talk about today are two aspects of this work that's ongoing. The first is applying an object tracking method to quantify these wave forecasts and sources of error numerical models. And then I'll talk specifically about applying this to some of these MPAS simulations to hopefully better understand the relationship between forecast error and these dynamical processes. And so in this particular talk, I'll focus on the Kelvin waves, but I'll briefly mention some of the results at the end for easterly waves and their interactions. So the first thing we need is a baseline. So we first are actually going to be utilizing a suite of operational model forecasts. This is a project that was published a few years ago called Different Models, Same Initial Conditions, DMOSIC. And so this is a suite of operational forecast models that were all initialized using the ECMWF analysis fields. We also supplemented this with hindcasts of the new AIFS AI forecast system for ECMWF and another ICON run. And so we actually have 122 runs from these experiments spanning a year, 2018 to 2019, run every 3 days. And this is a big table with a lot of info, but what I'll point out is that most of these models are around 10 to 15 kilometers in resolution, which is something that we'll come back to later. So we supplemented this, and we've been ongoing supplementing this with a number of MPAS runs. This is because the operational models that we have access to for the DMOSIC runs have limited vertical levels, times, and flexibility. And our goal is to use MPAS simulations to supplement these simulations to explore these wave dynamics and their relationship with errors. So we've so far initialized these runs in a small subset of the DMOSIC period. With the same initial conditions as used in DMOSIC. We're using a coarse mesh, a 30-kilometer mesh for now. And we also use, Tita, Cumulus, Thomson, MYNN, and other default settings. And one thing that pops out, of course, is that we're using 30-kilometer runs and we're comparing to 10-kilometer or so operational models. And does this matter? And so it is possible on its own, this could diminish forecast skill for Kelvin waves. But there have been a lot of studies, and we'll return to this, that have indicated that it's more the parameterization of cumulus itself that's a big factor for Kelvin waves and not necessarily the grid spacing. But again, we'll return to this as I show you some of the results. And so finally, we need a method for actually tracking and identifying these waves. If you're not familiar with Kelvin wave identification, it requires this spatiotemporal filtering, which can be really problematic. It's non-independent in time, and these model runs are very short, and so this can lead to issues. So we try to mitigate these issues by following a procedure that looks like this, where we take our model data and we actually append observation data for 30 days prior and pad it with zeros in either end. And then the actual waves we compare this to, we reference, is actually a data set that's been cut down to the same length as this model data, but replacing the model data with reference data. So the idea here is that we have a more comparable analysis between these reference waves and their models. And we also, and I don't show this here, we validated this with unfiltered data and other metrics, and we are very confident that what we're seeing is a product of the forecast skill for these Kelvin waves. Okay, one more methodology slide. Finally, we have to track these filtered fields. So we use an object tracking method. This is actually a modification of a easterly wave tracker that we developed a few years ago. And so what we do is we can track fields in both I-merge precipitation and NOAA OLR data, and build a reference climatology to reference against our, our model tracks. And so this is an example of what this looks like right here. These are the contours or some of the fields. This is a Hobmauler, so this is longitude. You can see the tracks going down to the right of these Kelvin waves. And I just want to mention that we've applied this in the Easterly Wave Tracker to many data sets, including MPAS. So if this is something you're interested in applying, please reach out to me, or you can also look up some of the documentation for the Easterly Wave. So let's talk a little bit about some of the results we found in our preliminary analysis. So we're limiting our analysis right now to June through October because it overlaps these MPAS runs. What we have is we have on the left, we have something called, okay, that doesn't really work well, success rate. So that's effectively how well the model is at capturing a Kelvin wave at all that exists in real data. So it's a percentage. We have the root mean square error of the strength of the Kelvin wave measured by filtered precipitation. And on the right, we have the track error in longitude for the Kelvin wave tracks over all of these waves and all of these model runs. And a real takeaway here, so this column right here is the MPAS model. And right away, you see the MPAS, at least at 30 kilometers, seems to have reduced forecast skill relative to the MOSIC models, especially in representing the track of these waves. And I don't show it in this presentation, but this is especially evident at earlier time steps, which may indicate this is either an initial spin-up problem with the precipitation, or it has something to do with the growth of these Kelvin waves. And speaking of the growth of the Kelvin waves, we can actually look at how these Kelvin waves are growing in these models. So we're looking at 3 examples from models of the basically the errors and growth rate. We have the IFS model on the left, the AIFS model in the middle, and the MPAS model on the right. On the x-axis, we have the actual growth of the observed Kelvin wave. On the y-axis, we have the modeled growth error. So are we having positive or negative errors? And we see that all these models seem to have trouble simulating these rapid growth changes. So when you have positive growth of the Kelvin wave, they tend to underrepresent the growth. And when you have negative growth, you actually overrepresent it. The reason you might overrepresent weakening is because if your model, underrepresent it, sorry, if your model isn't able to capture the peak intensity of the Kelvin wave, it's also not going to represent the weakening as being as rapid as observed. We also did some additional work that showed a correlation between these Kelvin wave related errors, the strength of the Kelvin wave, and its cloud radiative feedbacks, which is indicating to us that it might be deficiencies in modeling that convective coupling that is the culprit here, which has been shown in some previous work. And I want to go into a little bit more detail about some of these MPAS challenges. We've been playing around with a lot of different simulations, a lot of different runs. And one thing that's kind of stands out is that this is a bit unintuitive or counterintuitive to what we've seen in previous studies of MPAS. There's been some previous work on the MPAS model showing it does pretty well with Kelvin waves. And so it was a bit surprising to us that we saw this real drop-off in skill in these simulations. And so without going into too much detail, we've started to look at additional simulations where we modify the resolution and change cumulus and the microphysics schemes of a few of these cases. And we've basically come around to seeing that it doesn't really seem to fix much of the problems we're seeing. And I'm going to show you an example of why we think this could be a problem, and we're open to suggestions here. But we're looking here at a Hobmauler diagram of Kelvin filtered precipitation, and this is the observations on the left, and this is a number of MPAS simulations we've run at different resolutions, not convective permitting, and also some of these operational models. And, this is something you can do if you just put a box over the bottom half, and you look at the earlier time steps, you see that MPAS really struggles in the first half of these simulations. And we don't see this as much in these other models, at least except for SHIELD, and but the IFS and UK Met seem to do okay. And this could indicate that that initial precipitation spin up of the model could be a problem. And this is something that in the Demosic paper, they actually talk about because we're using the ECMWF initial fields, some of the models had trouble spinning up that precipitation in the first few days. Or it could simply be inherent issues that we already know and may exist with Kelvin waves and modeling them. So I'm going to give you a few preliminary takeaways here. The first is that we can apply this object tracking method to quantify tropical waves in these numerical models, including MPAS. And most of our numerical models underestimate the strength and the growth rate of these Kelvin waves. I don't really touch on this here. It's a whole other talk, but we found that actually the AIFS model has a lot of improvement. I'm sure a lot of people are curious about that, and something I'm happy to talk to you about. We also see that these coarse simulations of MPAS show increased forecast errors for Kelvin waves, but we also looked at easterly waves and their interactions with Kelvin waves, and we found that they also show diminished skill. And so the reason I come back to this when we look at operational models is, like Kelly talked about, like I introduced in my talk, is that these waves and their interactions are important for extreme weather. And so getting this right is really important to forecasting. So in the future, we're going to be supplementing these with additional runs and trying to do things to modify these waves in simulations to assess the impact and forecast, and hopefully explore this problem a bit deeper in MPAS, where we have a lot of data. So that's all I have for you, but happy to take any questions. Thank you.
Thanks, Quentin. We are right at 2:30. I suppose we could take a very quick question before the break, if anybody is interested.
I've seen some work recently, even one was presented at NCAR, where these kinds of waves are very sensitive to the vertical heating profiles, which often come out of the cumulus scheme. And by just a small modification, they're able to modify their waves quite a lot. Is that something you want to look at, is like how these different models do heating profiles?
Yeah, that's a great point. So on that, there was a study that just came out where people looked at Kelvin waves with different cumulus schemes, and they found that exact thing where it was very sensitive. So that is something that we're going to look at in the near future with MPAS, because I believe it's important as well. Yeah.
With that, if anyone has any additional questions for Quentin, Slido app or find him during the break. That concludes this part of the session. See you back here at 3.
It's 3 p.m. and time for the last 5 talks of the meeting. Hopefully everybody is still attentive. I have 5 on the online schedule. Are there only 4? Okay, never mind. Last 4 talks. I have to refresh a web page apparently. Anyway, I'll look again. But our first speaker of the session is Rob Favell, talking about using MPAS to diagnose operational model forecast errors.
Okay, thank you. Can you hear me?
Yes, we can hear you.
All right, thank you. So as you can see, there's going to be a wildfire theme to this talk. So you're looking at Southern California. The shaded areas indicate where fires took place last winter. Certainly you've heard of the Eaton and Palisades fires. They became very infamous, but I'm going to turn your attention to a fire in Ventura County that occurred 2 months prior to that in November of 2024 that reached almost 20,000 acres. So the mountain fire occurred during a historically strong Santa Ana wind event. One of the proxies that is often used for determining the magnitude and timing of a Santa Ana wind event is the pressure difference, sea level pressure difference between 2 ASOS stations, one located in Barstow Daggett, which is northeast of Los Angeles, and Los Angeles International Airport. The time series here is showing sea level pressure difference between these two stations. These stations are about 100 miles apart. And shortly before the fire started, which is the bright red dot there, the pressure difference reached 8.7 millibars, which represents the 99.7th percentile over a nearly 80-year record. So now what I'm showing you is the forecast sea level pressure difference from the GFS run that was started on 0Z the same day, 17 hours prior to the fire. So lower resolution models like the GFS generally do not generate the kind of strong downslope and terrain gap winds that are associated with Santa Ana's, but they can get the more synoptic scale pressure pattern. And so what you're seeing here is a excellent forecast, basically started the day of the fire. So let's go backward in time. So the previous day, the magnitude isn't quite as good, but that's still 7 millibars, which is a very dramatic event. If you go back yet another day, we're starting to see a little bit of phase lag. And in addition to the amplitude error, by 4 days previous, it's not quite as good anymore. And by 5 days out, it looks like the GFS has pretty much lost the plot. So basically, it's not really indicating that there is a very strong event that is looming within a week. So I'm also now going to show you the ensemble members from the GEFs. And so there are 30 of these members. And if your eyesight is very good, you might be able to pick out that there's one lucky member that actually seems to have done a fairly good job at indicating that this event was coming. And I'll come back to that soon. So now I'm going to transition to the European Centers operational model, the IFS. And if I go back and forth between these two slides, you'll see that the IFS actually retains higher value of skill over a longer period of time. But there is a increasing phase lag with time, indicating that the event was starting a little bit too slowly. Now I'm showing you GraphCast, one of the AI models that have been proliferating lately, initialized with IFS. One of the differences between this and IFS that you're seeing here is I only have information from GraphCast or a forecast every 6 hours. That's why the plot looks somewhat chunkier, but actually that's also a very good forecast. On the next slide, I'm going to show you GraphCast initialized with GFS. Now, I want to point out that GraphCast was not trained against GFS. It was trained against the ERA5 and IFS models, but actually this is doing a very good job. And not only is it a good job, it's better than GFS. So if I go back and forth between the two, GraphCast has done a better job of showing you that a potentially strong event was coming, okay? So to conclude this introductory section, I want to show you sea level pressure forecasts that were valid at the time that the fire started. This is around the peak of the event. The colored field, the sea level pressure, the reds are high. And so you could also see the locations of where LAX and Daggett airports are. And so what you're seeing is pretty much the same picture here for the simulation started at 0 UTC on the day of the fire, okay? But if we go ahead about 4 or 5 days earlier, we can see that the skill loss in the GFS, which is the plot on the left, is more severe than it is for GraphCast initialized with GFS on the right. So if I go back and forth, you can see that basically how the forecast evolved over time and the skill was retained better in the GraphCast model. So the experiment motivation and design here is we've seen that at least for this case, the IFS operational model has bested the GFS operational model. This could be due to better model physics. This could be due to better initial conditions. Most likely it's a combination of the two. What I'm going to do is I'm going to use MPAS as an honest broker. I'm going to initialize MPAS with GFS, initialize MPAS with IFS, and try to tease the model physics and initial condition contributions apart. So my MPAS exploratory experiments here are made with version 8.2.2, 30-kilometer uniform global mesh because it runs fast. starting about 5 days prior to the fire on November 2nd of last year, using the mesoscale reference and initialized with GFS and IFS. A serious advantage of MPAS for this particular experiment is there are no lateral boundary conditions to complicate this experiment. Okay, so let's look at some 500 millibar map comparisons. I'm going to compare it to ERA5 reanalysis. We're starting on November 2nd, as I said, about 5 days prior to the peak of the event and the fire. So at the upper left there, you're seeing the 500 millibar map from ERA5. I am going to consider this as truth. You can see a ridge over the west coast of the US and a trough located to the east. The white dots here are reminding you where LAX and Daggett are. So now I'm going to show you the difference between ERA5 and GFS. So it's GFS minus ERA5. The blues here are indicating that the GFS has lower geopotential height than the ERA5 reanalysis that I'm taking as truth. So this means the ridge magnitude was too weak, or the eastern progression was too slow, and actually it's a combination of the two of those. Now at the bottom left, or bottom right, I'm going to show you MPAS initialized with GFS minus the ERA5, and we can see, at least for the window that I'm showing you, that actually this is a very close comparison. So MPAS is proving to be an honest broker, at least as far as the GFS is concerned. So now I'm going to replace the figures on the right with the IFS. And so that's IFS minus ERA5 at the upper right, and MPAS initialized with IFS minus ERA5 at the lower right. We can see, first of all, that IFS is better compared to ERA5. That's maybe a little bit problematic. I'm taking ERA5 to be truth, but of course, ERA5 is based on the IFS. But in any event, there's less difference between IFS and ERA5. And if anything, MPAS initialized with IFS may look a little bit better than IFS does itself. So if I go back and forth between the two, you can see that there's a better forecast here relative to ERA5. So now at the lower left, I'm adding the forecast from GraphCast initialized with IFS, and I see from the 3 images here compared to ERA5 that they look fairly similar. And I'm going to go on the next slide. I'm going to show you the GFS situation. So you saw the pictures on the right column before, and we can see that GraphCast initialized with GFS also looks similar to what GFS has performed itself. Okay, so far it seems like initial condition differences are of primary importance, but I want to remind you that there was one lucky member of the GEFS, and of course it had to turn out to be ensemble member number 13. And so GEFS ensemble number 13 minus ERA5 looks a lot more like ERA5 than the GFS deterministic run did, but MPAS initialized with this ensemble member doesn't really look all that much better than GFS itself. So I'm going to emphasize that on this slide. So again, this is the forecast of sea level pressure difference. So what we can see here is GFS is not warning us of a particularly imminent situation, and neither is MPAS, but the GEFS ensemble member 13 is doing a better job, but MPAS initialized with that ensemble member isn't. So JEP's ensemble members are initialized with perturbed initial conditions, but also stochastically perturbed physics. So the summary this far is a lot of this is initial conditions, but some of it is likely model physics. So also both IFS and particularly GFS seem to propagate planetary waves too slowly. So my example experiment with MPAS is I'm going to play around with gravity wave drag. Okay, gravity wave drag has 2 components, an orographic wave drag component and a low-level blocking component. So here are my gravity wave drag experiments. I'm starting with the IFS because I want to start with better initial conditions. So you've seen this plot before. At the upper left, IFS minus ERA5. At the lower left, or the lower right, sorry, I keep on saying left, the control MPAS simulation. If I turn off the gravity wave drag, this is what we get in the lower right. That does not look like a improvement. But if I take the low-level blocking component and I reduce it, and I'm actually reducing it a lot by 75%, this looks like a somewhat better forecast. Or if I reduce the orographic drag component instead, it actually looks fairly similar. So the preliminary analysis here, and I want to emphasize that it is preliminary, reduced gravity wave drag results in a slight improvement to the forecast. The sum of the gravity wave drag components is more important than the source. The result is possibly resolution dependent, so we need to do this on a higher resolution net mesh. And other model physics are likely as or more important. We've tested those too, but I knew I would only have time for one. So to summarize here, MPAS is serving as an honest broker, and the experiment suggests that IFS better initial condition is a large factor in its higher skill relative to GFS in the mountain fire case. That forecast errors relative to ERA5 and AI models suggest that model physics deficiencies exist in the NWP models, and that's what I hope to use MPAS is to help identify what physics those are and where they emerge, and that would provide clues for suggesting improvements to the physics. Limitations here, the MPAS simulation initialized with IFS may need better tuning to match the IFS performance, and the experiment resolution is low relative to the source models. The ultimate goals here, as I said, is to use MPAS to identify model physics in need of improvements. And also what I'm trying to do with this work is leverage AI models to improve the NWP models so that they can outcompete AI. So maybe that's a little bit of wishful thinking here, but that's what I have. Thanks for listening.
Thanks, Rob. Are there any questions in the room or online? No? Okay. So for the sake of time, we're going to move on to our next speaker, Mei Wang, who will be talking about the impact of upstream resolution on the medium range forecast errors over the CONUS.
Thanks, Melissa. Hi, everyone. My name is Mei Wang. I'm in NSF NCAR. I'm CUBE. So today I'll be talking about some experiments that we've been doing and looking at the impact of upstream resolution, specifically the horizontal mesh spacing, increasing the resolution on the medium range forecast over the CONUS. So I actually spoke about some of these simulations last year, where we focused on the period of May 2019, where there was a series of multi-day tornado outbreak events that happened in the latter half of that month between the 17th and the 29th. And specifically, several studies kind of looked into this period, especially Gensini et al. 2019, that basically identified increased unpredictability due to sources of predictability in these tornado outbreak events that they can trace back to the occurrences of the Madden-Julian oscillation weeks in advance, providing that tornado outbreak potential forecast. So other studies have also looked at long 30-year database of tornado outbreak events and identified dominant weather regime patterns that are very conducive to these high-impact tornado outbreak events. And for example, Miller et al. Here basically highlighted the weather regime pattern that happened during this dominated in this May 2019 period, where we have this upper level trough to the west of the US and then thermal ridge to the right, really supporting that stream of moist surface airflow from the Gulf. So while these tropical convection associated with the MJO can induce Rossby wave perturbations along the North Pacific, traversing along the North Pacific, can provide increase in the predictability of these tornado outbreak events, these Rossby wave perturbation that traverses across the Pacific can also be more prone to forecast error amplification. So this study doesn't look at how well we can predict MJO with MPAS. That's definitely a very challenging problem, but we asked a simpler question of how well does MPAS represent just the large scale pattern in 7-day forecasts ahead of this tornado outbreak event. So we're limiting to looking at 7-day forecasts instead of weeks, and also the large scale pattern because these supposedly have higher predictability. And also what types of forecast errors impact a 7-day forecast over CONUS. So to do this, we ran 2 sets of variable resolution MPAS simulations using, 2 sets of variable resolution meshes with down to convection permitting resolution. The first set is the global 15 to 3 kilometer variable resolution mesh, where we have that 3 kilometer mesh spacing over the CONUS region, and then gradually increasing to 15 kilometers globally elsewhere. And the other set is what we call the HR belt, where we have the global 15 to 3.75 kilometer mid-latitude belt mesh. So we have the refined mesh spacing is over the mid-latitude belt between 30 degrees and 60 degrees north, and then gradually increasing to 15 kilometers everywhere else. So comparing these 2 meshes, certainly there's some discrepancy, and we chose this mesh because it's available, and it's basically captures that higher resolution upstream of the CONUS region to see if, to basically answer some of our questions, especially in terms of the types of forecast errors in upstream regions. So the forecast experiments that we ran, we did the HR CONUS simulations for the whole month-long period, May 2019. We ran 10-member 7-day forecast initialized daily at 0 UTC using GEF's initial perturbations. And then we also ran the HR belt simulations, but over a shorter period initialized daily between 10th and 23rd of May 2019, 5-member ensemble because it's a little bit more expensive, and then 7-day forecast, again, initialized with the same initial conditions. And also we selected these days 10 initialization dates because then it would then give us the day 1 to day 7 forecast over that multi-day tornado outbreak events between the 17th and the 29th. And for physics, we used the convection permitting physics suite. This is run using an older version of MPAS, version 7.3, but we did include some of the important hotfixes from version 8. And instead of the Grell-Freitas cumulus scheme, we used the scale-aware Nutica scheme. So here are some results from the HR CONUS simulations. This is looking at 200 hectopascal geopotential height RMSE, domain forecast errors, domain average over roughly the CONUS region. The y-axis is showing forecast lead time from hour 0 to 168, so that's day 7. And the x-axis shows the initialization time. So each vertical column in this plot here basically is one forecast integration. And so we have the whole period, the forecast errors looking at the whole May 2019 period. The diagonal lines in the dash line there basically highlights constant valid time. So you can see that the errors are actually more diagonally oriented, parallel to these diagonal dash lines, which kind of indicates that these are more flow-dependent errors and actually appears in multiple different initializations. If we look over at Western Pacific and Eastern Pacific, again, we see similar characteristics where we see these diagonally oriented forecast errors, again, highlighting how these are flow-dependent errors associated with the events and the flow that's happening at that particular time. And if we look at the times of forecasts in the day 5 to 7 range over the CONUS, where we see an increase in the height errors there, and tracking them upstream over those several forecasts, you can kind of see that, well, maybe there's some hint of some error propagation that's happening starting from the Pacific and then moving into the CONUS region. And so this was kind of what motivated us to run these higher upstream resolution experiments. This is just another error metric for looking at the large-scale forecast errors in our HR CONUS simulations using wave amplitude errors. And essentially on the left side here, we've got day 1, 2, 3 averaged over all 0 UTC forecasts over that month-long period. And then the right, I have day 4, 5, 6, 7. You can see in day 1, a lot of those errors pop up early over East Asia and over Central and Eastern US. And these areas are associated with active convection during this period, and so they're likely related to the representation there. By day 3, we start to see these errors propagating downstream across the Pacific and the Atlantic, and through day 4 to 7, we can really see these forecast errors continue to amplify with forecast lead time. So again, you can see a lot of those errors appearing upstream of CONUS, between 30 degrees and 60 degrees north along the storm track regions. So again, our question is, if we increase the mesh spacing, decrease the mesh spacing, increase the resolution in that region, how does that impact the 7-day forecast over the CONUS region? Still looking at XR CONUS simulations, but this is another way to average over all the forecasts, again, looking at large scale errors, but looking at the whole mid-latitude belt between 30 and 70 degrees north in the left figure here. So I chopped up each of the, chopped them up into longitudinal bins of 45 degrees, 8 sectors. And so the Sector 6 essentially corresponds to the CONUS region, and then 4 and 5 is Western and Eastern Pacific. And then I plotted the domain average forecast errors on the right here. The top plot is RMSE, and the bottom plot is bias. Y-axis is forecast lead time, and then X-axis is basically the sector. So it's kind of like a Hofmahler, basically a Hofmahler diagram, but coarser in the coarse resolution. So you can see a lot of the errors are growing. Well, the errors are growing fastest in the Western Pacific region. You can see the tighter gradient in the top plot here, showing how a lot of those errors do amplify much quicker than other regions, but it also appears to maybe propagate a little into the Eastern Pacific. You can also see that the bias over the CONUS region is smaller, potentially related to the higher resolution in that region. So how does the XR belt simulations affect these errors? So now I'm comparing the errors over just a 2-week period where they overlap. And these are the results. So XR belt seems to reduce some of the height errors, and you can see that I'm plotting the difference. So blue is improvement, essentially, when we use a XR belt mesh versus the XR CONUS, and the pinkish colors is slight deterioration. So the color bar is it's a little skewed here. But yeah, so a lot of the improvement starts to pop up beyond day 4, and then especially in day 5 and 6, and then mostly over the Western Pacific, and then appears to be propagating into the Eastern Pacific. And you can see how, interestingly, over the CONUS region, we actually don't see a lot of change, and this is sort of the interesting part of these results. But so this is average over all the forecasts over that 2-week period. So if we look in more detail using those similar plots as before, now we can see some differences that kind of pop up. So what I'm highlighting here, this is the same plot as before, but only for that 2-week period where we have overlapping forecasts between XR belt and XR CONUS. In the thin black contours, yep, you can see them. I'm highlighting larger RMSEs that appeared in our XR CONUS simulations. And now you can see how a lot of the improvements, which are highlighted in the blue colors, associated with those larger forecast errors that we saw before, and that the higher resolution upstream seems to have an impact, especially over the Eastern Pacific, but also over that larger RMSE blob over the CONUS at that day beyond day 5 forecast range there. And of course, we didn't see a lot of the improvement was definitely meeker in that forecast average plot that we saw in the previous slide, because we're basically averaging over some deterioration in the forecast at other valid times, which certainly warrants more investigation into why the XR belt was producing slightly worse scores. Out of curiosity, we also initialized using ERA 5 instead of GEFs, but this is for a much shorter period. And over just 5 initializations, and of course, these are deterministic forecasts comparing to the ensemble mean from XR CONUS. And it's kind of interesting to see how the height errors deteriorated over the Western Pacific, but that definitely needs to be looked into further. But there's a sensitivity there to the initial conditions. And in the Eastern Pacific, you can see that one of the forecasts, so actually the other thing I wanted to highlight is that you can see the differences are more vertically oriented, which we would expect because we're changing the initial conditions. And so we're actually changing there's more sensitivity to the initial conditions. So I think that's why the forecast errors are more vertically oriented versus diagonally, which is more flow dependent type of errors. But you can see how at the Eastern Pacific, we see this improvement over one of the forecasts, during one of the forecasts when we use an ERA 5 initial conditions. And that seems to maybe have improved the forecast down at later forecast lead times downstream into the CONUS region. And this is my last couple of plots here is just a summary of these large scale error growth between that within that mid-latitude belt. On the left, I have the RMSE for each of those sectors, comparing their forecast errors across the different regions. And you can see most of those errors are coming from the Western Pacific and Eastern Pacific. The CONUS, actually, the RMSE plot looking here, similar to what we saw earlier, is that there's very little change, at least on average. But I think the key thing here is that if you look at the bias plot, it's really clear that even though HR belt does improve it slightly, the forecast scale, there's certainly a huge systematic bias there that certainly warrants further investigation and digging into. And so in summary, so we utilize different versions of the variable resolution mesh capability to investigate how the impact of increasing the model resolution upstream has on day 1 to 7 forecasts over the CONUS region. Seems like there's some improvements in the forecast errors, but that's mostly occur over the Pacific. And also there's certainly this large systematic bias over the Western Pacific region that certainly warrants further investigation. And then that little experiment that we did using a different initial conditions from ERA 5 reanalyses showed that there's certainly large sensitivity there. So we're going to be looking a little bit deeper into where that sensitivity comes from over the Western Pacific. And that's it. Thank you.
Hey, thanks for your talk. Are there any questions from the audience?
Hi, May. Really cool stuff. During this time of the year, the Mayu front is very active over the West Pacific. So I'm curious if you have an idea of like how active the Mayu front was during this year, or if the simulations are handling that front differently, maybe.
No. But I will look into it. Yeah, if you want to talk further, I'm happy to chat too.
Sounds good. All right. Thanks.
Any other?
Small question. Is there any particular reason to choose non-aerosol aware Thompson scheme?
Oh, that was just the scheme that was available at that time when we made these experiments. Yeah.
You have time for one more quick question if anybody has any. Okay, I don't see any. Oh, go ahead.
Back in. Okay, yeah, I was wondering, it is interesting that the errors are bigger in over the Pacific than over CONUS, actually. So, but I mean, also you expect maybe there's a lot more going on over CONUS in what is actually showing up as the patterns, right? So, do you have you talked at all about looking at what other factors may be, sort of, is there a way to tease out the part that was really the influence from upstream versus, other features, other flow patterns that are actually impacting what's happening over CONUS, for instance, right?
Yeah, I think that's a good point. I mean, we only looked at 30 to 60 degrees, that band, and obviously there's maybe southern flow that could be influencing the moisture flow, for example. So no, we haven't looked beyond that, but I am starting to look into the just south of that band, between 5 degrees and 30 degrees north, and then try to see what the errors look like there. Yeah, thank you.
Okay, thanks. Our next speaker is Khan Du, and Khan will be talking about accelerating high-resolution downscaling of meteorological variables via self-supervised deep learning.
So I'm the second to the last speakers. Finally, it's my turn. We changed different days now, talking about machine learning, and my topic today is accelerating high-resolution downscaling of meteorology variables via self-supervised deep learning. So thanks to my collaborator and co-authors, Shuhua has do all the simulation and provide me the outputs, her poster over there. And my PI, Yang Chang, also thanks to the session chair. So my topic is I'll go over the deterministic downscaling using pseudo global warming and wolf simulation, and then also go over the deep learning methods using machine learning model, and then go the model evaluations into comparison between the evaluation and the machine learning group with the ISD database, and then compare between the group and the machine learning. Also use the train model to predict the climate change projection in the future. For assessing health impacts, we need requires very high resolutions of Mirachi data, about less than 1 kilometer resolution. However, the global climate model output is very coarse, is greater than 120 kilometer resolution. And then we want to have high resolution downscaling in Mirachi using WRF to study the impacts of the regional climate changes on public health under the shared socio-economic pathway scenarios. So we have SSP 1, 2, and 5. So where once we have all the clean energy, SSP2 is like right now we have the mix between clean and then the mix between fossil fuel, and SSP5 is the most aggressive scenarios where we have all the fossil fuel. So we have done the downscaling using WRF, the deterministic model. There's a lot of advantage. For example, the model results the small scale weather event, leading to more accurate forecasts. Also enables for high resolution climate simulations. We can simulate the Mirachi parameters and their dependency simultaneously. And we also get the support by a strong user community and extensive resources. So however, it's come with the more disadvantage, like requires significant computational resources, particularly for file resolution and large domains. So for example, we have done the downscaling for 2 states, North Carolina and Virginia, with 1 kilometer resolution. It will take up 12 hours for 1 simulated day with all the maximum output of the CPU. So here's showing the deterministic methods that we have done with the poster P2 over there. We have done by 2 steps. The step 1 that we project the differences in the future climate based on the SSP scenarios. So we have the difference, we apply to the EI5 analysis data, and then we have the initial boundary conditions. And then the second step that we use the initial boundary condition using WRF for downscaling. So showing the figure on the top figures, that we have the WRF domain configurations for 3 domains, DO1, DO2, and DO3, where DO3 is the most finest domain at 1 kilometer resolution over North Carolina and Virginia. So we have done the downscaling, and we have got a very nice, beautiful simulated T2 over DO3 as shown on bottom plots right here. It captures the 5 scale temperature across the North Carolina and Virginia, and also improves the local climate analysis for health assessments. But it's too slow, so we think we use the deep learning approach, showing this flow charts. That's the top of the diagram, so that we prepare the training data sets. We have the ICBC from EI5 for 2006. We use that to fed to the WPS, and we get the MEM for 2006, and we run the WRF simulations, and we get the T2 and Q2 for 2006. So the MEM and the T2 and Q2 is the input features for the deep learning. So right here we use deep learning autoencoder methods, and we use the features to train the model. So once we train the model, we have the model application. So we apply for the SSP scenario as shown on the bottom of the figure. So we have the SSP, and we derive the ICBC for SSP using pseudo global warming. We fed to the WPS, we get the MEM SSP. And then once we have a trained model, we use MEM to predict the T2 and Q2 temperature for the SSP scenarios. So in this, we completely bypass the WRF simulation, which requires the most computational resource here. So this shows the simplified version of autoencoder algorithm. We have all the features showing on the left. That's the T2 from the EI5, the surface pressures, so the wind property. So all the features we fed into the encoders. So the encoders will compress the features. It will compress the feature into the latent space. That's the smallest space that contains the most information. And then we decode the latent space back to the input. So here we twist the model, thus the input becomes the WRF temperature shown on the right-hand side. So it tries to predict the WRF temperature output. And we have trained the model on intensive data sets. So right here we have 87 features, include all the 2006 icon beacons from the WPS. That includes the meteorological parameters, the wind V10, U10, T2, the language index, and more. 2 spatial variables, the latitude and the longitude. And we target the outputs, the 2006, the WRF output for T2 and Q2. We also done the validation we test on the SSP55 scenarios datasets, and we use that to forecast the future climate conditions. For evaluation, we want the mean bias of the temperatures less than 0.5 Celsius as a benchmark, and we use the integrated surface database from NOAA as the observation. So shown here is that the benchmark performance, the WRF and machine learning performance over the O3 compared with observations. For the orange colors from the WRF simulation, and blue colors from the machine learning. So the WRF simulations show very strong performance over the O3 as shown on the table on the perform very well compared to the observations with the mean bias about 0.2 to 0.6 for machine learning, and all the correlations above 0.9. So when we compare with observation. So here we use the train model and we project the prediction over the SSP 585. The figure, the time series right here shows us the hourly T2 for the WRF SSP 55 from the period 2046 to 2055, and also the machine learning models in the orange color, orange line. So they both overlap to each other implicitly, which means that is the machine learning model can replicate the WRF simulations of T2 at 1 kilometer resolution over the O3, and it's also achieved very high correlation with WRF outputs with the correlations above 0.95, and it obtained the mean bias below 0.07 Celsius across all terms in 2006, as shown in the table on the left. So we have very high correlation and very low mean bias compared to the WRF output. This one's spatial variations for 2006 over the O3 compared to WRF simulations. The left figures on the left is from the WRF simulation. On the right is from machine learning using autoencoder methods. So they look really similar. Is the machine learning methods effectively reconstruct the spatial variations across the O3. So we have trained the model using the base case 2006, and now we want to use the trained model to project the climate conditions under the SSP 55. So in the time series right here, the one on the left, that's the differences of daily average 2-meter temperature. So the blue line right here is the SSP 55 from the 2036 to 2045. Minus for 2006, so minus for the base case. The orange line is the SSP 55 in the further future is 2040 to 2055, subtract for the base case. So you can see the difference in temperature compared to the base case. It accurately predicts the T2 increase under the SSP 55 scenarios, and also it captures the significant warming across both states. So as showing on the figures on the right here, time series for machine learning in Richmond, Virginia, and Raleigh in North Carolina. So the green line, the SSP 55, and the orange line is the base case 2006. So you can see the green lines have higher temperature compared to the base case. So sometimes it demonstrates that the SSP 55 is the T2 by 4 Celsius at some point, some place. So in summary, compared to the WRF simulations, the machine learning model significantly improves the computational efficiencies by approximately 2,000 times compared to WRF. It will output every hour in less than a second. So it also effectively captures the dynamic meteorology changes, and it's performed well compared to the observation with WRF. We have high R correlation and low mean bias. So once we have the methods, it can be generalized to other uses. For example, once we have the autoencoder, we can use that to predict the PM2.5 or the concentrations air quality forecasting. And the model have demonstrated the capability of to project future temperatures under different SSP scenarios. So thank you, everyone.
Thank you. We do have time for a question or two. Are there any from the audience?
Yeah.
It looks like we have one online.
Hi, so we chose the 2006 as the base year because we use pseudo global warming. So the historical data is go from 1990 to I think 2000. So or 2006 is the middle of the year of the 1990 and 2000. I repeat that as the base case.
Okay, go ahead and then we'll take the other online question.
Can you think of any way to extend this to precipitation? Or is there a way to do that with this method since you only use the analyses?
Yes, it's simple. So right now we train the model with the group input data for T2 and Q2, and we got very good correlation for even both T2 and Q2. For the precipitation, we just get the group output for precipitation as the label, and we train the model with that. It's also feasible to do it. Yeah. The training cost for autoencoder, so we use that. We use the literature to training with the A100 or the H100. It takes about maybe 5 days to train for 1 year. So very fast.
Okay, we do have time for one more question. You left a lot of time for questions. Good job. No? Okay, I do have one, and I was wondering if you were planning to train on more years moving forward, just so you capture a wider sample of potential events.
Sure. So for machine learning, when you train, it cannot extrapolate the data. So when you train with the data set, it's very good to interpolate between the data. So if you train more years, you have more data set, then the model have bigger capability to have more accuracy, capture the extreme event.
Okay, thanks. We'll move on now to our final speaker. We have Jay Zhang, who will be talking about land-atmosphere interactions in a long-term MPAS NOAA-MP simulation.
So yeah, hello, good afternoon, everyone. So this is the last talk of today, and then my name is Zhe. I'm a project scientist at RAL, working in the NOAA-MP land surface model group. And then I want to thank this a lot of the this work is supported by the NCAR's Earth System Prediction Across Scale (SPAD) initiative, and I also want to thank my collaborator here at Chen-Ling, Judith, Abby, Mike, Shanghai, Julia, Jimmy, Mac, and Yaga. So it's a lot of cross-lab collaboration. I'm happy and excited to share some of the results here. So to start with, the first is our motivation is to do this across scale. So it's looking a lot beyond, a little bit beyond the traditional weather forecast time range. So by S2S, we mean 2 weeks to 6 weeks. And then by looking at this diagram, it shows the predictabilities across after 7 days to 30 days, the predictability transition to hypothetically to land. That the hypothesis is if you have a realistic land surface initial condition, and if the model can correctly capturing this land atmosphere coupling processes, that will help you with improve your S2S forecast. So what are these land atmosphere processes? So the land atmosphere coupling process can be summarized into some feedback loops, for example, summarized on the figure on the right, that basically starting from soil moisture and then it interact with surface temperature in the red loop, and also the soil moisture precipitation feedback that's coming out on the blue loop, and also interact with cloud and radiations. But before we do the S2S predictions, there have something that we need to do, because after 2 weeks of forecast, the model evaluation actually based on removing the model climatologies. And also in the long-term more forecast that the model of and that some of the models deterministic, statistical, systematic deterministic biases will resemble the model climatology biases. So to start, we start to build a coupled NOAA-MP MPAS long-term simulation. So the goal is to first look at and evaluate the model performance at climate timescale. So start with doing at this one initialization run for 25 years at global 60 kilometers. And then we can start to establish this model climatologies for some of the extreme events. For example, how do you define your 90 percentile T maximum temperature to look at your, to define your extreme event in the model. And the third one, we can look at this land atmosphere coupling strengths, which can help us diagnostic some of the land atmosphere coupling processes. So the setting we use, we start a 25-year simulation starting from 1999 and run it to 2023 at global 60 kilometers. We initialize the model using ERA5, and then with prescribed SST and CIs, it's updating daily from ERA5. So to think about it, it's more like AMAP style, only driven. So after your initialization, it's only driven by the SST. The model version is used MPAS 8.2.3 with the mesoscale reference suite, which is showing on the right. We replaced the land surface model from NOAA to NOAA MP. So that's what we, the land surface model. The computational cost, so I'm not saving a lot of this 3D historical file and then the restart very frequently, but mostly on the 2D pressure level diagnostic and surface diagnostic. And then the cost is roughly about 12K per year. So it's not a lot compared to like the very high resolution run, but it's not like non-legible. So yeah, to start, how are the model performing? So first we look at global precipitation. So remember this is 60 kilometers, so it's not convection permitting. And it's and also depends on how you look at what's your reference data. So here we look at the zonal mean precipitation on the top and then the spatial pattern on the bottom. So obviously in the middle, it's the equatorial. If you compare it with GPCP precipitation, that the blue line MPAS is actually doing okay. But if you're comparing with the state of art satellite precipitation, IMERGE, that the MPAS is obviously underestimating. And then the big tropical precipitation underestimation occurring in the Eastern Pacific and also equatorial Amazon and also the West Africa. On the other hand, you can see this large overestimation of the subtropic precipitation under in the Indian Ocean and then the maritime continent. So if you look at seasonally, so how does the model look at seasonal precipitation? So this large overestimate in the subtropic region starts mostly in the MAN, JJA, and SON season, and then the most underestimating in the equatorial ITC in the Amazon occurring in spring and DJF. So this is for precipitation. How about global temperature? Start with, we also look at zonal mean temperature. So the zonal mean temperature globally, you look at, is actually the largest differences, the tropic and the subtropic is doing okay, but the larger differences occur in the polar region. So above 60° north and then 60° south. So what it happened is if you look at this large cold temperature biases in the Arctic region, and then if you look at it also seasonally, what you look at is the flipped pattern that you see in the winter SON and then DJF, that is large temperature, cold temperature in the Arctic, but then in the summer, or the MAN, JJA is the southern hemisphere. You also see that in the Antarctic region. So this is for the what's going on. We have to do some simple climatology analysis looking at the global surface temperature, surface radiation balance from this CIRRUS data. So simple to look at this, we look at the seasonal short way down, short way up, long way down, and then long way up radiation. So to summarize, you see this, the short way down is always overestimating, and then MPAS is looking long way down is always underestimating. So this gives us some hint that the model is not doing right with some cloud-related radiation energy balance. So this is first, we have some speculation is about cloud. The second one we look at is CIs. So CIs albedo, we derive it from CIRRUS. So you look at the short way upward divided by short way downward to look at the radiation or the CIs albedo. So in MAM, where you see that the CIRRUS give you about much higher of a CIs albedo at about like 0.75 or 0.8, but MPAS at CIs is set to a default value at 0.65. So this is something we see that also in the Antarctica, in the SON also it is underestimated the sea ice albedo in Antarctica in SON season. So this is about albedo. What else? We do some tests with sea ice thickness to start with. So sea ice thickness is also set to default in 3 meters, which we think is a little bit too high. Then we set to do a little bit shorter run to look at the sea ice albedo as to sea ice thickness. So if we reduce it to 1 meter, that you look at the temperature warmer differences, it's not only limited to the Arctic Ocean region, but it's propagated much south in DJF temperature in the North America and also the Eastern Europe and Western Asia. Another very sensitive variable is called snow thermal conductivity. So it's an option in NOAA-MP that snow thermal conductivity is a function of snow density. So think about if you have a very fresh snow, that the snow layer very high, that the snow acting as a very insulated layer that permitting your exchange of energy between air and then snow. And then when the snow gets compacted, so going to the right-hand side, you see this condensed and then old soil, that old snow, that the snow thermal conductivity will grow. And then it will give you a stronger exchange between the land, the snow surface and the air. So we do this by tuning around this default option 1, is this the blue line in the right-hand side curve, and then change it to 3, is a constant at very high snow thermal conductivity. That it shows the differences in the bottom where you see that is North America temperature getting about 2 to 3 degrees warmer in DJF, as well as in the whole Eurasia, but then it will amplify the winter warm temperature biases in the Asia region. So the idea here is that snow thermal conductivity and then sea ice thickness, they are very sensitive parameters to your 2-meter temperature model climatology. So yeah, this is for global temperature and global precipitation. How about we can look at in a seasonal, but looking closer to North America. So of course, this is 60 kilometer, I want to emphasize again, but then it's underestimating the biggest precipitation differences occur in the summertime in the central US, which we understand is like the convection season, and then not only in the central US, but also in the southeast, where there is some isolated convection over the southeast, but the model wouldn't able to represent at this coarse resolution. And then the other thing, this is for seasonal temperature, seasonal precipitation. Other than that, I would say if you look at the mid latitude or the central US precipitation, and then the scale is 200 per 3 months. So it's kind of surprisingly okay to me. And then the next thing is to look at the seasonal temperature too. So we already talked about this cold temperature biases in DJF in the lower right panel. What about the seasonal temperature in the JJA? That's the summer warm temperature. So these summer warm temperature about 2 to 3 degrees, it's associated, of course, to the dry precipitation deficit, which we know that's something before, that it's the dry precipitation deficit and then the warm temperature feedback. That's what we talk about in the land atmosphere interaction. So what are these co-located land dry soil moisture or dry precipitation summer warm temperature biases actually resemble this missing key land surface processes in coarse resolution. So I want to highlight 2 processes that are missing. For example, so right now, the first one is this shallow groundwater interaction schemes, which developed by Gonzalo and Mike put it in WRF. So right now we're not running them in the MPAS, but hopefully we will want to activate it in the future. The next one will be the dynamic crop growth and irrigation. So this is the study we do, but then interactively simulating dynamic crop growth and irrigation in this largely agricultural region, which will show you a very high and enhanced precipitation recycling. Also want to note that these 2 processes are resolution dependent, that if you do it at very coarse resolution, that might not be able to see it. But right now it's doing at 60 kilometer. So another feature we want to look at is the how do you look at it statistically, what the if you have a precipitation deficit for springtime 3-month precipitation deficit characterized by this standardized precipitation index, and as a soil moisture proxy, can you do some statistical correlation with your summertime heat extremes? The answer is yes. To look at this, we look at the correlation coefficient between your springtime precipitation deficit and then your summertime heat. So the green dotted region showing this significantly negative correlation between springtime rainfall deficit and summertime extreme heat. And we can find out there's a lot of widespread land atmosphere coupling hotspots in reality. So this is showing in observation, ERA5 and GPNI merge precipitation. But how does model represent these features? So there are some in this land atmosphere coupling hotspot, for example, in the central US, there are some significantly negatively correlated, but they're less widespread and less of a magnitude. Okay, so I'm transitioning to my last part. How do we do? So now we have built a 25-year climatology. How do we use it in S2S prediction? So this to give an example of the 2021 Pacific Northwest heat wave. So indicated by this red triangle between week 5 and week 6. So the idea is to, if we initialize our weekly forecast every Monday and then going backwards. So you have 1, 2, 3, 4, 5 initial conditions going right before into the heat wave. And then adding some white noise perturbation to give us some ensembles. The question to ask is, how far in advance can the model provide reasonable forecasts to this heat wave temperature anomalies? And then there, of course, there's some trade-off between if you want to act earlier with less confident forecast, or if you want to wait longer for a more accurate forecast, but then you will have less time to respond. And also I want to say this, many of the evaluation is based on we're removing the model climatology. But first, the model climatology based on this heat wave weeks is actually performing okay in this box region, Pacific Northwest, resembling where the heat wave heated the strongest. And then on the bottom, so the top is from ERA5 and the right from MPAS for this particular week. At the bottom, I'm showing this ERA5 temperature anomaly in that year, which means the red temperature going is as high as 8 degrees temperature anomaly, indicating the intensity of this heat wave. And then on the right-hand side is the time series of this box region, where you see this red curve showing the temperature anomaly much warmer than the black line is the ERA5 climatology. And then this is how a model performs. So I'm showing here 4 different initialization. You have 25 days of lead time, and then 18 days of lead time, 11 days of lead time, and then 4 days of lead time. So the model result can be best summarized by the figure on the right, which give you 4 different lead times of model ensemble 2-meter temperature. We want to get the model temperature, 2-meter temperature anomaly as close to the 7 degree high mark on the represented by this blue line on the top. So if the model is initialized 4 days ahead at 60 kilometers, it can capture many of the ensembles that can capture this high temperature anomaly over this region. But what's interesting is to look at these earlier initialized forecasts that although some of them are the earlier that the ensembles are very widespread, but then some of the ensembles can capture about 4 degrees and is consistently 2 to 3 weeks ahead of the initial condition. So the summary is the MPAS model shows some reliable S2S prediction skills in this Pacific Northwest heat wave event. And then some of the ensemble can capture this heat wave 2 to 4 weeks ahead. And then this some ensemble doing better than this 4 Kelvin or 4 Celsius temperature anomaly for this period. So this is my last slide and a summary. So to start, this is model climatology that looks okay with 3 degrees temperature biases, but mostly they're in the Arctic high latitude region related to sea ice thickness, sea ice albedo, snow thermal conductivity, and some of the polar cloud. And then for the next step, there are a lot of things to do. There's following this sub-X protocol to run 20 years weekly reforecast. So Abby is preparing the initial conditions, and we will be perhaps doing it in later half of this year. And then to look at land surface initialization is to run NOAA-MP spin up and then replacing a more realistic land surface condition to initialize this weekly forecast. And there's some discussion going on for regional refinement, 60 to 15 kilometers, 60 to 3 kilometers, and some of the offline OIMP runs. Some of this S2S prediction are really valuable because we can supplement it to run offline OIMP and then to look at agricultural application, for example, that we can build up early warning system. Yeah, thank you so much.
Hey, thanks. Any questions? Okay. Are these 25-year continuous MPAS simulations? Or are they reinitialized anywhere? No? Oh, okay, nice. It's good to see you're not having any issues with drift. Potentially.
Yeah, the drift. So we do a 25-year trend temperature look at and then compare with ERA5. There's something climatologically, for example, we didn't add like CO2 warming effect and then aerosol effect to the, so there's only, what you see here is SST driven model internal variability.
Okay, thanks. Any other questions before we move on? Okay, I'm going to be following up with you later. But now it's time for discussion, and I'll hand that over to Bill to chair.
Well, congratulations. You've made it to the end of another MPAS WRF workshop. Time goes by way too quickly. While this is the last session here, this discussion session, it's not the last event at the workshop. Tomorrow, we've got 2 mini tutorials. The first one, UX Array at 8:30, and the second one, MPAS Jedi at 10:15. So if you're interested in either of those, I know I'm going to be here tomorrow. Please come, and they'll be here. So same place. And for this session, it's a general discussion. So you shouldn't feel bad about bringing up something that's, for example, on our Tuesday discussion, we focused on NOAA and our collaborations, particularly physics, et cetera. This is general, so you can bring up whatever you'd like. I would like to start with some housekeeping things, although we'd like your views on if you have any, or in this case, to give you some information on what we're thinking about. First, I would like to talk a little bit about the tutorials that we have, because they're very popular, both the virtual ones and the in-person ones. We're going to be moving the MPAS tutorials from our spring-fall slots that we've been using to summer-winter, which is right now where the WRF tutorials were. And the reason we're doing this is because we've got a fair amount of feedback from our university folks that, of course, spring and fall sits right in the middle of their semesters, quarters, classes. And so that's not very convenient. So we're going to switch the MPAS tutorials to summer, winter. Now WRF, we may switch them to spring and fall. We haven't quite decided what to do there. One of the issues there, of course, is that there are a number of us who work both of them. So having them both in the same kind of period wouldn't be optimal for us. We're also considering not only a switch, but potentially going to 1 per year. But we would make that decision based upon, I think, demand at this point. One thing to note is that all the WRF tutorials are now virtual. So, and typically we are accommodating 70 to 80 people. So actually it's an efficient way to do it. From an instructor standpoint, it's not the most fun way to do it because you don't get that personal interaction. But I think the virtual ones seem to be working very well for the participants, and it works okay for us. So starting with there, does anyone have any comments or suggestions in terms of community training needs we should be addressing that perhaps we're not doing so much on right now? And anybody out in the virtual world, I think if you raise your hand, we'll catch you and you can speak up. Okay, that didn't generate much. Very good. So in terms of tutorials, I think this is an opportunity to announce what the next ones are. There is a WRF tutorial. That's, of course, virtual, as I mentioned. Coming up next month, the 14th through 18th of July. Again, virtual. The registration is now open. So please register. Even though it's virtual, we do set a limit on how many people we accommodate. And I think that limit's somewhere between 70 and 80 for a number of reasons. So if you know people who want to take the WRF tutorial, it's coming up and the registration is open. The next MPAS tutorial is going to be in person here in Boulder, September 15th through the 19th that week. And it's going to be MPAS and MPAS Jedi, essentially 2.5 to 3-ish days of MPAS and then 2 to 2.5 days of Jedi. We're going to open the registration in early July. So quite a ways before it, because people obviously would have to make travel arrangements to come here and everything else. So you'll see that. And we're going to have a virtual tutorial on MPAS this winter in this switch to the winter-summer mode, but we've still need to determine the dates. So that's not there. And I think the biggest thing we look for when we schedule that typically in January is to not coincide, of course, with the AMS annual meeting. So that'll be our primary thoughts there. Okay. The workshop format. Now, this one was different in that we didn't charge any registration fees. And we were fortunate to have a pot of money we could tap into. But that pot of money is sort of a one-time pot of money. So I don't know that we're going to have that next year. I would expect that everybody, well, people like the fact that it was free. For some of you, that meant you could come. For others, it means you didn't have to pay a few $100s or whatever, or your organization didn't have to pay. If you've been to past workshops, you notice that, for example, we didn't have a free reception here because that was a high cost part of the event. So we had to cut back on that. And the lunches were a little more simple, I'd say. Again, a cost thing. Does anyone have any comments about how that worked? Okay, you like it. Okay, all right. So I got a thumbs up there. And again, I don't know if we will do that next year. Given the response we got, though, I think we will certainly look into it. But we would have to kind of start looking into it soon, because again, we were fortunate enough to have funds sitting in a place that we could access, but that will not certainly be the case next year, is my guess. We're going to have to line those up much further in advance. But I think the response we got to having no registration fee, the number of talks that were submitted, we got talks from all over the world. I thought it worked very well. And as you saw in the emails before the workshop, we were concerned about people attending and being able to participate. So we're very pleased to see that. Go ahead, Gretchen.
I'm just going to make a plug that, yeah, we will try to see what we can do going forward. We are open also to sponsorship. So feel free to reach out to me, Gretchen, or Bill, if that would be something. We can keep it really low cost, but just want to open that up to folks. Thank you.
Thank you, Gretchen. Does anyone have any thoughts on when we do this? So we've tended to, we'd like to have it in June, and there's another workshop. Next week is the CESM workshop, so they actually occupy this space also. So we're working around them. We're also working around the June 19th holiday, that if it sits in the middle of the week means it's not a week that works for either CESM or us. We would like to schedule next year's as soon as we can so we can get this location. Does anyone have any thoughts on early June or late June? I personally like earlier in the month, but early is better. So maybe you'll hear soon that we've locked down a date, because I think we're going to try to lock down a date much sooner now, instead of thinking when we get to around the end of the year, geez, we've got to schedule this, and then finding the rooms are taken or whatever. Okay, thank you. All right, that was mostly the housekeeping stuff. I wanted to put up a list of what we feel are, we, meaning those of us in M-Cubed here at NCAR, what we've looked at as kind of our critical MPAS development areas as a way to maybe start out what people may want to talk about. Here is a short list. It's the major things we're thinking about. It's not necessarily in order. And I would say it's very hard to put down an ordered list because so much of what we do is dependent upon where funding is coming from, what areas of expertise we have people that we can put on these projects to work. So oftentimes we can't necessarily do what we think is our highest priority or make as much progress because of the mapping of funding and expertise to these development efforts. But I will also say it always helps when we have outside groups that want to work with us in the development, because one of the things now with certainly with MPAS that we're seeing is that at times we're developing for applications where we don't have strong in-house needs for them. And the way to do the best development is to work with folks who need it so that we get feedback immediately when things don't work. And invariably, when we first do things, they typically don't work. So with that, I'd like to open it up to anyone. It doesn't have to be what's on the screen. It can be anything you want to bring up. Please, what's on your minds in terms of how this enterprise is going forward?
Bill, I just wanted to add to this list that MPAS Jedi is also an area that we really also welcome feedback on. And one of our high priorities on that right now is usability for the broader community. But again, we need to identify resources and time for that. But I just wanted to open it up to make it clear that we'd also welcome feedback on MPAS Jedi.
Yes, this reflects what I think about. Please, go ahead. And I will say MPAS Jedi, if you look at the Jedi development, MPAS is ahead of just about every other model that they're working on in there in terms of its capabilities. Go ahead.
So around we are developing the MPAS Hydro. We're not decided on the name yet, but we are coupling MPAS with Hydro, and that's I think that's very high priority for us. And hopefully by this time next year, we will have this system ready and have some results to show, and then they're probably open. We will probably release that to the public. So stay tuned for the MPAS.
Okay, please keep talking with us if there's anything you need to facilitate that in terms that we can do here in terms of build mechanisms, things to make sure that that works. Yes, and in terms of a name, well, ChemPass is a really nice one. It's got a really good ring to it. So I encourage people to be creative and try some things out.
Is this on? I just want to say we're working on a logo for ChemPass, and so we'll reveal something next year. But on a serious note, how much interest is there in having an easier way of bringing in additional physics parameterizations? Like, I mean, we have a fairly small selection of physics schemes right now and 2 physics suites, and I think that confers some advantages, but I think there are probably things that we could do on the software side that would make it easier to bring in additional schemes from WRF. And we could probably do that in a modular way. I think there's concern that these things get dumped into the MPAS repository, and they become a burden. But I think there are ways on the software side that we could make it possible to latch onto them from a separate repository and have them get compiled into a physics driver at build time. But if you don't select those, they do nothing to the model code. So if there's an interest in having a broader set of physics schemes available, maybe there are things that we could do on the software side to prioritize that idea.
I think we are all interested in seeing the pool of available physics schemes grow. I think we have an initial, software architecture that we have worked out together that is working. And I think NOAA GSL will continue to contribute physics, but there might be other groups that are interested in contributing. We saw different parameterizations from the Brazil group, as I'm sure others, have interesting things. So yes, I think continue to flesh out the method for bringing parameterizations in a sustainable way, right? That doesn't overload. The M-cubed group is a great idea. I think the list you have is, it's wonderful. I think it aligns with several of the priorities that we have. If I were to add something, would be the community fire behavior model that we saw the presentation by Pedro Jimenez, talking about the WRF fire and the possibility of coupling that to MPAS.
So we have ongoing discussions with the group from Brazil and Monon with Salo, and especially with regards to the future of the Grell-Freitas scheme and its extensions, which we heard quite a bit about this morning, actually. We're going to keep in touch with them, and it's not impossible that the Monon suite may come in as a separate compilable suite with MPAS. We are particularly interested in outside groups that develop suites and test them, et cetera, that they can be available to the community easily. So I'm thinking, for example, of the WRF SV2 suite. And I think using the suite descriptions may be a really good way to distinguish these physics that come in and to give ownership of them to the groups that contribute them. Because as opposed to in WRF, where people would contribute individual physics components, and then sometimes they go in a different direction. And we really want to make this a community model, both in terms of its availability, but in terms of its support and development. And the one thing we can't do at NCAR nearly as well as, for example, GSL and Brazil, is to do all the testing and tuning and evaluation of advances. We have very limited capabilities in that regard here. So that is something we appreciate, and we're going to try to move forward quickly on.
May I add to Michael's, suggestion or question in terms of expanding, like adding more physics or physics suite. I just want to, I think it's worth mentioning this coupling aspect, right? Like just not adding like a one by one, but within the suite or whatever, we want them to kind of communicate with each other, especially with this chemistry or aerosols. So I guess it would be good to think about this, who's gonna do the coupling, or how we wanna, I don't know. I mean, we just need sort of guidelines, or my 2 cents.
I very much agree, and I think we are at a critical time in this regard as things start coming in. For example, the transport of chemical species, scalars, et cetera, how to generalize that so any physics that come in that should do transport can just do so. And other aspects of coupling, for example, the aerosols and other schemes. Yes, I agree completely, and we're thinking about that for sure.
Is less related to physics, but my group would love to transition to using MPAS instead of WRF for regional climate. We are somewhat concerned about the lack of spectral nudging, though, at this point. So I'm
Ah,
wondering if that's in the works at all, or if anybody's thinking about that.
okay. I'm not a fan of bringing in spherical harmonics or anything like this.
Or some other
However,
form of
there is a way to do spectral nudging using wavelets. I don't know if Craig Schwartz is here. I don't see him because he's the one, he and I have been, well, he's been working on it. I just gave him a few ideas. So I think we have a way to do that in MPAS very, very cleanly.
I will talk to Craig about this.
That
Thanks.
you should talk to Craig about it. So yes, so that possibility is there. A few people have asked me about nudging. And we have within MPAS an IAU capability incremental analysis update for the data assimilation to bring in increments that effectively, I don't want to say nudges those increments in, but it looks like nudging. So we have the hooks to do nudging if you're really that desperate. So it can be done, and it wouldn't take a lot of coding. So that's there, but the wavelets definitely is, I think we're getting close to being able to be serious about putting that in and using that in place of more traditional spectral nudging, but it'll give you the same kind of thing.
I just wanted to add a comment to this and then ask a question. So as somebody who has been criticized for using MPAS for Kelvin waves or tropical waves over the oceans for not having ocean atmosphere coupling, I think like having ocean coupled would, as a priority, would be beneficial, not just for my own purposes, but for people interested in that regard. And then, so a big portion of the WRF users use the idealized test cases, and I didn't see much of WRF idealized or anything idealized during this workshop. And I know the idealized capabilities within MPAS are limited, so I'm curious if there are any plans on bringing some of those idealized test cases capabilities from WRF into MPAS, or if that would be left off for, say, CM1 or other models?
So there are a number of idealized cases that they're not well, you have to look for them. But if you look in the download section, you'll see some, not quite as many as WRF. What we don't have that WRF has for limited area domains is we don't have open boundary conditions. We could put those in, but it seems like, well, we have WRF and we have CM1. So we've tried to focus on capabilities that take advantage of MPAS, I would say, in MPAS structure. However, if you have idealizations you want to see, come talk to us, and I think we could relatively quickly get those in or illustrate how to do them. I think it would depend specifically what cases you actually would like to, idealized cases you'd like to see.
Yeah, I'm asking as a general question. I don't have anything in mind, but I've just heard that from the community, like the tropical cyclone test case, for example, is one that it's not an MPAS yet, but you know, that's just one example. I was just curious for benefits of the community for knowledge.
Yeah, and so for example, for that one, George put that into WRF. I'm not sure he wants to take his time to put it into MPAS, but we could. Oh, George, there you are. Do you want to put it in? Yeah. Okay. Yeah. So part of it is it exists in another system, but you're right. You'd like, for consistency purposes, if you're going between idealized cases and real data, or more complex idealized cases, you'd like to be able to do it within the same system. I think it would be actually very easy to put in because I know how it works. So I teach it in the WRF tutorial that is, I explain it. So.
Thanks.
Right.
Laura has her hand raised online. So Laura, do you want to unmute?
Yeah, I think one of the issues that we have
at MCube is that, I mean, there's this huge amount of pull requests that are now sitting in the GitHub repository. And some of them actually do include like physics suites. Like, for instance, I'm thinking of the EPA physics suites. And so I think we're a bit kind of guilty in that respect, that we need to figure out a way to kind of transfer some of those pull requests a little bit faster, so that, you know, they don't get out of sync with the most recent MPAS release. Because I'm thinking on my end that, I feel pretty kind of actually bad about it in a sense, is that by having those physics and physics suites sitting so long in a pull request in the GitHub repository, that actually has the negative impact of having physics people kind of not wanting to kind of contributing to new physics and new physics suites in MPAS. So I think it's our job to kind of figure out a way to kind of accelerate that transitions between pull requests and what goes into